خليه شغال وش الصوت. هذا الميكروفون وهذا الشاشة زمان وشير بس الشاشة الثانية كان في صوت يتكلم ودي برادي
شغلت البث.
تمام يعني المفروض الآن شغال
Would go online. I don't mind.
What is that? So I was somewhere here. So I was. Yeah, okay. Well, thank you very much for this. That's fine. As I said, I think it was and I was. How would you expect that?
And I have a video in that.
Hello. Very good. Thank you. Fine, thank you. Yeah. Okay. I have a USB to load. Yes, yes, it's quite different. I added a medical.
In my slides, I have a video.
I checked today morning.
Okay.
Yeah, everything alhamdulillah fine.
Okay, that's good.
Okay. So let me start with this one. Which one is yours?
This one is
This one. Right. We just want me to update them, right?
sorry.
You
Yeah,
want
you
me
need to
just
update.
When is yours?
I'm checking now because they changed it
Oh, they changed.
previously, so not immediately. I think they changed some time ago, so I'm not sure.
Uh-huh.
I thought it was in the morning.
It is, right.
Yeah, this one, yeah,
right?
yeah.
Okay, it's gonna be in the morning.
Yeah.
So let me just update this.
So this is the first one. So David is giving first one. Okay, yeah. So this is like 4 of us, yeah.
Nice. To be honest, yeah. What a nice auditorium. Yeah, really well laid out. Good visibility, huge screen.
We have another one in this floor as well.
So you do? Wow.
Yeah.
Wow. Very impressive.
From here, right? So
This is,
I-
just one second. This is the old one. I think.
I'm gonna remove them now.
Yeah.
I'm gonna add the new ones.
Nawab al-Rais. What does Nawab al-Rais mean?
Vice presidents.
I'm reading there
Oh, I see. Oh,
because Nawab in Urdu language, Indian language, it means say the feudal lord.
I see. Oh. On my business card.
It is. I think it's not PowerPoint. It's PDF files. Right?
Yeah, it's PDF file.
Okay, so I need to convert it first.
Convert it,
Convert it from PDF to PowerPoint.
but that might change the thing. So
Really?
yeah, can you just keep it PDF?
Okay, if you'd like to keep it as a PDF,
Yeah.
then it's better to keep it in the USB. And
Okay.
once your presentation comes, we can move to the USB and we can do the presentation there.
But it's 10 minutes, so if you do it that time, then it will take time. I mean, why don't you just upload it on the desktop and then we can
Alright.
just open it.
Okay,
I can come and open it as long as it is there.
right, okay. So Dr. For Dr.
Rashid.
Rashid, his presentation gonna be a PDF file. So I'm gonna add it to the desktop, and once his presentation comes, you need just to open the PDF file.
Yeah, if it is there, I can open
Once
it.
it
Yeah,
comes.
yeah, yeah. Can you open it to just see that
Okay.
working?
Did you copy? Is it from USB? No, okay, it's from the desktop. Okay.
So just make sure that it's copied and yeah, this is the one.
Okay, so Doctor, once it's opened,
Yeah,
the PDFs,
yeah.
yeah, it is a PDF.
Would there
Once,
be a problem?
once it's opened,
Yeah.
just please hold it and move it to the next screen there.
Mhm.
So
We'll
it
have
can be
technical
appear.
support. So help us.
Okay,
Once your presentation comes, I'll come and help with this.
okay.
I come to the stage and help with this.
Yeah, what I can do is that I can share PPT if you want through my drive if you want.
Oh, I don't think we have enough time. for
Okay,
this
okay, that's
for a
fine.
moment.
Okay, so that's fine.
Yeah.
You can eject,
All right,
just make sure that you copied it because it might not be there.
it is copied.
Okay.
The title of everything is the same, right?
Yeah. I think I have just to.
Yeah, just open it and check it that it is there.
It is indeed more. Yeah, perfect.
Yeah.
Yeah. Doctor, which one?
Blue
is
one.
yours? The blue one.
Yeah.
Okay, thank you.
It's the 40 MB PowerPoint.
Already. I think I've already added yours.
Yeah, but this is it's a brand new talk. I
That
mean,
one, that one?
because that one, because I have medical and
Sure.
medical now. When I sent it, it was just environmental.
Right, okay.
And I took note of the
I
theme.
think your session is the first.
Yeah, that's right.
So I'm gonna remove them all.
Yeah.
And add the new ones.
That's
Up to here.
correct. That is correct.
So. That one?
That one. Yep.
This QR, in case any of the audience has any question.
Oh, okay,
So
yes.
at the beginning,
Yeah.
You can just jump in. If they have any question, you can just scan the QR and
Okay.
they can maybe scan it through slide. All the questions will come to my iPad.
Yeah, I'll let you moderate.
Sure.
Yeah.
So
So did you get it? Did
Yeah.
you get them in?
everything is fine now. Doctor,
Can we-
the last one, I think it is,
Is it DK Fundus?
I think this for Bandar, right?
Yeah, probably.
Yeah, already.
I just want to check mine.
You'd like to, you can.
So don't worry about the questions, we have.
Yeah, I'm not worried about questions. I just want to make sure my slides are there.
All right, so I think I got it under here. I need to cut it and take it to the beginning of his slides.
You do not see my slides.
Your slides are not there?
No, those are somebody else's slides. And after my name. Oh, those are mine.
Those are
Those are
yours,
new one,
but
right?
those are the old ones.
Was that the old one?
Can I have the USB one more time, please? I'm gonna remove it now. And here's your presentation.
directly.
Okay, here, sure, sorry for. I need to go through this one by one. This way.
Maybe it would be easier to open them like we're doing the first sheet. But anyway,
I think so. I think so. It's better to just introduce you and then open them from that USB. That would save our time as well.
Yep.
Because opening them one by one, it's gonna take time. So once we introduce you to this
Yeah,
slide,
okay, so you better put it on
then,
the
yeah,
desktop.
that's what I'm gonna do. I'll be around if you need any help.
Thank you. We're already 5 minutes into
Yeah,
my
yeah,
time.
yeah. This one or that one?
Yes, that's the right one. That is correct.
You can recognize from the size, right?
Yep, that's right. Yep.
Mute the live stream. Mute the live stream. People all over the world are hearing all of these discussions.
Sorry. Thank you very much. Okay, so that's fine.
So you'll find my talk.
Once you just introduce you and your stage comes, I'll come to the stage and I'll be talking. Yeah.
Assalamu alaikum wa rahmatullah wa barakatuh. In the name of Allah, the most gracious, most merciful. Here at IIU, we are very delighted to have you on the second day of events that are full, packed, and jam-packed with interesting talks and sessions. And as followed from the first session and the second session that was presented yesterday by our esteemed guests, we will continue on this journey, and we will be delighted to also welcoming our esteemed members that will be talking to you today about today's theme. So I would like to introduce myself. My name is Dr. Mustafa Muhammad Zayed Yildash. I am an assistant professor of the College of Computer Science and Information Technology from the Computer Engineering Department at Imam Abdurrahman bin Faisal University. I'm very delighted to be here to be basically a chair for this session that will host a number of esteemed and distinguished guests, some of which are local and international. So today's session that will start from the morning will basically be about high performance computing and cybersecurity and cloud computing. So high performance computing is one of the most essential tools fueling the advancements of computational science and the universe of scientific computing. And the universe of scientific computing has expanded in all directions. Quantum computing has the potential to offer giant leaps in computational capabilities, impacting a huge range of industries, from drug discovery, as we've seen yesterday, to portfolio organization. Realizing these benefits requires pushing the boundaries. Developing algorithms, researching more capable processors, and creating tightly integrated quantum classical systems and tools. Accelerated computing is transforming the world of AI, cybersecurity, and computational science. From the data center to the cloud and the edge. Building cybersecurity solutions that take advantage of data science and data science techniques and addresses cybersecurity from data first lens is difficult. Now, developers can take advantage of AI and data science tools and frameworks and pre-trained models, as was introduced yesterday. And infrastructure optimization software to tackle cybersecurity challenges in new ways. Today, we are delighted to welcome you, especially welcoming on stage a distinguished list of speakers who will entertain us with an in-depth overview of the latest technologies, innovations, experiences, best practices, and recommendations that will help us in academia and companies, industries, and our beloved nation reap the benefits of high performance computing and AI and supercomputing. So without further ado, I would like to kindly invite our esteemed speaker, Professor David Keyes. He'll be on stage. So Professor David is Professor Keyes is a professor of applied mathematics and computational science and the director of the Extreme Computing and Computing Research Center, having served as the dean of the Division of Mathematical and Computer Science and Engineering at KAUST for its first 3.5 years. Also an adjunct professor and former full foundation chair, professor of applied physics and applied maths at Columbia University, and an affiliate of several laboratories of the US Department of Energy. He graduated in aerospace and mechanical sciences from Princeton in 1978 and earned a doctorate in applied mathematics from Harvard in 1984. Before joining KAUST, among the founding faculty, he led scalable solver software projects in ASCII and SciDAC programs of the US Department of Energy. So without further ado, welcome you.
Thank you. Thank you, Professor Mustafa. And I need to call up my talk here. If someone could help me find it. It's while we're finding the slide deck, it's a great honor to have this invitation and this audience to this extremely well organized and executed HPC Saudi. I have changed the title of my talk somewhat to reflect a medical research emphasis since learning of the special theme of this year's. So it's not just environmental statistics, thank you kindly, but genome-wide association studies. And the good news is that the same algorithm applies across this seemingly very wide space of applications. So the additional slides can go in without too much extra introduction. So up front, I'll provide the highlights. I'll present a new algorithmic technique that reduces the memory requirements and the processing requirements of dense linear algebra operations that arise in both environmental statistics with max likelihood estimation and genome-wide association studies. The savings come from loosening the accuracy requirements relative to traditional dense double precision linear algebra. The conventional linear algebra very often oversolves such problems anyway relative to the quality of the data and the requirements of the estimation. And so tuning accuracy requirements to resource budgets in terms of memory and computing is really a very powerful knob to give to applied computational scientists. We do this by combining on-the-fly discovery in these large dense matrices of blocks of low rank or blocks of small magnitude relative to the main diagonal blocks. Both such situations turn out to be very common in physical applications, statistical applications, and machine learning, but neither is typically exploited. But we offer both as a good way to use advanced hardware, including GPUs. And so again, there are two applications today, the first of which is an advanced look at the 2022 Gordon Bell finalist presentation that we'll be making at the US Supercomputing Conference in November. And the second one actually is related to the 2018 Gordon Bell Prize, but that prize was purely brute force using the dense double precision linear algebra, and we will show ways of improving upon that. For those who may not be familiar with the Gordon Bell Prize, it's awarded once a year for the past 35 years to some application. It can't be just a kernel. It has to be a full application that exhibits one or more of these properties: algorithmic improvements, improvements over the previous state of the art, measurements of scalability, strong, faster execution with more processors, or weak, bigger problem size for the same execution time and more processors, some efficient use of a bottleneck resource, whether it's flops or the memory bandwidth or the IO, and or of course peak performance. And it should have solutions that are transferable to other applications and solutions that translate beyond one-of-a-kind architectures. And it could be a high watermark for some impactful application. As I say, this is a prize that's been going on for 35 years. I have actually had the honor of having it once before, but this is the first time that the Middle East is a finalist for the Gordon Bell Prize in any way. It's typically the US, Japan, or Europe. And this is the title of the page, the paper that will be presented in November. And I'll give you a little preview of that this morning. Let's see if I can. Yeah, so today's results are still preliminary. We have extra time before November. But the application is one of geostatistics. Saudi Arabia is about to place billions of dollars worth of solar collectors and wind farms across the country. Where should they go in view of current climate conditions and questions of this nature? When should farmers plant? When should ski resorts plan on high traffic? All these kind of things are examples of economically important geostatistical applications. And we have both a spatial and a spatiotemporal demonstration in our paper. This is not simulation, I would emphasize. This is emulation. Of course, supercomputers are very often used to simulate the climate using first principles, conservation of mass, momentum, energy, and so forth. But this is using data to interpolate or extrapolate using statistical models. And it could be sourced either from observations or from expensive simulations. And it's an alternative to doing many simulations and then taking means. But it does assume a correlation model, which is the added value from the statistician. As I say, this is an economically important application, especially to the kingdom in the near future. And whereas simulations based on partial differential equations with their meshes and their sparse matrices are often memory bandwidth bound and can't really use all those petaflops and exaflops that are built into today's systems. The emulations based on dense covariance matrices tend to be compute bound, better balance of resources. The opportunity here is to estimate the maximum likelihood function. Contemporary data sets are often huge. We can be speaking of millions of observations, and each observation is correlated with each other. So right there, you have 1 trillion entries in your matrix. And from these observations at p points in space and time, we want to find a fit. If you put those observations into a dense matrix and try to factor it by conventional means, it's an n-cubed operation. And of course, as I mentioned, n squared in storage. So 10 to the 6 locations would be already 4 terabytes in double precision, taking advantage of symmetry. So this is a quote from a leading geospatial statistician in the US National Center for Atmospheric Research, who basically says, computing hasn't kept up with the density of observations that we now enjoy. And indeed, as I mentioned, a 1 million observation system requires 4 terabytes. And the traditional approaches of statisticians are to assume global low rank, which is not true of these covariance matrices, or to zero out the outer diagonals where the correlations are small, both of which are rather severe. And better approaches are just to assume hierarchical low rank, to find those isolated blocks within the matrix that can be reduced to low rank, and to find the small magnitude blocks which can be replaced with lower precision data. And as you know, 4 terabytes is a lot, and you know how long it takes to write 4 terabytes in flash memory from your own backup disk. Now, in order to qualify for the Gordon Bell Prize, one is advised to collect letters from the applications community. So I have 3 quotes from leading statisticians about our paper. We have controllable and high accuracy, typical of universal level precision while exploiting mostly half precision, keeping relatively few tiles clustered around the diagonal in their original dense format. By reducing the memory footprint of such models, they allow much larger data sets to be accommodated. One of our favorite quotes from George Ostrakoff of Oak Ridge National Lab says, as you know, my motto is statistics is, quote, the physics of data, and statistics is to machine learning as physics is to engineering. Your Gordon Bell campaign is accelerating the use of spatial statistics to allow it to keep up with exascale hardware. The secret sauce behind this is a package that you can find at our GitHub repo called ExaGeoStat. And the architecture of that is, some general applications at the top, 2 tasks, modeling into statistical model and then inferring from that model. We need some optimization library for that fit, for that training. And then we need the parallel linear algebra libraries as part of the optimization code. We run that over various frameworks. And the key thing there in the middle is a task graph showing the factorization of a dense matrix in the Cholesky format, where the colors on the left of those nodes are tasks on the individual tiles, color-coded on the matrix to the right. And you can see that at various points during a traditional tile-based elimination or factorization, different amounts of work become available. And these are choreographed to minimize the vertical, which is time, and maximize the horizontal, which is concurrency at any given point. This is built on top of dynamic runtime systems to handle the heterogeneous load that such a breakdown gives you, and built on top of conventional stacks and a wide variety of architectures at the bottom. And this is all delivered primarily by our research scientist, Sameh Abdullah. So ExaGeoStat's 3-fold framework is to generate synthetic data sets to test on, and many other people use that part of it alone, and then the maximum likelihood estimator, and then the predictor for inference. So you could say, in analogy to machine learning, that this is the training phase, the expensive one, and this is the inference phase. And this has been ported to many of the world's largest systems, including number 2 Fugaku with its A64FX, Summit at Oak Ridge with its NVIDIA, Hawk in Germany with its AMD EPYC, and Shaheen 2, our own system, which entered the world in 2015 as number 7, but is now number 97. And you'll hear later this morning about it being refreshed. This is the function that we want to minimize in order to find the matrix sigma, which is the covariance matrix, and actually to use that covariance matrix to find the parameters theta, which define the model. So L is a scalar, sigma is a matrix, and the bar of that is its determinant, and the inverse, of course, is its Cholesky factorization. Z there is a vector of the data observation. So Z could be 1,000,000, and sigma could be 1,000,000 by 1,000,000 matrix. So what we want to do in order to find the optimal value of theta is to evaluate this function many times, each one of which requires a matrix solve. And there are a variety of optimization methods that I'll shorten here. And in fact, I'm going to shorten the next few slides because I want to get to medical stuff. But you have a random process Z, the weather, the climate. You find its expectation, that's the mean, and then you find the variance, the difference from the mean, which could be positive or negatively correlated depending on different locations, S1 and S2. And you build all that into a dense matrix. The variance is down the diagonal, the covariance is off the diagonal, linking different points. And then you can infer from your known observations ZM to your unknown locations ZN, where you don't have any data. And all of this just involves a lot of matrix inversions. And the different functions that can be used for that max likelihood vary on the left between spatial and on the right between spatial temporal. And we're not going to go into the details except to say that there are various parameters that statisticians have characterized as important. And you can see from on the top, we have an exponential covariance fit. On the bottom, we have a Gaussian covariance fit. And from left to right, it goes from weak to strong. And you can see, you know, in the graphics, the strong, you know, variance from one point to another in those larger domains with slower tapering. And these are some of the functions that we want to fit in that big matrix. So now to get to the meat of the talk, it's all about the linear algebra. For most of scientific history, if you want to solve a symmetric matrix, you do a Cholesky factorization. You only need to store half the matrix. That's in gray double precision. In blue, we find that the small magnitude blocks off the diagonal can be represented with single precision with no appreciable accuracy loss. In fact, as the correlations become weaker and weaker and the magnitudes are smaller and smaller, instead of setting them to 0 like statisticians do, we can keep them, but store them with fewer bytes. And rather than making a rigid diagonal by diagonal division, we can do it adaptively on the fly as we evaluate the magnitude of those matrix blocks. Another trick that's about 20 years old in applied math is to replace those off-diagonal tiles with low-rank representations. For instance, the singular value decomposition, where the full information of the big block is represented by a subset of row and column vectors that, when multiplied together, reproduce the information of the big block. So we call that tile low rank. And that can be done adaptively, and that can also be combined with lower precision. And this picture on the right is the algorithm that I'll propose today, and you can see its advances over runtime. So why are we messing around with mixed precision? The answer is obvious to anybody who's been following modern architectures. If you go from dense double precision to dense half precision, you don't just save a factor of 4. You save a factor of 16 if you can exploit the tensor core performance of these little convolutions of dense matrices. So we want to ride the hardware with the algorithm. And you can see here for 5 different runs. On the top, you have, by the way, this is in flops, so up is good. So let's start at the bottom. That's the dense algorithm on a Pascal. And if you go to blue and red with the dashed curves, you're following just NVIDIA's advances in architecture with the same algorithm. But if you go to the solid curves, for instance, compare the dashed blue to the solid blue, that's the algorithmic improvement on the old voltas. And then you can see the algorithmic improvement on the amperes. And the good news is that those can be used together to get like a 10x improvement from algorithms and architectures over the past 8 years or so. How do we choose the blocks that are relegated to lower precision? There's some good theory of that just came out. In fact, it says 2 up here, but it came out in 2022. I won't go into this slide except to say that when the ratio of magnitudes of the blocks falls below the ratio of successive precisions, you can use the lower precision. And how do we choose dense versus tile low rank? We estimate whether the work to produce the low rank factorization would be greater than the work to produce, to stick with dense. Whichever one is cheaper on the fly, that's what we use. And so this is a dynamic computation, and therefore the individual cores could go out of load balance with each other. So we require a dynamic runtime system to allocate the work. And the one we chose for the Gordon-Bell is Parsec. We run over many of these systems. There's not a standard yet like there is with MPI, but one of our favorites is Parsec from Oak Ridge, because George Bosilka has been willing to work with us to build in the features that we need for this very dynamic computation. We've been graced to run on Fugaku in Japan, formerly the world's #1 system on the ARM A64FX. And it's a very large system. So far, we're using about 1/10 of it. And just to cut to the quick, here are 27 blocks and whisker plots. These are how statisticians evaluate their results. So the Top row to the bottom row is examples of weak, medium, and strong correlation for different data sets. Going from left to right, you see the three parameters of this 2D spatial fit, the variance, the range, and the smoothness. And within each box, you see in brown, red, and blue, the three algorithms. So the blue algorithm is the cheapest. It's the mixed precision with the tile low rank. It's that, algorithm in the lower right corner of my linear algebra slide. The brown one is the expensive one from the upper left corner where everything's dense and everything is double precision. So as we move from left to right within a box, we're using fewer and fewer computational resources, getting the problem done faster, or being able to accommodate a larger problem in a small memory GPU. And what you can see are the means in the dark line in the middle. And then the boxes go out to 75 and 25% percentile accommodation of the data. And the little whiskers at the edge are the outliers above and below. And you can see that for the most part, there's very little sacrifice in moving to the cheaper method. You can see that some of the boxes are skewed, and that's interpreted here on this slide in terms of these 75 and 25% statistical marks. Now, the key for this is the mean square prediction error. And for the dense algorithm, the mixed precision dense and the mixed precision tile low rank, you can see there's almost no degradation in predictive accuracy with this large computational savings. And from our preliminary results on Aku, you can see for a variety of algorithmic things with successive numbers of nodes up to 16,000, that there's up to three times less time for the same problem size. The matrix size is going from small to large along the x-axis. And alternatively, you could say for the same time, for the same y-axis, number of seconds, you can solve a problem up to 3 times larger. So this, of course, is data dependent, but this is the typical environmental data set. And if you look at the footprint of those Cholesky factors, you can see in the weak correlation on the left, you're saving, about a factor of 3 or 4 of the 4 terabytes. And on the right, you're saving much less, but at least paring it down to the optimal. So now I'd like to move to a totally different problem, but from the same PhD thesis of Dr. Rabab Al-Omari, who graduated this year. She came to us from KAU, did her PhD with us, and will be heading to a postdoc at the Innovative Computing Lab run by this year's Turing Award winner, Jack Donguera at University of Tennessee and Oak Ridge. Actually, this is just 2/3 of her thesis. She had another application on acoustic scattering using the same dense matrix technology. And by the way, she won the German Computer Center Gauss Award in 2020 for that acoustic scattering work. But now we'll talk about her latest work in our group, which is the Genome-Wide Association Studies. This is a way of sort of exercising the central dogma of biology that the genotype predicts the phenotype, structure predicts function. If you can build a large database of people and categorize their genomes and the kind of diseases or traits that they have, obesity, height, whatever, then when you get a new genome sample, you can predict how that patient will turn out. This is not just useful in medicine. This is useful, for instance, in doing drought-tolerant, salt-tolerant agriculture using the genomes of plants, which is another big use of GWAS at KAUST on our Shaheen systems. The cast of characters is the number of patients in the study. We have about 500,000 British patients in an encrypted anonymous database. G is the number of genetic markers that are considered. We consider up to about 5 million genetic markers from human DNA, known as single nucleotide polymorphisms or SNPs. And P is the number of phenotypic markers that you want to infer about, will this patient with this DNA have these characteristics? Now, of course, a simple linear fitting model is very idealized, but it's commonly used in biology today. So we'll have a matrix X, which contains the patient genetic data, that's given. We'll have a matrix Y, which contains the patient trait data, that's given. There are genetic types, P phenotypes, and of course, N patients. So those are very large matrices. And then beta is the matrix that we will try to fit, that we will try to find to produce this mapping of genotype to phenotype, from structure to function. And the central equation is in the middle there. We want to get, we want to minimize this. We want to get the best fit between y and x times beta. Beta is the set of parameters to be fit. And we add a regularization term, lambda times beta squared, in order to try to keep from overfitting the model. And also that lambda gives a nice diagonal dominance to the matrix that we have to solve. So the lambda is a tuning parameter that can be used to do the quality of the fit. After some linear algebra, we get the equation boxed in red at the bottom. And you'll notice two things. By the way, this is the same calculation that won Gordon Bell in 2018, but for the dumb way: fully dense, fully double precision, no exploitation of the mathematical structure of X, which is symmetric and positive definite. And you can see here the symmetric rank K updates that build X transpose X. And you can see, sorry, it's X transpose X that's dense and symmetric. X by itself is not. X is not even square, so it couldn't be symmetric. But that overall matrix in the inversion sign is symmetric, positive, definite. It can be factored by Cholesky using the tools that we just looked at. And so we can illustrate this on a variety of hardware. It ports well with a variety of precisions. And just cutting to the chase, as with the environmental problem, without going into the application, just looking at the HPC aspects, you see here on the right 5 diseases with their box and whisker plots, the medians in red, 25 and 75 percentile marks in the solid boxes, and the extremes in the whiskers. And you see these are mapping the mean square prediction error, the actual y versus the y that is fit with x times beta. So this is a quality of fit. And across each box, you see different algorithms. So in green is the dense double precision default, the one that would be expensive to compute with millions of patients. And as you go across, these boxes in yellow are varying degrees of exploiting low precision and low rank. And the very last one, obviously, where we have 90% half precision, it's not good. It's always good to see that the algorithm eventually breaks down. You have to have a knob to get the accuracy you want. But all of those other replacements of dense double with single and half precision along the way from left to right are obviously very legitimate replacements. They give you the same statistical model with no degradation of accuracy. And on the right is our adaptive model, where we're not restricted to diagonal bands, but computing on the fly. And the accuracy is as good as the uniform case. And once again, a plot where the red shows the improvement coming from the hardware alone, from NVIDIA's hardware engineers, a factor of 1.3 over 5 years or so there. And then the algorithm gives a factor of 2.2, 2.5, and together get about a performance improvement of 3x. So this is the algorithmic opportunity. It's a very simple, common core problem to do Cholesky factors and solves. It could be applied where there are memory constraints like geostatistics, where there's PDE constrained optimization like subsurface seismic modeling with Hessian matrices. It can be used with adaptive optics, where we have energy constraints on the top of mountainsides to control the flexible mirrors in the telescope. It can be used in real-time constraints, like decoding wireless signals, which is, again, a matrix convolution problem. It can be used where there are running time constraints, large databases in chemistry, materials, biology, and so forth. The matrices come from covariances, integral equations, sure complements from PDEs, Hessians from optimization, non-local operators from fractional differential equations, radial basis functions from unstructured meshing, kernel matrices from machine learning. Do linear algebra, see the world. All the applications come to your doorstep. And I'd just like to thank my team, including Rabab on the lower left, who's in common between the two projects. The Oak Ridge team is on the top. And again, our philosophy is to build this algorithmic infrastructure, which is callable for many applications, diverse as they may be, and ports them to many and always evolving architectures. And with that, I thank you for your kind attention.
Thank you so much for the outstanding presentation. And
Thank you.
now we will also welcome our esteemed Professor Native Hpc. He's a he's a professor at the University of Ohio State University. So Professor Panda obtained his PhD in computer engineering from the University of South California. His research interests with high performance computing. His research in high performance computing, high performance networking, also called InfiniBand. Also big data analytics, Spark and Hadoop, deep learning, cloud computing, virtualization, GPU, and subgroups, file systems and storage, and scale computing. He has published over 500 papers in major journals and journal conferences related to these research areas. Professor Panda has served, or rather serving, as a program chair or co-chair or vice chair of many international conferences and workshops. So without further ado,
Thank you, Professor Mustafa. I need some help here. I think to open the slides. So. That is. It's not working.
Also, just a quick note before I forget, there is a QR code, so for the audience, if you kindly also have any questions or any of our guests, we highly encourage you to participate using the QR code. If you can actually scan it with your phone, it'll give you a good opportunity to actually ask questions and learn from our esteemed speakers. And we'll also be able to partake and deliver messages as well. And again, this is the QR code. You've got access to your phone supports scanning QR codes. And yeah, and also on social media, we have the hashtag of the event. So please, if you have Twitter or different social media, we would be delighted to see you also sharing your thoughts and insights about today's experience and for the conference. So without further ado, please,
Okay. So thank you again, Professor Mustafa, for the kind introduction. Thanks to the organizing committee for inviting me here. This is my first time in Saudi Arabia, but I'm enjoying. Thanks for the great hospitality. So today I'll be talking about high performance, deep learning, machine learning, and data science on the modern HPC systems. Broadly, how do we take advantage of all the latest technologies and then try to make it easier for all the end users, whether you are running HPC application or deep learning or machine learning and data science. Now, one thing you will be seeing over the years, what is happening is high-end computing, I'll call it high-end computing, that comprises a lot of this stuff, is changing over the years. The last 3 decades, we are seeing multiple stages. If you go back, like the stage 1, we started like almost like 30 years back with traditional supercomputing, high-performance computing. Then in the 2000, the big data analytics came. So HPC and big data analytics, people tried to combine together, and that changed a lot of things, saying how we can take large amount of data and then try to make sense out of it. And then, of course, many of us know, like in the 2010 onwards, we are into the new wave of HPC and AI, whereas machine learning, deep learning are coming together with the data. We also not only want to make sense out of it, we want to see whether the machines can be actually be trained to do those kind of analysis. But now we are entering a new era, which is like the emergence of the computing continuum. So I'll explain that a little bit later in the next slide. But if you take a look at the left-hand side, this is the traditional, like HPC systems or data centers. We are focusing on those 3 stages, like scientific computing, big data, data science, and AI. But look at the right-hand side. These days, the data are not centralized. It comes from all different places. It could be coming from an on-field sensor. It could be coming from the drone. It could be coming from any other places where things are being fed. Now the question is, where do you do the computation? Do I do the computation at the edge? Or should I move the data to the near edge? Or how much data should I move it to the cloud or even to the HPC center? So that is the kind of the new domain we are entering. And I call it like a computing continuum. And a lot of people also in the field are also trying to address that. So let's take a look at an example like agriculture. Traditionally, agriculture, has been there. I mean, the farmers have a lot of knowledge. Can we even change that to a AI-driven precision agriculture? Okay. So think of like, let's say there is a big field and it has some kind of a disease has happened and the farmer wants to actually spray. So these days, typically most of the time, the farmer actually, based on the history information or based on his or her expertise, they know, yeah, this disease is there. They will just spray. So they take the tractor and spray the entire field. Is that the most optimal way to do it? May not be. Because if you have a large field, might be only some part of the field has the disease X. Some other parts might have disease Y. So I should not be unnecessarily spraying pesticides all over the place. So can I take help of the technology, like I fly a drone and the drone actually takes the picture and I have a neural network model running behind the scene. It will exactly point me saying this part of the field has disease X, this part of the field has disease Y. And then I take that information and drive the tractor with that information so that I can do very precision spraying. Okay? So if I do like this, that has a big impact, not only to the environment, I can reduce the cost, I can have a very good yield, and it helps everybody. And as you know, like our human population, world population is increasing. So in the next decade, we will see there is a big need of generating food with the lowest cost. So you can think like we can take our systems challenges to these kind of applications. So that broadly leads to this broad challenge, how to design high performance and scalable middleware for these high-end computing systems with that computing continuum for all those stages, 1 to 4. I indicated we want to solve the traditional one, but also we want to look for the future. And as you can see, like the underlying the systems are becoming all the heterogeneous systems. You name about CPU, GPU, DPU, IPU, XPU. A lot of these devices are coming. How do you take advantage of those and also the cloud resources? So while we focus on that, we also need to take a look how the end users are trying to design their workflows. So traditionally, if you see, people used to only do high performance computing or big data or machine learning. These days, they are all combined. Very complicated workflows people are coming up so that in some part I can do HPC and the next phase I do machine learning, then I can do big data or go back to HPC. So we have to propose software infrastructure so that this becomes much more easier. And that's what I call like a convergence of the HPC, deep learning, machine learning, and data science. We want to design the software, which not only works on the on-premise system, but also on the cloud. And especially here, I'll be trying to focus on this talk, can MPI-driven middleware be really used? That will be the theme of my talk, because MPI, those of you know, like a message passing interface standard, it came from HPC, but most of the modern machines have MPI. So can we actually leverage that, not only to do HPC, but also machine learning, deep learning, big data, data science. So I'll give actually example, and that's what in my group we have been working on. So this will be kind of the outline. I think when the slides got incorporated here, I believe the fonts got changed somehow. My excuse for that. So I'll start with this, the top Hpc MPI library. Many of you might be knowing that. That is the largest project, longest project I've been doing for 22 years. Then I'll go into a little bit of high performance deep learning, machine learning, followed by high performance Spark and data science applications. And as we are working on the on-premise systems, I'll also be talking a little bit about how we are deploying it on the cloud. The same software, we are deploying it with the cloud at the AWS, Azure, and Oracle. And if some of you don't know, over the last several years, we are actually also providing commercial support. Even though I have been in university, a lot of people have been using our software. They want commercial support. So we have a commercial spin-off. I'll talk a very little about that. And then towards this end, I'll introduce this new NSF AI Institute, which I am leading, called Icicle, and that is actually addressing the future, the computing continuum, and then I'll conclude. So this is the overview of the Hpc project. If some of you are not familiar, we started this project in 2000, 22 years back. Many of you must have heard of InfiniBand. That is the networking technology. It was introduced in October 2000, almost 20 years back. And prior to that, in my group, we were working on Myrinet, Quadrix. So those were the traditional systems, if some of you remember. And when this new networking technology came, my team members and I were at the right time, and we just jumped in, saying, wow, this is a new technology. Can we actually take advantage of these features? The hardware was there, but nobody knew how to design software. So we actually first demonstrated a supercomputing O2 almost 20 years back, the first MPI running over InfiniBand. Okay. And it was a struggle to even run 8 nodes. And these days, 8,000 nodes, 10,000 nodes of InfiniBand are being deployed. So we have been having in that ecosystem. And we started with InfiniBand, but now we support all the network. If you see Omnipath, IWAR, Rocky, even AWS EFA. Recently, we introduced Rockport networks, and very latest links are 10 and 11, Broadcom, Funnelist network, you name any network which is being used in HPC, our software can run. Okay. And not only that, we have gone over the years with MPI, all the standards. So right-hand side, you can see like this stack is now currently being used by more than 3,000 organizations in 90 countries. And just from our website, we crossed 1.6 million downloads just from our website. This is the OSU website, but the stack is available also in the SPAC, Red Hat, SUSE, OpenHPC. We don't keep track of those. So I'm very proud of my team. Being in an university, we are really providing production quality software over the years to all these people. And literally hundreds of thousands of people in the world are actually using our software to advance their sciences. Okay, so I'm very proud of that. As you can see, this is like the downloads, how it is increasing over the last several years. But this is our software architecture. The way we have designed, if you see at the very bottom, the left-hand side, these are all the modern networking technologies. So they are features, they are protocols, and those are actually the bread and butter of our research. So anytime new networking technology come, or a CPU technology, DPU technology on the right-hand side come, we first try to explore and come up with designs and then try to publish this. And in 6 to 9 months, we actually take those designs and push it to our software. And in fact, in my lab, we have 200 servers continuously doing QA testing. Okay, so we think of just like any other company trying to come up with production software stack. We have full-time software engineers. A lot of students work on this. And as we go along, as you can see from the top, we provide interface to MPI, PGAS, and also hybrid MPI plus PGAS. And the middle part is our research. So this is where all these innovations come in. And then we try to link it with the upper levels. So I'll just give some sample numbers here just to get a feeling. This is very latest servers. Many of you might be using AMD Milan, the EPIC architecture with InfiniBand SDR 200 gigabits per second. The top left, you can see this is intra-node. And look at the latency, 190 nanoseconds. Like an MPI to MPI communication within the same socket, we can actually deliver 190 nanoseconds. So we are designing software designs at a nanoseconds level these days. Okay. So each and every, if you are familiar, even if you do a if then, if else, while, all these things matter, how the conditional branching taking place. So we even go to that level to really give you the performance. And then the lower one is saying internode. Here we see like this Mellanox ConnectX. So it's like a 1.6 microsecond. We get very good bandwidth there. So those are the point-to-point. But many of you, if you are familiar with the MPI, is a big challenge in design collectives. So these collectives are like all-to-all, broadcast, reduce, all reduce. And if you don't optimize those, you don't get the best performance. So this is where we have been coming up with our own designs. We also leverage the in-network computing capabilities of, there is a Mellanox / NVIDIA has something called SART in networking. So we have done a tight integration. And as you can see, like in many of my slides, I'll indicate to the papers. You can go and read more details, but you see if you do these intelligent designs, instead of like the green, the orange one, we can actually give you 5x speed up, 9x, 6x kind of things, and that gets reflected into the application. But then in the collectives, there are not only focus on blocking collectives, there is a lot of focus these days on non-blocking collectives. Okay, in fact, in the next few years, you will see there is a big discussion going on there. The idea is that blocking, let's say I do all-to-all, unless the all-to-all finishes, the processes are just spinning there. They are not producing anything. And as the system size scales, we are going to these 7 million core systems and all, most of the times you lose in the collectives. On the other hand, the non-blocking collectives, that is the way we actually also live in our life. If something is happening, I'm not sitting idle. Like, let's say I want to go with my friend for a movie, and the friend says, yeah, I'm coming. So I'm not just sitting idle there, right? I mean, I'm doing my work, and as the friend comes, I go. So it is like a non-blocking operation, and I can overlap the computation with communication. So we have coming up with these newer kind of algorithms. You can see the left-hand side, like the green and the blue, I can reduce the latency, and then also see the dotted line, the percentage overlap, I'm able to push. So that means I can give you a lot of overlap capabilities so that the processors can continue to execute while the communication is happening. And that especially becomes very helpful. I'll introduce the DPU technology a little bit later, and you will see the difference. This is the very latest number. We made a new release recently, just I think a few weeks back. This has the leaf fabric support. If some of you know, this is the Slingshot 11. I think Aws is getting the system. A lot of Slingshot 11 systems are coming, and see, we are able to deliver. As of now, this is available. You can download and run it on your system, 2 microseconds. Node to node, we can deliver 2 microseconds. And if you see the bandwidth, like we are able to saturate the entire network, like 24 gigabytes per second or 42 gigabytes per second, we're able to give the bandwidth information. Now, those are on the CPU side, but now the next thing is I'll introduce the GPU. I mean, GPU has been there for many years, but the question is how we can make them first-class citizens, okay? So this is the concept. How many of you, I don't know, have heard of a term called CUDA-aware MPI? Anybody has heard? Okay, some of you have heard. So we introduced this term actually at ISC 11 from my group almost 11 years back, and that has become now common. In any software stacks you go with GPU, they are trying to utilize this. So what does that mean? So let's say in the right-hand side, if you see there's a GPU, that is the square. Most of the time you do a CUDA mem copy. That means, let's say I give a kernel to the GPU performs the operation, but I need to send the results to other GPUs. Okay, so typically what I do is I do a CUDA mem copy to the host. Host does an MPI send. The other end, you do an MPI receive, and then again do a CUDA mem copy. So there are 4 steps involved, and especially if you are using very large messages, you encounter a lot latency. So what we did in the 2011, we worked very closely with Mellanox and NVIDIA at that time. There was a technology called GPU Direct Rdma. So if the GPU and InfiniBand are sitting the same PCI bus, I can actually transfer data between this GPU and the device. So for the end user, you don't need to even touch CUDA for communication. For computation and all, you use it, but otherwise I can say MPI send from a send device buffer, and then receive, and I said, okay, put the data in the receive, and everything happens. Look at the animation inside the MPI library. You don't have to touch anything at all, okay? And the library is very intelligent, so we introduced this concept, and that has a big impact. Like you can actually these days, again, sorry for all these things got disturbed, I don't know. So now very latest what we have done here is the on-the-fly compression. So these days, if you take a look at the very latest GPUs, there are so many cores are sitting. Let's say you perform the computation, but during the communication time, these cores are sitting idle. And especially if I have to send, let's say, 4 gigabytes of data from this GPU to the other GPU, can I do compression on the fly? And that also lossless manner. And if I can do that, I'll reduce the length of the message. So that means I can reduce the latency and I can give you the best bandwidth. And that's what I have done. This paper was actually last year's IPDPS best paper finalist. And here we are running a AWP ODC. It's a seismic simulation. And as you can see, if you use this kind of on-the-fly compression, I can give you boost in performance, 18%, 35%. So it's the same hardware. We're just playing with the software and coming up with intelligent software to push the performance higher. And those are like the NVIDIA GPUs. We have been continuously working also with AMD GPUs as they have come. So our stack can actually run on both CPU and, the AMD GPUs and NVIDIA GPUs. We have plans to we have started working with Intel GPUs. You will see the results will be available. And this is actually the Corona cluster at the Lawrence Livermore National Lab. And as you can see, like we are comparing MHPs2 and OpenMPI. At the MHPs2, you can see, especially in the collectives and all, we actually beat all the other MPI libraries. Okay? Now let me talk to a little bit about DP. I don't know how many of you have heard of this. This is the new technology which is coming called data center processing unit. Okay. Now what is happening? Think of like I can explain it very nicely called executives and assistants. I know there are many executives here and you have assistants. And just like in the real world, you try to ask your assistants for help or to offload certain things. Okay, so let's say a meeting needs to be taken place. There is a reservation needs to be done. Instead of you doing it, you tell your assistant or your secretary to take care of this. So that's what you can think of, like the main cores are actually the executives, the host CPUs. And now the DPU, in addition to the RDMA engines, have actually a set of ARM cores. They're not very powerful, but they have intelligence. So the question is, so in this case, we are saying how MPI functions can be offloaded. So we have actually done this. This is a library which is available called MHPs2DPU. You can actually now use and experiment with it. So this is a non-blocking all-to-all. The concept I introduced earlier. That means if the all-to-all in the blocking manner I do, I lose a lot of time. On the other hand, here I can do the non-blocking all-to-all. I initiate all-to-all. But while the all-to-all is taking place, these are the ARM cores will be communicating with each other, coordinating with each other. The processors can continue to perform computation. So then if I put together, so if you see the metric here is not just the communication, but computation plus communication. Okay, so if I use that metric, now you can see the red bar, which is the basic MHPs2. On the other hand, the green, which has the MHPs2DPU functionality where we have offloaded, you can see the benefits. The same hardware, I can give you like a 22%, 21% kind of benefits at the all-to-all. Okay, but the key thing is the application needs to be modified. Okay, if you just give me the old application, I cannot do much. And that's what happens. Like, let's say tomorrow you hire a new assistant or a secretary. If you don't change your work flow, you will not be able to get the benefit. So it is just like what in the real world happens. We are trying to take it to the systems. And this is actually an application, the P3 FFT. Many of you know the FFT is very widely used in a lot of places. So this is like at an application level. So this is the paper we presented last year. You can see this is the left-hand side is like a 512 process run. The right-hand side is a 1000 process run. We are able to boost the performance of the FFT kernels by 18%, 21%. So these are the first cut designs we are working on, even newer designs. So these are like some initial results. I mean, not initial, some sample results I'm presenting. Of course, I mean, this project is going for 22 years. I mean, you will see 300 papers. I'm just taking some of the papers. Here you can see real end impact. So this is like the OCRI Summit paper. They're saying like how MHPs2 is able to really deliver the performance. Idaho National Lab, if some of you are familiar, they use like nuclear energy research. Their entire things, they're using PETC, MOOS. And we had a very nice presentation here. We do an annual MHPs user group conference. And this was actually presented. If you see the right-hand side, they were using all different libraries. But just this year, you see the left-hand side, this MHPs2 is the leading. So all the users have now moved to the MHPs2 because we are able to deliver that kind of a performance. In fact, yesterday night, some of you must have seen this NASA, they had this, the colliding with the meteor. And I'm very happy to indicate all those simulations happened on the Lawrence Livermore National Lab with MHPs2. Okay, our library was actually guiding those kind of things to happen. Very soon you will be seeing a lot of news articles and all will be coming out. Just 24 hours back, this happened. So those are the basic MPI. Now the question is, okay, how do we take that power to all other middleware? So here what I'll focus on is the machine learning and deep learning. If you take a look at the top, many people like a program with TensorFlow, PyTorch, MXNet and all. So we want you to remain at that layer. But the question is, how do you scale out? How do you scale up? And this is where MPI library is good enough. Okay. So instead of like trying to take TensorFlow and redesign with InfiniBand or redesign with Slingshot, a lot of people have been trying to do. The question is, MPI library is already giving you very good performance. So can I bridge that gap? And that is our project here. We call it high performance DL. So some of you must be familiar like with the Horobot or TOS distributed deep speed, that is the middle level firmware. So what we have done is we have linked our MPI library there. either with a CPU-based training, GPU-based training. So at the end users, you don't have to change your paradigm or your application. You still use your TensorFlow. But if you install our library, you get the performance benefit in a very transparent manner. So we have a very detailed user guide. You can take a look at that site, High Performance DL. It gives you step-by-step how do you go and build all these things and to boost your performance. So here I'll show you some sample numbers. This is running on the CPU-based training. In fact, most of the time, people always focus on GPU-based training, but many people have access to CPU, very large CPUs, even a small university, even a small centers, they have a lot of CPU resources, and you can actually use a lot of deep learning using the CPU. So here we used TAC, Texas Advanced Computing Center, like 2,000 CPUs. Look at in ResNet 50 on 2048 nodes, we were able to train it in 7 minutes. Okay, so it is very practical. You can use this kind of a CPU-based systems. This is the data parallel model. Now we have been doing, many of you must be familiar with NVIDIA has their own library called NICO, NVIDIA Collective Communication Library. We are able to beat them, okay? Because entirely all these TensorFlow, everything below, if you see, it goes back to all reduce, all to all gather. And these collectives, we have been optimizing for 30 years, okay? So we are able to, if you see here, this is running on the Livermore-Lassen system. Compared to Nickel, if you use MHPC GDR library, which is the GPU direct library, we can give you boost in 10,000 frames per second higher, again on the same hardware. So this one I talked about this yesterday in the panel. If some of you remember, we have been working with a computational pathologist. So the idea is that how we can really take this kind of deep learning to the end healthcare person. So we are working with several pathologists at Ohio State. So if you look at the blue line, they had a model. So if you see in a hospital these days, you get so many pathology images every day it comes. Instead of a pathologist spending 15 minutes, can we have a deep learning model which will narrow down that? Okay, saying, look, this could be of this disease A, or this could be disease Y. And then the pathologist just comes in and then very quickly just spends 2 minutes. So it was taking 30 hours using one GPU. So they were not very happy. And we scaled it up. This is the hybrid parallelism we used. And we were able to reduce it to 27 minutes, 1.46 hours. Okay. And it was a 15x reduction in the training time compared to the one node, 30 hours. If you see, we improved it by a factor of 60 kind of things. And then similar kind of things, the benefits we get. So this is what in the panel, somebody was asking me where how you can justify the cost. Of course, you are using a lot of GPUs here, but if you can cut down the time the pathologist spends, and they are very expensive, at least in the US. And if you take their collective time, it will be significant reduction in benefits. You will see how high performance computing can really help in the healthcare. Similar things we have done with the machine learning. If most of the people use these k-means, nearest neighbors, truncated SVD, linear regression. So there again, we have linked it with our MPI library. So you should be able to get the speed down. And then the third field is the big data. So big data in my group, we have been working for many years. There is a project called High Performance Big Data. If you go to this site, you will see that. So there, the initial approach we had taken, we have, you can download from the Apache Spark, Hadoop, all those stacks are there. We had actually done native InfiniBand designs, okay? And it was good. 7 years back, we were able to beat all the Apache stacks. But then the question is now, since there are so many different interconnects are coming, it is becoming very troublesome to individually go and then redesign, a slingshot is coming. Then we have to put again another 2 years to optimize for slingshot. Okay. Then the question is, can I do the reverse way? Can I now link to the NPR? So that's what is my theme that we can introduce here. So this is a DASK, which is the data science stack. So here we have introduced together with, we have introduced a module called MPI for DASK. The community is actually working on. So through that, we link our MHPC library. And you can see here, you get a 3.47x speed up, 6.92x speed up. And this is comparing with IP over IB, which is like the TCP IP stack. NVIDIA has a stack called UCX. Some of you might be familiar in the HPC, and we are able to beat all of them if you use the MPI library. And this is the very latest Spark running over MPI. Okay, we just presented this at the Costa conference. So some of you know the MPI library, there's a package called NETI. in the middle. So that's what we have taken, that Native library, we have now linked it to the MPI. So anything running with a Native or on top of that, we'll be able to get the benefits. And see here, like there are some sample numbers here on very different machines, compared to like if you just take like a speed up compared to the vanilla stack, Spark, we can improve by 3.65x. Even with our own RDMA Spark, which we had designed like 5 to 7 years back, we are able to beat now. Okay, because technology has advanced, so you need to continuously re-enhance your designs. But MPI library is already giving us that. So we are getting the benefits through the MPI library. So as we are coming up with these solutions, gradually we are also working with cloud providers, because a lot of people are trying to run the same things in the on-premise system as well on the cloud. So we are working with the 3 major cloud providers, the AWS, Azure, and Oracle. If you take a look at the Azure actually is choosing InfiniBand on their HPC instances. So all our stack, whatever we have developed so far, will just run. Okay, so and that's what happens every time we make a release. They take it and then make an image and make it available to the users. Yeah. On the second one, the AWS is a little bit different. AWS has something called an elastic fabric adapter. They don't use InfiniBand. They are their own customized adapter. So what we have done is we have taken our design and linked to that elastic fabric adapter. So we have a native design there. Okay. So we, in fact, we just made a release just last month. So you can actually download it. Even we also have libfabric support there. With that adapter, you can use that, but it may not give you the best performance. If I go to the real network layer at the lowest level, I get the best performance. So here you can see some sample examples here, WRF. Here it is comparing with our own earlier version, also with OpenMPI. We are able to, as you can see, as you are getting the scale out, this is where our MPI library shines. If you just do it in 1 node, 2 node, you may not see much difference. But if you start running larger scale data size and larger number of nodes, you will see benefits. And similar things we have done with the Oracle also. Oracle has gone the other way, called Rocky. If some of you know RDMA-enabled converged enhanced Ethernet, they call it Rocky. So, and our stacks again runs on Rocky. So this is some number here. You can see like a, this is the mini AMR. And as you can see, like compared to HPCX, also Intel MPI, we are able to beat in a significant manner. So like this, we are able to really deliver the solutions, not just for the on-premise system, but also in the cloud, you can actually use it. But then I hinted at this in the beginning, since a lot of people are using our software stack, since it comes from university, many people say, yeah, it is university, but what happens if the software stack fails? Who will fix? Who will do the bug fixes? So we started a commercial spin-off. It is called Xscale Solutions. And in fact, through that, we are supporting many large laboratories like Lawrence Livermore National Lab. If some of you know, we totally support their all MPI needs. Okay? Similarly, KIST is South Korea. So we have like all over the world, many HPC centers, we are providing commercial support. So just like think of any other Intel MPI or any other MPI, you can actually get the commercial support. And we take care of these using professionals. And then gradually what is happening, a lot of these end users are also asking for some additional features. I call them value-added features. So like this, so we have different packages like Xscale HPC, Xscale AI. I showed those DPU results. Again, so that is like we are trying to handle also the commercial customers. So I just want to say, so it is not just for like any only open universities. Your work, you can, depending on which spectrum you are at the end users, we should be able to help you. But with that, let me go to my last segment. So this is the new AI Institute, which is trying to take it to the next level. Okay, so if we take a look at like a 2030, how the cyber infrastructure needs to be designed, how the middleware needs to be designed, 2030, 2035, 2040, next 10 to 15 years. And this is where that computing continuum comes in, the stage 4. So we got this funding from National Science Foundation in the US. It's called iCycle. It stands for Intelligent Cyber Infrastructure with Computational Learning in the Environment. I'm the overall PI, but I'll introduce, there are 14 other universities, 50 faculty, 60 students. So it's a very large team on working on this. But before I go there, let me play a very short video here. Let's listen to that.
A policymaker must know how land use policies will affect their region's biodiversity. A farmer is concerned about how new weather patterns will affect crop yield, while food distributors and public health officials are concerned with how supply chain disruptions will affect deliveries of nutritious foods to communities. Current technology can provide data and models to tackle grand challenges such as biodiversity, conservation, and agricultural and food system resilience. But it still lacks the infrastructure to link across data and models seamlessly to answer complex questions from diverse stakeholders' perspectives. Even AI experts are challenged to create standardized solutions across domains because a standardized cyber infrastructure integration with AI just doesn't exist. Enter Icicle, intelligent cyber infrastructure with computational learning in the environment. Icicle is an institute dedicated to building a national AI-driven computational infrastructure that functions as a utility, much like our electricity, water, and transportation infrastructure. This new utility will enable the delivery of AI to end users with a flick of a switch, enlightening solutions for imminent problems of national, regional, and local importance. Icicle will provide an operational rationale and framework for a cyber infrastructure that delivers wide and easy access to smart computing, plus a conversational interface that allows stakeholders from diverse domains to ask questions and receive answers informed by currently available data and knowledge. For example, food distributors, emergency food agency managers, and logistics company executives might ask, which food supply chains will likely be affected by an approaching storm? The Icicle conversation agent might respond with, I will predict future states of your regional supply chain under forecasted weather scenarios and evaluate alternative scenarios. Okay. Upon confirmation, Icicle would then retrieve satellite data on weather, connect to weather forecast models, acquire inventory data for food producers, processors, distributors, transportation networks, wholesalers, and retailers throughout the region. Use AI models to forecast supply chain conditions from a baseline and alternative logistics that maintain consistent food supply for vulnerable populations, and estimate supply chain disruptions based on historical and current data from other locations. Mindful privacy. Icicle will go even further by accessing high-performance computing centers to backcast and learn how reconfigured landscape-scale precision agricultural production and distribution systems could integrate with alternative supply chain infrastructure to avoid similar future disruptions. Using an orchestra of smart cyber infrastructure elements, Icicle produces a symbolic answer that improves outcomes for diverse stakeholders. Icicle holds the potential to transform today's AI landscape from a series of fragmented tools for use by a few to one where democratized AI and integrated plug-and-play architecture empower diverse end users with knowledge and data flows that are science-based, traceable, transparent, reusable, and trustworthy. Introducing AI for CI for AI. AI for everyone.
So that is the kind of the idea what we have. Really looking forward, as I said, like a 2030, 2035, 2040, how do you design this next generation cyber infrastructure? If you think of like these days, think of like your WhatsApp or Telegram, it gives you a very simple interface. I can post a message. What happens behind the scenes, somebody else is taking care. That is the kind of vision we want to bring to the AI. Like the example I gave to the farmer. The farmer can just talk to the iPhone, say, should I harvest it today? Everything else happens behind the scene. And then the main interface is the conversational AI, and through that you get the solution. That is our vision. Okay. So this is where we want to really democratize AI so that the end users really take advantage of AI. But of course, we have to work on the actual research, and we are trying to solve societal problems. But the main focus is also a new generation of talents. We want to train them, because not many people are now familiar with all the latest things, what is happening. So I talked about this computing continuum here. I explained a little bit about the digital agriculture, but we also have two other verticals in our project called the animal ecology. like how the animals move, wildlife conservation, so all those topics are there. There is also smart food set. You heard a little bit about that in the video. And in fact, as I'm talking, many of you might be following, there is a hurricane is developing in the US. It crossed Cuba. It is heading to the Florida. This is exactly this time you need softwares like this, which will exactly tell how to move the logistics, how to move the food, supply chain, all those things get disrupted and you want to recover very quickly. And those are our actually the broad goals. And it's a very large team. There are 14 organizations. Very quickly, if you are familiar with the US map, RPI, Delaware, OSU is the lead. Case Western, Indiana, Wisconsin, Madison, Iowa State, PAC, University of Utah, San Diego, SDSC, UC Davis, IC4, that is a nonprofit, and all these other collaborators. So we are working almost like a 110 members team to come up with a solution. We started this project officially last November. So we are just 10 months into the project. And I'll not have much time to go into really all the details. We have a lot of solutions out there. If you are interested, just follow icicle.ar. That is a website and you can get a lot of information. But at the very highest thing, this is our overall vision. I talked about this heterogeneity. If you take a look at, we are having heterogeneity in compute, context, data, model, interface. Everywhere there is heterogeneity. And if we really want to come up with a plug and play architecture and trying to have democratized AI, this is where the right-hand sides are the solution. We want to have abstractions. We want to have standardized API at all the layers. Intelligent CI, adaptive AI, federated learning, knowledge graph, model commons, conversational AI. So not only we want to work individually, but also across the stack, we want to standardize. So our vision is like this. So we actually co-design. So in fact, in our team, not just the computer scientists, we have the faculty from food and agriculture, faculty from animal ecology. So we are working together with them and with their students. And the idea is that these are the end co-designs. They will go through the conversational AI interface. And as you can see that logo of different size, that is our software. So you can think of like it is a distributed computing software. A smaller version will be running on the edge, on the sensor. Might be a little bit heavier version is running on the near edge. A little bit heavier is running on the cloud, but they are all interacting together, dynamically detecting the heterogeneity, what you can do at what place and up to what extent. So inside that on the right-hand side, those are our like the foundational, like we have a lot of focus on foundational systems AI. We have CI for AI. And this is the new field. I think, some people talked yesterday about AI for CI. That is also a lot of focus. Like some of you gave examples of schedulers. You are learning from these. On the execution, should I use so many cores or should I use so many cores? So we are also trying to do very similar things. As the things are running, we want to learn from that. That's like a learning from the environment. That is our title. It is not only computer science, but any environment we'll be able to learn. And then we have a lot of focus on also visual analytics, explainability. There are big issues about privacy, accountability, data integrity. So we have specialized teams working in all these things, and we want to bring together that software stack. So in this context, we are completely like open. We want collaboration from all different researchers, faculty, students, industry. So if any of you are interested, we'll be very happy to work. So with this, let me conclude here. As I started saying, we have already crossed like the exascale mark, but we are talking about zetascale, but next 10 years, you will see a lot of machines will be coming up with exascale performance. So we want to design the middleware. It needs to be designed in a holistic manner. You cannot just design only HPC or big data. You need to take that computing continuum, the heterogeneity, and also try to handle the big data, data science, deep learning. And that's what I presented, saying how we are approaching from our group. And I also provided an overview of NSF AI Institute. In a seamless manner, I want to advertise this also. All our thing, what we have done in our big data area. We just had a book published from MIT Press, High Performance Big Data Computing. So just last month, it has like it's a 250 pages, which talks about everything is happening in the big data field and HPC, how to combine together. So if you are interested, please take a look. But I'd like to thank all these sponsors. I mean, these projects have been running for 20 years. Without their help and funding, we would not be able to do this. But more importantly, these are all my heroes. What I just presented in 30 minutes is like a work of 22 years. But all the staff, students have continuously come. I'm very fortunate to have all these brilliant people joining my team. And I continuously look for new students. I have students from all over the world. If any one of you here would like to come and work with us, please feel free to send me a note. So with this, I'd like to conclude here. And I'll be here again throughout the day. If any one of you would like to have more discussion, I'll be very happy. Thank you.
Thanks a lot, Mr. Mike, for the outstanding presentation.
Thanks.
So now we would like to also welcome Mr. Munir Shahri and his colleague who believe the way is available. Basically, what Mr. Munir is a cloud architect from Saudi Arabia, and his talk will be basically about a cloud native HPC use case. So that's what we do.
Why are you so quiet? It's a community. Try to be active, live. It was there now, just now. Oh, let's not put it. You put it. No, you didn't add it. In this one. Some technical difficulties. No, not this one. Oh, okay, this one. It's okay. The one. We drop the slide.
Hi, cloud native.
Yeah. It's okay. So while we have this technical difficulty, I want to comment on Dr. Band's presentation. I want to comment on Dr. Band's presentation. So basically on the information that is seen, but very mindful when we speak about. Remember,
and now it's a bit.
But basically, and think about satellite and drone and delivery truck. So this is computing at edge. Kubernetes, I will say Kubernetes many times. I have promised that I will say that at least 10 times. Kubernetes basically can run in the edge. You're ready? Oh, sorry, we'll finish later. Okay. Thank you.
Assalamu alaikum jami'an. Good morning, ladies, and good morning, gents. Looking in today's life, HPC is everywhere around us. It's ubiquitous. Whether you know it or not, you're surrounded by HPC-related projects. Everything, almost all products around you are results of a solution that was resolved by HPC for a specific problem. It's in our everyday life, from finance to economics, to medicine, image processing, designing coffee machines, and even simulating images, and even formulating shampoos and perfumes. The demand for these computing resources continues to rise, and having it as a dynamic environment, that is having HPC on cloud, positions enterprises to be more competitive, driving greater return of investment. Today, we'll talk about cloud native HPC, My name is Noura Ludaa, an HPC specialist from Saudi Aramco, and my colleague Walid Shah. In this presentation, we will define Cloud Native, the CNCF Foundation. We will also talk about the evolution of Cloud Native and Distributed Cloud. We'll have a look over HPC adoption, the challenges and the advantages, and finally we'll conclude with some public cloud use cases with the cloud. So to put the recent rise of demand into perspective, in 2018, Hyperion Research stated that adoption of public cloud in HPC sites increased 5 times, moving from 13% to 74%. And this year, many companies started running Kubernetes, that is a containerization cloud native solution in their companies. So what is cloud native? Cloud native is a new paradigm or a modern way to run, develop, and deploy applications. It uses mostly open source software stacks. It exploits the advantages of cloud computing models, which means you will focus on how you deploy and create containers and applications rather than where. So the cloud native application design revolves around 3 main concepts: the microservices. Those are basically breaking your application into multiple smaller services that run independently from each other. But there was a main issue, that is how to manage these microservices, and especially when it comes to cross environments. That's why we have containers. Containers, they're basically a bundling of applications along with their dependencies as a package to be deployed regardless of the environment. Containers made it easier to run on a single host, basically. But dealing with one or few containers, it's pretty simple. And as the number of containers grow, you'll need a container orchestrator. What that does, basically, it builds, run, and manage the application. This will basically automate much of the operational effort that is usually done by the software teams. And one of the widely known orchestration solutions is Kubernetes, which was created by the Cloud Native Computing Foundation, which takes us to our next topic. So the Cloud Native Computing Foundation stands for CNCF, known for short as CNCF. In 2015, Google partnered with the Linux Foundation to create CNCF, with the goal of encouraging the development and the collaboration of different cloud solutions to advance container technology. Now, CNCF has a landscape map that shows the full extent of cloud native solutions. The ecosystem, as you can see here, grew exponentially, and it is still growing. Now, this covers the runtime, provisioning, orchestration and management, monitoring and logging, and so on. And you can see many projects started to appear for HPC, but they're scattered all over the place. That said, we hope that HPC-related projects will get attention having its own cloud. It's similar to this one. Now, where does HPC stand when it comes to cloud, and how mature is it? This is an evolution timeline of the cloud and the distributed cloud-related projects. HPC in the cloud, it's not the future, actually. It's already happened, and it's still evolving. There was multiple attempts more than 10 years back. That is a decade. Some are publicly and some are private. One of them is the cycle computing, which was conducted in 2011. In 2015, CNCF launched Kubernetes. 2017, University of Michigan worked with Red Hat and a lot of projects. One of them is Kubernetes. This is basically one of the attempts to run a traditional HPC job scheduler on a Kubernetes cluster, which was a failed attempt. But there was multiple success ones. Those basically created job schedulers all the way to be cloud computed, all the way to be a cloud native from the scratch, such as Volcano, that was launched in 2019, and Q, which was launched this year, actually. Lastly is Karmada. Rdma is one of the CNCF's first multi-cloud container orchestrator. It basically allowed the orchestration functionalities to run cross clouds, cross clusters, and cross planes. Now, cloud and HPC projects were mostly distinct in the past years, and with the recent technology advances, they became almost fully integrated, as you can see. And the future is basically not cloud and HPC as we see it. It's actually smart HPC. Now we can see a visible trend here, the importance of orchestration in HPC jobs and workflow scheduling, especially that schedulers doesn't understand HPC workload. For example, the fair share concept. And of course, hardware, in which HPC cares about, if the cluster is equipped with GPUs, what type of interconnects it has, and so on. Kubernetes has the basic functionality being fully abstracted from the hardware. There are many challenges, as is, which we will talk about now with my colleague, Walid Shah.
So before I go to the second slide, if you look at the slide on 2020, you see Mindscore. So Mindscore is an edge software, and this edge software you can put it in a satellite. It's actually running right now on a satellite. Okay, and you can put it on a truck, you can put it on anywhere, and it runs on Kubernetes. It's created by Huawei. Any Huawei? No? Any Chinese? Yep. So this is one of your products. Thank you. How do I go next?
Yeah, that's okay.
Oh, okay. There is something wrong. This is not the second slide. Okay. This is supposed to be the second. Okay, there's something wrong in the slides. Thank you, Nora, for missing my slide. No. Nora, by the way, she graduated from here and she's one of the stars on Saudi Aramco. She started as a platform engineer and she's now HPC. So she cross-pollinate between the two disciplines. Cloud adoption challenges for HPC is the same. It's the same as cloud adoption. What is holding us from cloud adoption? The first thing is basically, so this slide is messed up, but the first thing, for example, here in Saudi is data residency, data governance. I work in an enterprise that will not allow data to be outside of our department, not outside of our organization. Okay, how can you basically process this data on the cloud? There are solutions. For example, Google have confidential computing. You can encrypt the data. There's lots of things, and having a region here helps a lot. So data in platform engineering, in cloud native, the most important thing is the application, and the application requires data, and data has gravity. The more data it builds, the more you need the services to be as close to the data as possible. Okay. Second one is that the paradigm shift. Change is constant. The only thing that is constant is change. You hear this all over the place. And people resist changes. And you are changing them from running batch script, running jobs for SLAM, for LSF, for SGE, UGE, Univa, Altair, because I know Altair is here. So, Altair? Yes, so Altair is a good PBS Pro, UGE. So, now you're gonna run it as a service, not as an MBI job. You still run it as an MBI job, as Dr. Bender showed you, Dask and All4, which parallelizes the MBI, actually you can run them on top of Kubernetes, on top of cloud native workload. So basically the talents are not there, as he finished his slide saying that we need talents that know new skills and stuff like this. This is one challenge, and that's why we depend on you students and researchers to grow this kind of talents and basically encourage them to adopt new technologies. The third thing, which is the slide that dropped, is the special hardware. Again, we saw that the Banda talking about the data center, what was it? The BDU, the data center unit, correct? So the PDU, the accelerator, the GPU, the tensors, the TensorFlows, the TPUs from Google, the InfiniBand, the special network, EFA, you saw EFA from AWS, from Amazon, the Elastic Fabric Adapter, which basically can perform different than InfiniBand. How in HPC, you need to know about this. You need to know that the existence of this hardware on the worker node. You need to know the CPU, what kind of CPU. Now that we have ARM everywhere, at least in the public cloud, in the 3 public clouds. So AWS produces its own ARM, Graviton, and now they are in Graviton 3. Google just released this year that they have ARM, and Microsoft also have ARM. And it has proven that ARM is like 30% cost effective and 30% less sustainable, better sustainability. And so how can you tell about this? Because basically Cloud Native try to democratize the workload, try to democratize the platform. So the portability is very important. How can I run it on a satellite, and how can I run it on a delivery truck without knowing the platform that I'm running on? In HPC, that doesn't work. I need to know the platform. I need to know the architecture. I need to know the topology. I need to know if there's a NUMA. I need to know if there's the InfiniBand. So there are solutions, and the solution is node feature discovery. So basically, there's work on that. So these are the challenges. The challenges for HPC is very specific, but the challenges for adopting the cloud is very general. Now, if I go back to the messed up slide, I just want to show you that sometimes that what we conceive as a challenge is not really a challenge. This is from the last top 500, June 22. You can see that Microsoft had 2 entries in the top. Actually, Microsoft last year was top 10, was in the top 10. When I say Microsoft, I mean Microsoft Azure Cloud. They had a cluster on the cloud, which was one of the top 10. We are top 45, correct? Around, I think we have one on the top 45. 3? Okay, sorry. And Google and Amazon also had 3. They had 3 on the top, they had it on top 50 in 21, and now they dropped to 52. But if you look at the Microsoft, they had NVIDIA, which is a special card. They had Mellanox. So basically, these things exist in the cloud. Now, how do you discover it? In Kubernetes, will give the node feature discovery. So it's not really a big issue. So what I'm saying, what you think is a challenge, most likely is not a challenge. Okay? Something, sorry. Okay, I shouldn't use the slide. What's the advantage of using cloud native and cloud native technology? I have been looking, and our team, the high performance computing team, have been looking at CERN for a long time. CERN are well known HPC data center, or more as an HPC data center. Dr. David Keys is here, and I have to be precise about what consists of HPC. So HPC, the traditional one, is deeply and computational. HPC, high throughput computing, which is most of what the cloud really products are, which are not really dependent on each other. And that's the 3 slides that you remember from Dr. Bandhan. So basically, in 2008, they started their virtualization journey. Every HPC data center will shy away from virtualization because they use NFS, they use technologies that the moment you use virtualization, you will get like 15% to 20% overhead, so you lose 20%. But they said that's reasonable. We will gain management. We will gain that they are like a public domain, and they need to change their infrastructure. In the morning, for example, they will be processing a huge data. In the afternoon, they will be doing HPC, and maybe later they will be doing something else. So they need to change the same infrastructure as quickly as possible. They have adopted the Kubernetes Cloud Native in 2017, and the researchers, which are around 5,000 on-site and 10,000 globally, have asked their infrastructure team, give us a proof of concept. They gave them a proof of concept. How many nodes do you think? 1,000 nodes. This is unheard of because they always work at a scale. They don't work small, we are always big. And their motto is, if I solve it once, I solve it for everybody else. And that's what our motto should be. So basically, it's not really medical, it's particle physics. But we did change the name, by the way. We didn't change the theme, but we did change the name of the title. Another public cloud use case for containers from AWS, something called AWS Batch. Now, why I'm talking about batch and why I'm saying batch? Batch is a workload that is interactive. It could be machine learning, it could be HPC, it could be data. So basically the same as what Dr. Banda says about computing continuum. So batch is why we are here. And there is something in the CNCF just created recently in last February. It's called the Batch Working Group. Now, this is the commercial one. This is basically an AWS managed service, fully managed service. So when it's fully managed service, you just think about your ID, you just think about your job, you forget the infrastructure, you forget the monitoring, you forget the logging. This is all provided by default. So it will dynamically provision resources for you. You give it a job, you say this job, for example, requires that number of resources, or under that number of amount of dollars of Saudi riyal, like I needed this job to run under 1,000 Saudi riyal. It will pick up the right time, will pick up the right resources, and run it for you. It can run it on virtual machine, it can run it on containers, and it can be completely serverless. It will plan, schedule, execute. It's free to use, but the resources that you are using are not free. And the data you are entering is free, but the data that you get out is not free. Okay? Now, the other thing, the beauty about AWS Batch, it's running on ECS, Elastic Container Services. This is the second popular orchestrator after Kubernetes, but it's in public cloud on AWS. More 60% of the containers run worldwide runs on AWS. That's some statistics from 2020. In December, they will produce another statistic on their conference, reInvent. I couldn't get them on time. This is Ricardo Roca from the CNCF TOC, the Technical Oversteering Committee. He's very active. He's a CERN engineer. He's been 7 years working with CERN, and he's very active in the CNCF community and in the scientific community. We are operations. We use automation, infrastructure as code. We use Puppet, and basically CERN uses Puppet, so he's a Puppet engineer. What's special about Ricardo? Ricardo is the organizer for the next KubeCon event, and he's also part of what we call research group. So, and what they found in CERN, he always talks about CERN and their profile and stuff like this, and we have a blog that you can check with the QR code. So this blog will have these URLs for you that basically can go deep. He says in CERN, they don't develop in-house anymore. If they want to do something, they look basically at the CNCF or open source, the landscape, and they check something close, and they contribute to it or the enhancement. So what is next? In 10 minutes, we cannot really tell you much, but we have this QR code which it has links, and it has a video for Ricardo describing the bridging between cloud native and HPC. If you've done it last KubeCon in May in Valencia. There is a workshop in October, the HPC Batch Day. Last time it was very successful. It was half day, attended by around 200 people real time, but you can see the counts on YouTube. It's actually very nice to tell you about the landscape of batch on cloud native. And the supercomputing conference, SC22, there will be another workshop specific for containers and HPC. How can you contribute? There are students, there are researchers, there is everybody here that can contribute. You can contribute as minimum as possible, just feedback, just by attending one of the calls. The calls are bi-weekly calls over Zoom. So the CNCF Technical Advisory Group, under it is the batch work group. They meet bi-weekly. You can join Slack, you can join the mailing list, you can join the call, you can introduce yourself, you tell what problem you have, is it solved, is it not solved, you can give back about any project, and that's the first thing you can do, the least thing you can do. And here, you can basically, if you want a thesis or you want a project, you can contribute to any of the projects that they are overseeing. Okay, and let's see. Okay, that's the end of the slide. So basically, the key takeaway, CNCF, the Cloud Native Foundation, tries to promote open source, and there is a conversion happening between the traditional MPI HPC workloads and the new smart HPC, which has AI, which has big data. And they wanted to consolidate the infrastructure. They wanted to automate the infrastructure. The only way to automate the infrastructure better with less resources, with less talent, is using infrastructure as code, which we've done. Now, what's the next stage? Is automated using the platform, which is Kubernetes, which is cloud native, because you focus on your core area. You focus on the application, and you forget about monitoring, you forget about logging, security. This will be taken care of by us, by the way. Thank you, Noah. Thank you, everyone. And thank you, Dr. David, Dr. Banda.
Thanks a lot, Mr. Relegated, for the outstanding presentation. And now we have the final discussion for the first part of the presentation. We have Professor Rashid Mahmoud. Professor Rashid Mahmoud is the research professor of Big Data Systems and the director of research training and consultancy at the High Performance Computing Center in Abdulaziz University. He has gained qualifications and work experience from universities in the UK, including Cambridge and Oxford universities. He has 25 years of experience in computational modeling, simulations, and design using computational intelligence, big data, high performance computing, and distributed systems. His board research aimed at the development of multidisciplinary science and technology to enable a better quality of life and smart economy while they focus on real-time intelligence and dynamic automatics. He has published over 200 research publications, papers, including 6 edited books. He has organized and shared international conferences and workshops. So without further ado, we want to present Professor Rashid. And so as a reminder, please use the QR code if you have any questions for the panelists. And try, present Professor Rashid the floor to the
Control L. Okay, see where is page down. Okay, yeah, that's okay. Okay, thank you. I have to hold it, is it? What is that? Okay, I just use my hand. Okay, assalamu alaikum everyone. So my talk on smartization of societies, ingredients and examples, and I will focus on healthcare. Sorry, I need to get used to this thing now again. Just click. This will not work. Okay, do I need this thing? Okay. Okay, that's fine. Okay, so before I start my talk, so this is the context of my talk. So first thing, that I'm looking at distributed systems model of HPC. So, you know, we heard some stories here, and David is very particular about HPC, I don't know. I just heard it. So, so I will be looking at distributed system model of HPC. The second, okay, so I can show you here what I mean. So basically, this is a typical smart city or society, and we have different applications at the bottom. You can see healthcare, ports, agriculture, energy, whatever. And basically, we have clouds on the top, and I mean, cloud can mean mainframes as well. That if you want to do something, then they will not be at the edge. They will not be close to the applications. Typically, they will be away from the applications. And because these applications are generating data in real time, so moving that data in real time to the mainframes and bringing it back after making decision is not possible. So because of that, we have fog and edge layer. And so basically, fog layer can reduce the latency. So if you look at the left side, at the edge, on the bottom, you have the least latency. And if you go to the cloud, you have the highest latency in orange at the top. And on the right side, you will see that we have the lowest amount of computation and storage at the bottom, at the edge, and we have highest on the top. So we need to balance these two things. So in order to solve these problems, so we can look at a distributed system model of HPC where we are able to bring HPC to the edge. So that's the purpose of, well-known purpose of fog and edge computing. So there are some technologies I mentioned at the bottom and on the right, which are changing the way distributed systems are being designed, and the 6th generation networks are coming, which rely on softwareization and AI-based optimization and so on. And not only that, but they deliver AI as a service as well. So that is the aim of 6G networks. So looking at that model, and on the left side, you can see that latency aiming to be less than 1 millisecond. Mobility should be 1,000 kilometers per hour. Data rate should be 1 terabyte bits per second, and so on. There are other things there as well. So this is the model of the society which we are looking at in the future. And in order to support this society, we need a distributed systems based model of HPC. So the second thing is the second thing in context is that we are looking at triple bottom line. So we are looking at design of these applications, which are based, the foundations are social, environmental, and economic sustainability. So this term triple bottom line is well known in business. So whatever you design, it should meet the social, environmental, and economic sustainability aims. So having said that, so this is my base of context of my talk. So what is the aim of my talk? So I will be looking at some technologies that how they are driving innovation with concepts such as smart cities and societies and smartization. And I will limit the applications which I will mention to healthcare. Okay, so what is smartization? So we can say basically designing applications, keeping these three aims in mind, which is the social, economic, and environmental sustainability. So why it is needed? For example, we can see that recently there have been many unrest around the world. There have been economic depression coming now, and it's not completely there, but it has been predicted that it is going to get worse. Many things are changing with, for example, oil industry, carbon footprint, and so on. And, we have many pandemics and disasters. So all these things are calling for triple bottom line. And there are new criteria coming like ESG, which is environmental, social, and governance criteria, the UN SDGs, and so on. So that's why it has become very important. Okay, so I will cover some healthcare research with this context. And what we are doing at HPCC, which is the HPC Center at King Abdulaziz University. And I will give some examples. These are Arabic names, Imtizaz, Iktishaf, except Diesel. So the Arabic speaking people will understand, and I will just say something about them. Okay, so this is the first example where we try to bring high performance computing, the typical mainframe cloud computing, with edge and fog computing. So this setup basically on the left side, you see cloud or mainframe, and on the right side, you see different kind of computational units. So a laptop can be used, Raspberry Pi, Jetson Nano, and mobile phones can be used to deliver these services. So we call it imtidad. So these are different things which I mentioned already, just I put it on another one so you can see what they are. So this is the reference architecture we developed. So we want to develop services, healthcare services. So what you need to do, you do an application selection. So you want to know what application you are looking for, you get the data set, which is needed for that particular application. You design the model, the AI model, and then you develop the service use cases. Then you design the services, you design a service catalog, and then you select execution platforms and select what networks you will be supporting. Then you operationalize the services. So this is the whole workflow. On the left side, on the bottom, you can see what user will do. User will select a service, request a service, and receive the results. And then validation can be done by user or by domain experts or by third parties. Okay, so these are some example of the, so this is basically a skin cancer, skin disease identification, and there are some classes of diseases on the right-hand side. So we designed 22 services that provide skin disease diagnosis. We have 4 service classes, gRPC, containerized, gRPC, Android-based, and Android nearby-based. So this is based on the software platforms. On the basis of hardware platforms, we have Google Cloud, we have HP Pavilion laptop. So we deliberately selected these kind of architectures, hardware, which are easily available and which are cheap. So NVIDIA, Jetson Nano, Raspberry Pi, and then the typical mobiles people have. Networks, we had fiber and cellular, we had 2 selections, plus Wi-Fi and Bluetooth. And in terms of deep learning diagnosis model, we used Inception model and CNN model, and we used their tiny AI versions through TensorFlow Lite, because in order to run on the smaller devices, you need those models. So here's the detail of this one, and I will skip this one. I explained already the same thing earlier. So this is the catalog, and we have on the left side, this is the number 1 to 22, service name, what we called it based on Cloud Fog or whatever that was. So you can see Cloud AB. So AB refers to the model A and B, and Fog AB, A Lite, B Lite means that this model runs on use A model or B model, which I mentioned to you, Inception and CNN, and I will give you the details. And then the A Lite model and the B Lite model using TensorFlow Lite, so that it can run on lighter devices. And then you have, we call them based on the architecture. For example, Raspberry Pi 8 A Lite is the model which runs on Raspberry Pi 8. 8 is the number, and A Lite means, as I said. Okay. So on the right, then next one, service type. So what different service types are there? I mentioned 4 types. So they run on different places. So the top one, containerized, that runs in cloud. And then it can run on Fog as well. And then gRPC, it uses Google RPC service to connect to the resources, and then local mobile service and Android nearby service. So then I mentioned some what platforms we are using, what specifications of the hardware, then what energy the platform uses, because we looked at the energy as well, and the network specification, whether we can configure the latency or not, and then the model name. Okay, so these are the 5 kind of services, and gives a little bit detail. So diagnosis, request service, how it is built, the diagram giving the main components. There's mobile local service. So mobile local service can talk to diagnosis request service, and it can talk to gRPC service or containerized gRPC service, depending on what kind of service it is looking for, where it is running. and then it can ask for DL model service, so it can send the data and get the results back. So these are the details of the data set which we use, and these are the models, as I mentioned already. So I will not talk about them. So this is the user interface. So you can see, for example, the user can select different service types. It can select different platform and so on. And of course, this can be done automatically using some user preferences. Okay, so here are the results. I will quickly mention them because my focus more is on introducing some services. I have total some application. I have total 10 minutes. So so processing time. So it shows that Jetson uses very high processing time. This is because of the model size. Because when the model is small, it is able to run very fast. And on the right side, there's a box plot, so it shows that what is the variation. And because we deliberately use home environment and typical network to understand whether this kind of services can be delivered by anyone. So for example, can we ourselves get these service, or a doctor, can the doctor be sent a photo of skin disease or any other application and return the results? So how long it will take? So I will skip this because of the time, but just mentioning. So we looked at response time and the variation, and we use typical home environment to understand that, the network time, and we developed some service values to allow users to understand what kind of service value they are looking for, so that we can develop preferences, and based on preferences we can automatically suggest users a particular service. So here we looked at the energy and other things as well. Okay, so second one, we looked at, so this is NLP based service. So we looked at one of our students, Kisama Lomari, she has passed her PhD now. So we looked at Twitter data to understand what government measures were introduced by Saudi Arabia. So what you see here is the timeline on the bottom. It is 2020, and from 14th March to something June. So automatically we are able to detect that COVID-19 has started, and that stay home measure has been introduced by the government. And then some prevention measures were introduced. Loans were given to people and companies. Hospital treatment problems started because people were not able to get into hospitals. Then government introduced quarantine. Mobility was reduced. Curfew was introduced, salaries were paid by the government, and so on. So we were able to detect all these events automatically. This is the temporal progression of these events, different events or measures. And this is a spatiotemporal, so the size of the circle shows that how much intensity is there for that particular measure, and the color shows different regions on the left side. So how do we do that? So this is a typical machine learning pipeline. So we collect data, we pre-process that, and then we detect the measures and concerns, and then we extract spatiotemporal information, and we validate and visualize. Some data about what we did in reducing the time. So this shows that if you want to run one instance of this LDA application, then it takes us 163 hours, which is roughly 6 days. So typically we needed 30 to 40 runs. So if we do that, then it is like 6 to 8 months it will take. But we were able to run it on multiple cores and reduce the time initially to understand what different iterations we use and what is the best number of iteration to get the best results. And then doing all that, we were able to reduce the time to around 2 hours for one run of the application, and the total development time one month roughly. Cancer, so this is another work where we detect cancer services through Twitter data. So what we see is that we are able to look at information availability services. We are able to look at socioeconomic sustainability services. So these are like macro services, and smaller services, normal services are under that. So we are able to detect some psychological support services, treatment services, and prevention services. These all works are published, and you will be able to find them with the names which I mentioned, and you can get in touch with me, and I will be able to give you the links. Data-driven participatory education governance. So this is what we looked at during COVID, that how Ministry of Education or government can govern education in this kind of uncertain times. So this shows, for example, on the left, we have actors, people, government, industry. On the top, we have data sources. So you have social media, government data, scientific literature, institutional data, and other data. Objectives are on the right. So you have quality, you have productivity, transparency, responsiveness, and all that stuff. And on the bottom, we have the foundation that we want to maintain the social, environmental, and economic sustainability. So what happens is that we get the data, use machine learning based analytics, we extract education governance parameters, we evaluate them, we validate them, we improve them. And then on the right side, we put it into a self-improving loop where these governance are going to the real life, and then these are being tested, and then we get the feedback through the data and other things, and we come back and we continue to put it in self-improving loop. We improve and we put it back to the implementation. So how do we do that? This is typically same pipeline, but there are some differences. So here is what we detected from these governance parameters. So we have success factors, so government can understand what success factors are there so they can focus and improve them. There are challenges on the left, so they can understand what challenges are there. They can work on them and improve those and develop better governance parameters. On the bottom, we look at socioeconomic sustainability. And on the left side, accountability and transparency of all this process so that people have trust and confidence in the government. So we do some other applications because I have already finished 17 minutes. So I will just skip them. So this is parallel DNA profiling, which is used to in criminal investigation cases, for example, to find the DNA of the person, and so paternity tests and other applications. So one of the problem in this is to find the number of unknowns in the DNA sample. So we looked at this problem as well, and we used machine and deep learning, and here are some results. We also used maximum likelihood estimator to do the same problem and parallelize it on Aziz supercomputer. So it took 5.8 days without that, and we were able to reduce it to less than 3 hours. Some other applications, detecting some diseases from Twitter data. So this shows that what is the proportion of diseases. So you see diabetes is 30% in Saudi Arabia, dermal diseases on the top 20.7%, hypertension 27%, and heart disease. And this is the distribution over different cities, and awareness activities and afflicted cases. So we also work on network level to improve performance of these healthcare applications. So this is work UB Health. And then we work on sparse computation. We did some work on auto-selective kernels, so it automatically select a kernel based on the matrices. The work is called Diesel, and because I don't have time, I can't talk about this. And also another work, Sura, which develops multiple parallel kernels to run on GPUs based on the matrix properties. And again, I can't talk about this. Conclusion. So I will say that that social, economic, and environmental sustainability is becoming very important. And HPC is everywhere, data is everywhere. And because the data is generated on the edge, so therefore efforts are needed to bridge this gap. And we are working on all this space to develop better algorithms and applications and solutions. So some of the people who contributed this work, and thank you very much.
Thanks a lot, Professor Rashid, for the awesome presentation. Now I would like to go over the first part to be have a large session on various topics and questions that will present this part. So I'm going to join us here on stage. Thanks. So again, I will be presenting a number of questions that were actually provided by the audience, and we actually have a nice question that are actually. So we'll give one for actually basically talking to Professor David. This question is for you. What is the memory optimization that benefit from the mixed precision, like two times or 3 times?
The amount of compressibility of the data in one of these large dense matrices is very application specific. In the example I showed of the statistics computation, if the data are highly correlated, there won't be very much compression available, and there won't be very many low magnitude blocks that can be reduced to lower precision. But in many cases, you can see factors of 10 or more in the amount of memory that can be saved. The key really is not speeding up the flops. The key is living higher on the memory hierarchy. In today's deep memory systems with maybe 3 levels of cache, registers above that, DRAM below that, and DRAM, high bin on the chip, all the way down to disk. You have literally orders of magnitude of access speeds. DRAM can be 1,000 times slower than a register when you're clocking at gigahertz. If you lose 1,000 times, 0.1% efficiency in computation. So the smaller memory footprint you can use for a given working set, much faster the computation go, independent of how many flops there are. Whether you get a reduction in flops, it's almost less important than reducing that size. And again, it's application dependent. Random matrices don't compress at all, to any realistic sense. By the way, that same technology that we've been using algebraically is actually being used now for data compression. So we're not just talking about a linear operator like the matrix, but actual field data, temperatures, pressures, combustion species, and a combustion reaction. Apply those algebraic methods to it block by block, and you can actually get significant compression for your disk I/O, and that's another bottleneck. So really, key to a lot of algorithms is finding the right basis in which to express things and reducing to the right precisions for capturing significant data. It's ironic that for years we pounded on the GPU people, give us double precision. And when we finally got there in HPC, we realized that in many cases, we don't need double precision at all. We need it occasionally, we like to have it, but we should always tune to the lowest precision available. Thank you.
Thanks a lot. Okay, so I'd like to direct the second question to Professor Banda. There are actually a good number of questions, so I'd like to discuss you. One of which would be is the non-blocking also all completely hardware as agnostic?
Yeah, so non-blocking multiple counts of the application, you can have different mechanisms to implement it. So if I don't have any like a basic implement, the Rdma means I can implement it in software. Like if I have some ID rows, they can actually perform the computation or the communication. Okay. So in a way, it can be dependent on the hardware. But the example I showed, especially with the DP technology, that actually helps much more better. So we have more ARM cores there, we can actually perform the correctly on there. So either way, you can go to the.
Thanks a lot for the answer. It's pretty good. I'd like to direct this question to Mr. Dave and Professor Rashid. So what are the key takes from the talks, and what are the outputs so far for the current work? So I'd like to Dave and then.
So basically, we look at the first of the way the Banda. There are a lot of things that, for example, when Dr. Banda talks about the computing continuum, This is true, this is happening already. HPC have changed. I'm a dinosaur. I have been in Saudi Arabia for 15 years, and when we started with very traditional HPC. And there's the question: should we integrate AI or not? So basically, the question of AI, the question of data, the question of what is next. But is asking what is next after that. We already know what is here. Huawei research have been doing lots of work, and they call it distributed computing versus cloud data. And we think that we already compared, and we will see better. And they are focusing on, and if you look at the trends from my side, when I look at the trends, I look at it's mostly the scalable, it's mostly the resource management. But when you look at the scientific research, it's the problem itself. How can you make the problem better? If you look at the sort of trend, basically, how can I make optimize the tools that I have for what is coming next? And how can I do it faster? That's okay.
Amazing. And your thoughts on EFO?
The output based.
Okay, so I think first thing is that I mean we can see that HPC is getting better and better. We are getting better and better architectures, and we are able to optimize software for them as well. In terms of AI, we are getting better and better because of the data and because the HPC architecture which is available to us. So that is very good, and that could continue and that should continue. I think that what I mentioned that we need to work more on the whole space of distributed system, and we need to optimize the whole system in a way that we are able to run the applications in real time and make decisions, because that's necessary. And maybe more, some more efforts can be put there as well. And in terms of healthcare, I mentioned yesterday as well that I think that currently we are doing very well in terms of developing better, I don't know, algorithms to predict diseases and all that. But if we look at healthcare data at this time, for example, in the US, 20% of the budget goes to healthcare. That used to be not the case, and this is the same thing all over the world. People are getting more and more ill. They are also taking the medication, early time, obesity is increasing and so on. So healthcare needs to change. And in order to do that, I think the people who are working in this area, they need to start looking for alternative medicine. And some of the work which we are doing, we are looking at that side as well. And in terms of AI, we need to look at the risk which I mentioned yesterday as well. That yes, it is very important that we develop the best algorithm, but what about their fairness, their transparency, and the trust in them, and so on? Because the decisions are amplified in the AI-based society, so this can endanger the sustainability of the society. And I'm not saying that anyone who reads it, they will know that we can already see the signs, and it can make the humanity collapse. Many people have said that. So.
Outstanding. Thanks a lot. Now we'd like to give an opportunity to the audience if they have any questions to direct them to the esteemed speakers. So if there's any questions so far. Yes, please.
Yeah, so the question is, can I give some examples of non-working collectives? So I showed one example, like a P3D50. So we are working with the designers that is like a from San Diego Supercomputing Center. That's a very concrete application. They have been able to, earlier they used to have locking collectives. So they modified the application to introduce non-locking order to all and then bring the computation next to it. So that's how we are able to take their modified application with our library and then we able to. I think the UK there is a code also I think the X compact 3D from Cambridge. I think they're working on that. So probably what is happening is like a chicken and egg. See, many people have not like a HPC applications. They are still remaining like behind Because they don't know that no system, no library supports good non-public collective, so they don't have any incentive to build it. So that's why we are moving ahead, trying to show that look, you can do it, and then the application people can. So if you can take this idea, I just know with Audible, you can do it with the non-public broadcast, and we support all these things. So gradually in the next few years, you will see more and more such applications.
Traditionally, hardware leads software. It poses the strenuous aspects, but in this case, you see software encouraging hardware. There's 700 functions in MPI4, but a lot of them aren't implemented as well as they could be. But the more that people like DK and his group are, putting into software the possibilities, the more they encourage the vendors to follow that. So it's a good trend.
Thanks a lot. Are there any further questions? Okay, please join me for thanking the esteemed speakers again. It's been a wonderful time, and and now we will be moving on to the second round of these talks. So due to time constraints, we will be we would like to invite also this Munira and Mohamed. She is a computer operating systems specialist at Saudi Arabia. And her talk will be about Native Hpc use case for other benchmarks. So without further ado.
Assalamu alaikum. Good morning, everyone. I would like to welcome you all to this conference. Before I start, I would like to give a quick introduction about myself. My name is Munira Mhedib. I graduated from this university in 2018 with Bachelor of Science in Cybersecurity and Digital Forensics. After that, I joined Saudi Aramco as cybersecurity specialist, and I had the opportunity to work with 4 different teams, starting with governance, risk, and compliance, then with the Security Operations Center, network management, and finally, high-performance computing team. During my work with high-performance computing team, me and the team worked on a cybersecurity benchmark study that I will be sharing with you today. So let's get started. According to National Institute of Standards and Technology, security solutions for HPC systems must ensure both computing performance and security requirements. And this is what we will be exploring in this presentation. So our problem statement was as follows. The cybersecurity standards followed by cybersecurity assessors and auditors do not consider HPC complexity and environment uniqueness, which in turn demand performance degrading recommendations. I will start with a survey report that was conducted by the Cloud Security Alliance. It was conducted in 2020 and gathered 21 responses from different HPC organizations. This survey provides an insight to the level and type of cybersecurity adopted by HPC industry. One of the questions tackled by the survey explores current practices relating to the security measures adopted for HPC sector. The survey question says, what types of security control is your organization using? We noticed that firewall is the most security control in use, followed by encryption in transit, endpoint protection, and log management. We see that the list goes on. Another question tackled by the survey is how much performance would you give up for security? 0%, 0 to 1%, 1 to 5%, or more than 5% for security? Well, we noticed that minority of the respondents are either unwilling to accept any performance impact or the opposite, willing to give up more than 5%. However, majority of the respondents are willing to trade off between 0 to 5% performance for security. And this shows that despite the very performance-sensitive nature of the industry, organizations recognize the risk and the importance to address them. Now we move to an important part of our presentation, which is benchmarking. We have benchmarked against multiple organizations in HPC, and we focused on 3 main points, which were security patching, security monitoring, and vulnerability scanning. We have benchmarked against 7 locations around the world, 2 in the United States, 1 in Switzerland, 1 in Saudi Arabia, and 3 in India. So the first aspect that we focused on was security patching. The problem with security patching is that the frequent security patching causes long outages due to the complex software and hardware stack. And we can see the results in this table, where it lists the center patching cycle along with whether they have internet access or not. For our first center, which has no internet connection, their patching cycle was between 1 to 2 years. However, for the centers connected to the internet, such as the CDAC, IIT, and NIT centers in India, their patching cycle was every 6 months. And for the Oak Ridge National Labs in the US Department of Energy and the National Center for Supercomputing Applications, their patching cycle was once every 3 months. And this shows that the minimum patching cycle for systems connected to the internet is 3 months. However, this could be extended for isolated systems. Moving to our second aspect, which is monitoring. The problem with excessive monitoring using audit delogging protocol is that it causes performance issues. So we looked into it and we found that the audit delogging protocol is still under study by big HPC sites in terms of magnitude and performance. However, they stated that it should never be implemented in the compute nodes and only on the login nodes. On the other hand, syslog was found to be the main logging protocol for most of the HPC sites. Moving to our last aspect for today, which is vulnerability scan. Vulnerability scans may cause, the problem with vulnerability scans is that they may cause job failures on the compute nodes. And we found that HPC-specific sites scan only the login nodes without focusing on the compute nodes because they have the same configuration and structure. However, for non-HPC-specific sites, they scan pool of nodes, including the compute and the login nodes. Now we move to the proposed architecture. Now that I have mentioned compute node and login node multiple times in this presentation, let me explain what I mean by compute node. So compute nodes are the core of HPC where all the critical jobs are running. And we're trying to, in our proposed architecture, we're trying to secure those nodes by introducing the login nodes. The users will not be able to connect directly to the compute nodes. By introducing the login nodes, they connect to the login nodes first, and then they connect to the compute node. And to add an extra layer of security, we can deny the access to the compute node entirely and rely on submitting jobs to the compute nodes through the login node. We if you decide to create your own cybersecurity framework, we recommend involving outsourced cybersecurity consultation services to assist and help in that. So we did our research and we found two cybersecurity consultation services that can help you. The first one is Abertium, which have helped the Oak Ridge National Labs to create their own cybersecurity framework. And we also recommend HPC, which is a consultation services company specified in HPC. These were our references. I would like to thank you all for listening. I hope you enjoyed my presentation. And if you have any question, I would like to help you to hold it until the next panel discussion. I would like to take this moment to thank my supervisor, Brahim Al-Fouaris, and my mentor, Ahmed Barrada, for helping me in this project and in understanding HPC. Thank you.
Thanks a lot for the awesome presentation. I'd like to call upon Mr. Rick Quilton. Rick will talk about the recent technology developments and work with customers on reducing runtime and improving quality results of biomedical analytics, genomics, workflows, while also the dramatically reducing carbon footprint of the technology required to achieve these goals. His work researching to develop multidisciplinary science and technology to enable a better quality of life and a smart economy with a focus on real-time intelligence and dynamic automated system management. He has published over. So, without further ado, please, for yours.
Okay, thank you very much. Thanks for hosting me here also for this session. I'm going to do something slightly different than what we've seen so far. There's not going to be deep dives. There's not going to be anything related to code and to code optimizations and to code deployments. I do want to talk about a couple of items that do require our attention. Now, if my colleague Zishan has talked already on the first day about what we have been doing with the GA toolkit in improving any omics workloads that can be deployed on the platform. So it is a broad deployment capability of that software stack on the different platforms, which can reduce the runtime of that tremendously. So I'm not going to go there. What I want to draw attention to now is talk a little bit about what we are going to experience in the coming 1-2 years on a data center level. If you want to run and optimize the run and optimize the energy consumption and reduce your carbon footprint, you first have to put a stake in the ground and know where you are from a data center perspective to determine where you want to be and how you want to reduce your energy consumption and your carbon footprint tremendously to make the world that we live in a better place for everybody. And that's something that we need to think of and need to work on before we start on the deployment, the development, and the installation of new systems, because there's a lot happening at the moment. Now, once we have that stake in the ground, we can define a path forward and define what we need to do and how we need to operate our supercomputers in order to optimize the energy footprint and to reduce the carbon footprint, or even contribute to the reduction of carbon footprint by, I'm going to show you in a second. So let me get on to that now. We need to get to a problem statement first. So a problem statement first is what we're going to see in the coming 1 and 2 years, dramatic changes in power consumption. We're going to see dramatic changes that are going to have a huge impact on the data centers from which we're going to deploy our supercomputers. So we're seeing processors that we're using over time. They have been increasing since 2014 to now, 2022, 2023. We're going to have processors of 400 watt each. So when you run a benchmark on that processor, and you utilize that processor to the maximum, it's going to consume 400 watts. And guess what? If you put 400 watt in, it's going to generate heat also for 400 watts. So you need to get rid of that heat. And one of the issues that you're going to run into now, starting now basically, is that you can't cool that with air. You can't cool that with air for many reasons. One of the main reasons is that air is not efficient enough to transfer heat away from the always getting denser technology that we're getting. So the dense technology applies to the processors, it applies to the GPUs that we're deploying. They're getting smaller. The TDP values are increasing. The TCase temperatures are decreased, which means that the temperature on which the dense processor can operate is getting lower. So if you want to cool that efficiently, you need to do something else than air cooling only. Now, processors are one step. So you have, typically you deploy 2 processors in one node. In a dense solution, that means that you have a 1U tray, 2 processors, meaning 4 400 watt processors in a 1U tray. Aggregate that, keep those numbers in mind. GPUs, we're moving to 700 watts for GPUs. 700 watts. You want to deploy at least 4 of them in one server. 4 GPUs in one server at least, and 2 processors in that same server. Remind those numbers. Memory, we see increase in memory channels per processor. We're going from 8 for some vendors to 12 memory channels per processor. That's going to aggregate to over 288 watts per server, the increase of the power consumption. And again, power consumption, power really means also that you need to cool that. You need to be able to cool it efficiently. And that doesn't mean that you can cool it with air that is blown up into the data center, pulled through the compute nodes into the hot aisle, and then removed again. That's not efficient enough. So next topic, network adapters, another topic. So I'm only talking about the key components in a compute node. Processors, GPUs, memory, network adapters. I'm not even talking about the voltage regulators that you have in compute nodes, which need to do the power conversion from 220 or 3-phase into something like 24 or 48 volts nowadays in those new server and highly GPU equipped servers. Now, T-case, I mentioned it already. It's going down dramatically. At the moment, what we see is that already, it is ready for the top bin processor SKUs. It is already around 70, 71 degrees, where I still remember that it was 85 degrees from a T-case perspective. So the temperature on which, what the maximum temperature basically is from the surface of the processor that you can run it in before it starts disintegrating, self-destructing. So you don't want to run processors above T-case temperature. You want to run it below that T-case temperature. So, you know, from an energy consumption perspective, this all looks ugly. From a cooling perspective, this also all looks ugly because it means that we need to do something in order to scale our solutions into the use of the highest performance processors and GPUs that we have available. Now, so if you look at additional things, so I was only talking about the key components in the left 4 quadrants. Think about the fans that you would require in those nodes to pull down the air from the cold aisle into the warm aisle through the racks. That is going to be dramatically increasing the power consumption with the increase of the TDP values. Heat sinks that need to be changed, redesigned, and optimized. A lot of CFD work has to be done on that to make sure that happens. Air handling capabilities in the data centers. I mentioned the voltage regulators already. High capacity power supplies. So if you want to run 2000 watts, even though then you also need to have power supplies and provide that and provision that, where 800, 900 and 1100 watt power supplies not that long ago, I'm talking about a year, 2 years ago, were sufficient for computing. That's not the case anymore. That's going to change dramatically. So you see high power draw, you see increased density of all the components that are being used in our technology, densely packed on each other, because we want to have an dense as possible solution in a data center, because data center space translates to cost on the operational side, and that's not something that is easily absorbed. And to reduce TKs, it all adds into no good news at all. So very bad news if you look at it from the surface. Now, look at what fans bring into simple compute nodes. In 2014, on average, fans were using about 400 watts maximum. That's going to go to 1,000 watts. For 1,000 watt servers, what I'm trying to explain in this picture is what the overhead of the fans is going to be on your operation, on your compute nodes. So in 2014, an average server was 400 watts. It's going to move to 1,000 watts by 2023. So you're going to have a dense solution, a 1U tray with 2 nodes in there, 2 nodes of 1,000 watts. So on a compute rack perspective, 1U rack is going to be 2 times 1,000 watts, so 2,000 watts. So we're going to cross boundaries in the very near future. Boundaries of 100 kilowatt on a normal 42U 19-inch rack boundary for the deployment of compute technology. That is impossible to cool with air, and that's why we need to step up our play. Now, the consequences and the energy consumption and the overhead that fans are creating for the workloads also has a very big impact if you keep using air cooling technology. We measured it, and we looked at it, we studied it, and if you're running a real stress load on the CPU side, on your nodes, then by 2023, your overhead of your fans, if you want to stick to air cooling, is going to be 33%. So 1,000 watt node is going to have an additional 33% overhead only to blow hot air around. That doesn't sound like a smart approach. That doesn't sound like a sane solution for large-scale deployment, and not even for smaller deployments. Now, there's different topologies on the server designs that we use for the deployment of issues. So on the top left, for viewers, right, so on the layout side, the top one basically represents how we deploy our dense solutions. That basically means in a 1U tray, we have 2 socket nodes together, or in a 1U tray, we have 4 GPUs and 2 sockets available. So that means that on a 1U tray, you will have at least a 2 kilowatt power consumption, or a 1 kilowatt plus 4 times 700 watts power deployment and power need. So from a power provisioning perspective, to your compute nodes, things are going to change. 632M power feeds are not going to be enough anymore. So the way you are designing the bus bars and the way you are connecting your power feeds to the bus bars even is going to need consideration due to these huge changes that we're going to see in the way power is going to be consumed on the rack boundary. Now, power efficiency, in the many years that I'm working in high-performance computing and in many engagements and many talks I have with customers, I continuously still see that we're not speaking one language when we're talking about this topic, power efficiency. So in RFPs and in tenders, you see different things and different requirements where they try to ask for the same thing, but they ask for different things. Let me explain what I mean. This is a formula, is it? Yes, looks like a formula. It's a ratio. You determine the ratio how efficient your data centers is. So power use efficiency, PUE. In RFPs, people talk about PUEs. In the responses, vendors talk about PUEs. What PUE means is that you look at the total facility power and you divide it by the IT power. And with total facility power, I really mean the total facility power. That also means the chillers that you're using. That means everything that you use in the data center is part of this equation. If you're not doing that, then you're speaking a different language, and you're probably talking about a different equation. An equation like, for instance, the ITUE, which is total IT power divided by the total compute power. So we run into different variations and different sets of inputs from our customers, and we try to bring it always back to one and the same equation that we can agree on and that we have a clear understanding of on both sides, both on the customer side and our side. And we talk about the same thing because we're all looking at the same end goal, and that is the most powerful and most power efficient supercomputer deployment that is available. Some other variations that we run into where the end goal of the customer basically was the top line. These are the variations we've run into in the last couple of years, which create a lot of noise, which create a lot of misunderstandings if you don't properly address them up front and you put the stake in the ground to agree that you're talking on the same topic. Now, everybody should know this. You know, the one on the left, that's what we're doing for ages. That's basically agri. That is where you use chillers that create cold water. Cold water is used to create cold air. You blow it around in your data center, you put it back, you absorb it again at the warm side, and you cool it down again and reuse it again. It's a circle of life for air. Not very efficient, because the direct water cooled one on the right, we started that in 2012 when the entire team that now local was still IBM. The heat transfer to water of all the components that are direct water cooled is 4,000 times more efficient than heat transfer to air. So that heat transfer of the components to water is 4,000 times more efficient transferring heat to water than transferring heat to air. So if you're talking about the compute nodes that we're going to deploy this year and next year, the year after, you're going to require an Arctic hurricane in your data set if you would be willing to cool them with air. That's impossible. It's physically impossible. It's scientifically impossible, because you will not be able to transfer the heat away from your components fast enough. So if you look at these three topologies, start at the left one. That's what we've been doing for as long as I remember, and that's a long time. The middle one is air-cooled with additional heat exchangers installed on the rears of the racks, through which cold air was running to cool down the air that comes out through the racks before it goes into the hot owl with a very high efficiency. You see already the PUE value is improving dramatically by simply adding doors on the racks, which have cold water in there, and the water is cooled down before it is blown back into the data center. Now, if you look at the right side, the direct water cooled side, that's where you're getting somewhere, because that's where you're getting a PUE ratio lower than 1.1. You're getting it lower than 1.1. And the interesting part of that is that we're cooling it with water and with real water. So it is not something like the green stuff that you're using in your car radiators. It's really mineralized water. We're cooling it with water of 50 degrees Celsius. At this moment, we know that we have to get down to about 40 to 45 degrees for the coming generation, simply due to the T-case temperature that I just mentioned. We need to be able to keep the temperature of the processors below the T-case temperature. If you don't do that, they will self-destruct. And that's not what you're looking for with compute technology. So The right side is what we have been doing since 2012 with many large deployments throughout the world, direct water cooling with warm water. And you know, from a efficiency perspective and carbon footprint perspective, you're getting somewhere there. You know, you're not entirely there yet, but you're getting somewhere there. And you notice that on the page on the right side, there's some space available yet. There's some space available yet because I want to add something. So if you really want to contribute to what you're doing with the environment and the reduction of carbon footprint, we need to smarten up. So it's not only that we need to reduce the CO2 footprint that we have. You know, 1 kilowatt per year translates into 40 tons. So 40 tons of CO2. 1 kilowatt per year. We're having data centers that are megawatts. So imagine what that means for footprint on a global scale. Now, this is where we're getting somewhere. So we've been reducing in the third direct molecule phase, we've been reducing the amount of heat that needs to be processed after the computational work. So we've been very efficiently cooling it down with water of 50 degrees Celsius. At the end of the loop, that water is going to be around 60, 62 degrees Celsius. It goes down, it comes back in that same loop. It's a closed loop, it's our loop, it's a water loop. So it's not the primary data center loop, because between those water loops, there is a coolant distribution unit with a heat exchanger. That is doing the cool down of that 50 degrees water, 60 degrees water back to 50 degrees. And that can be done in multiple ways. So remember, the water comes out at 60 degrees Celsius. Why 60 degrees Celsius now? Because that's when you can do something efficient with water. You can use it for other purposes. What other purposes? Well, a couple of things we are doing is what you see on the right side. With one of our customers in Germany, a very big one, we installed absorption chilling. So what we're basically doing is we're not using chillers to create cold water. We're using an absorption chiller, which is nothing else than a reverse heat pump, to create cold water from the warm water. So that delta T of 10 degrees Celsius for us is enough to create cold water from the warm water with an efficiency of about 60 degrees. So that means cold water for free with energies that you have been creating by efficiently cooling down your processors, your memory DIMMs, your voltage regulators, etc. in your compute environment. That's pretty efficient. Now, that is one step. That's one thing you can do. And that's where you positively contributing to the carbon footprint, because you're not going to use your chillers anymore to create that cold water. You don't need your chillers anymore to create the cold water. If you have enough warm water, you can create enough cold water also to cool down those components in your data center that still require air cooling, like network switches, like spinning drives and storage environments, etc. They're not as heat intensive as the compute environments, and that can be done with the air that you have. Water cooling spinning drives is kind of an interesting exercise. That is moving parts, cooling moving parts with water, direct water. You need a hot plate construct, and that is not there yet. So that is one approach where we improve tremendously the PUE value, and where we reduce the carbon footprint also. Now, reuse of the heat, optimally using. What can you do? Well, there's 3 ways to get to a better ERE value. Remember the 4 formulas I had on the screen? We can route it to the cooling tower on the roof. So if the water comes out at 60 degrees Celsius, the heat exchanger in the CPU transfers it to the data center loop, and the data center loop has the cooling loop on and then cooling tower on the roof. Not very efficient because you're blowing hot air into the atmosphere. So you're not doing anything with the heat that you're creating. The second thing is direct reuse. We see more and more initiatives happening in this. It's where the heat that's been generated can be used to heat other things, like glass houses. I come from the Netherlands. In the Netherlands, there's a lot of glass houses for tomatoes, for flowers, etc. Heating up those glass houses is one of the initiatives we see in the Netherlands. Another thing could be direct reuse in the form of swimming pool heating. We need to close down swimming pools at the moment because the swimming pools cannot afford the gas bill anymore. It's an option that we can use there. We see initiatives all over the place now. I'm working with one company in the Netherlands that is working very closely with construction companies. They're now deploying single racks into new apartment buildings in a closed facility in the basement. And they're using the heat that's generated by that for the heating of that apartment building. They have tens of these buildings already. It's a startup initiative that started 2 years ago. It's building. Yeah, they have defined the grid. They have defined the compute grid, which basically is a cloud approach for the HPC environment that they want. And it's transparent for the end users, and they use the heat that's been generated by direct water cooling through the heat exchanger in warm water that can be used for other purposes than only blowing it up in the atmosphere. The indirect use one is what I already mentioned. That's where you can use smart technology, you can use technology like dispersion chillers to gain something else, like cold water, like the creation of cold water, or whatever you want. Thank you.
Thanks so much for the outstanding presentation. And now I'd like to call upon Mr. Lawrence Tyers, the Vice President of Data Direct Networks. So, Mr. Lawrence, his interests lie in HPC software, file systems, government and digital security, cloud storage, and analytics, selling DDN solutions together with strategic end user and key partners, working cross-functionality with the product management, engineering, scales, and other high performance and hyper scale solutions that meet and exceed customers' expectations. His talk will be on accelerating intelligent infrastructure for the changing world. And without further ado, I'd like to welcome you.
Good morning. Actually, good afternoon. So at the end, everything becomes high performance. So we're going to try to compact this presentation and deliver what's the results to you today. I hope you appreciate it. So I'm a French engineer. I joined DDN in 2001. So today we're going to discuss one of the most well-kept secrets of the HPC industry, the storage. So you heard during the panel's presentation yesterday and today the growing importance of data scientists, growing importance also of acquiring data from IoT, various sensors, or model-generating data, processing the data, curing the data, healing it, cleaning it, and obviously, which is a new big thing in Saudi, Europe, and everywhere in the world, about data governance, where data is kept, and the security associated about it. So, as I said before, what's missing, in our opinion, is the storage, obviously. So, data is the source code of artificial intelligence and HPC. Data is related to AI, and we believe storage is also related to AI and HPC. So this is us. This is one of the examples of what we are shipping today. It's an appliance. We still do hardware R&D at DDN. We do this for almost 20 years now. And most of the serious, biggest or complex supercomputer in the world have been using DDN storage since 1998. Some of the big brands are even using our storage internally. So actually, obviously, that slide very quickly, but that can give you an idea of why people are using our storage as well. In the world of life science and pharmaceuticals, we have done a number of deployments, especially working with the new drug discovery industry. But obviously, we have some application for cybersecurity, autonomous vehicles, climate modeling, green energy, but life science, to be honest with you, is a big pillar of our business in the US, in Europe, but also in the Gulf. And in Saudi, we've been powering life science behavior initiative for quite a while as well. The Saudi genome, this cost. So what's the big secret to enable all this great code that you've been seeing with Dr. David, Dr. Lambda? We believe that you need a very special storage to be able to run at this speed and to make sure that your infrastructure, compute, GPU, CPU, etc., will never be slowed down because of the storage bottleneck. So you might say, that's fine, I have a lot of storage internally in my computer, my GPU nodes. That's true. Some of these nodes, not all of them, some people, they like to have storage-less compute infrastructure, but there are some vendors or architecture which still require local storage and compute, so you end up getting a lot of storage locally. But what about if your data set is bigger than the local storage? You need a central storage in this case to run your science. So I took a picture of one of our proposals and we blended it into this marketing slide. But we believe that in order to enable your workflow, you need a very parallel file system technology enabling read-write at blazing speed. And today, this is what we are shipping. The code name is Exascale 6. It is made of open source and not open source software for parallel file system, but it is running in hardware appliance. So we've been working very, very hard over the past 10 years on this solution. So this is the 6th release today that we are shipping this year. We added, so this is basically an HPC AI solution, but we added over the years hundreds of features as well, like file protocol access with NFS, SND, and S3 on the cloud, synchronization to cloud, copy tools, parallel copy tools, in order to move data in and out from the cloud to the HPC on-prem or vice versa. Security, I brought many hints to security and data governance in these presentations. So you're going to be pleased to know that with Exascale from DDN, you have a complete end-to-end secure infrastructure. Recently this year, we added client-to-server compression and encryption. Obviously, we had already encryption at rest. And in addition to that, we also provide the free of charge feature, multi-tenancy. So life science, genomics, but cybersecurity, oil and gas, more and more customers deploy our solutions with multi-tenancy, where we have a complete isolation between your tenants. So, in a nutshell, you can do more with us, more with less time. You can enable more and more computing. Now, I would like to tell you a bit more about what makes sense when you do an RFP for storage. You have the IUR, IU500 benchmark that helps you a lot to design your infrastructure, your acquisition. But please do not compromise on the performance. It's very easy to be honest with you right now to be providing throughput and release with end-to-end workload. But if you are talking about end-to-one with shared file access, this is a bit more difficult. So we encourage you to look at the benchmark that we produce. And and also with a strong emphasis on writing performance. Writing performance is definitely something that you don't want to overlook. In terms of collaboration, as I said before, our solution is not open source, not entirely open source, but some of the components are. So we decided to enable cooperation with industry and university to take more advantage of some of the features of the platform that we have. One of them is multi-tenancy plus, as I said before. We decided not to offer this feature as a commercial feature. It's more a set of professional services and consulting services that enable you to adopt multi-tenancy in your HPC or initiative. Another one is the portal analyzer. This is a feature that is already available in the solution, but you can customize it and you can develop code around it. And we are open for collaboration. Like if you acquire, obviously there is a catch. If you acquire our hardware technology, we are willing to do cooperation with you on the long term and acquire together from the data center statistics from your workloads, so that basically you can basically acquire smarter in the future of your storage. You can decide if you need more flash or disks or different tiers of storage more intelligently. Data sharing is also very, very important these days. All the industry goes to flash. This is a known fact, but this is not actually entirely true. There is still a big demand for affordable media. And we have a solution that enables you to have both like a hybrid solution of flash and disks. But you need to move data from different tiers, and we have the software to enable this. But it's open also to be integrated with your jobs delivery. HotNode is the last example we picked, HotNode Plus, to foster collaboration, especially with the compute node members. Like I said before, you might end up with local storage in the compute node that you can use for your non-coherent stretch. But what about using it as an extension of our data system? So that if you need to read data, you're not going to read it again from the network, but you can read it from the local cache. So that's another example of what we can do. So all of these features are free, but if you can collaborate with us, you can extract more resistance out of them and you can integrate it into your environment. So feel free to contact us. We're here on the roof, and we want to do with you on research. So I would like also to thank my team. Please stand up, they're here. Thank you. Thank you very much. And have a nice day.
Thanks a lot, for the outstanding presentation. Now I'd like to call on Dr. Nadia. She is a professor in the Department of Computer Science, College of Computer Science and Technology, and her research interests is basically quantum cryptography and security, and also specific higher. So without further ado, for Nadia. Okay, just a fun reminder, if you have any questions, you can use the QR code scan, use the QR code scan on your phone, and basically you can participate, submit your questions, and we'll be more than happy to give these questions to you through the webinar. So now that the floor is available to Dr. Nadia.
Thank you very much for inviting me, and I'm happy to see you here. Coding in the entanglement domain. Entanglement is a characteristic that is specific to quantum physics. And this is what we will see in this talk, characteristics of quantum physics that apply to our field of computers. We will also talk about advantages of quantum computation methods. They are not ubiquitous, so quantum computation is good for certain things, but not necessarily improving much on others. I will also talk about some of the applications that we have done ourselves about some present state of quantum computers, and then maybe finish with some ideas. We have mainly three properties of quantum physics that are applied in quantum computers that you do not have in classical computers. And then those are superposition, measurement, and entanglement. And measurement, even though it sounds very familiar to us, in the realm of quantum computers, it happens differently than what we are used to in general. A classical bit is physically kept by a voltage level, whereas a quantum bit is kept by, it can be physically embodied into several ways. One is by the polarization of light, in which case, let's say vertical is 1 and horizontal is 0. It can be embodied as the spin of an electron, which says 0 is up and 1 is down. Again, a classical bit is a 0 or a 1, whereas a quantum bit is a 0 and a 1 at the same time in different proportions, and is called a superposition. This is the first difference, that you have superpositions of 0 and 1 at the same time, which gives you the parallelism right there into the physics. You have the 0 and the 1 in parallel, quantum parallelism. What is the drawback? When you measure a superposition, what happens is you get back a classical bit. You get again either a 0 or a 1, but not both. You're back to classical knowledge. We call that a superposition collapse. The third property is entanglement, and this is the most unusual one. When you have 2 or more qubits, 2 qubits, let's say, which actually have a state that is in correlation with each other. So both of them are in superposition, but their state is not independent, even though they may be physically in 2 different cities. Which means that if I have such 2 qubits which are in a superposition and I am looking at one of them, it will collapse, but the other one will also collapse. They are like sisters working together. So these are the 3 physical characteristics that we see in quantum computers, which we do not see in classical computers. Now, what are the advantages? The most successful branch of quantum computation is in security. Successful in the sense that we have the bad news, because with quantum algorithms applied on sufficiently large quantum computers, you can attack security schemes, mainly those that rely on public keys, public key crypto systems, those that rely on mathematical functions, one-way mathematical functions. The good news is that once you have been breaking the present schemes, you can replace them with quantum security schemes, which are way more secure and also secure against quantum attacks, because they rely on physical properties, not on mathematical properties. You cannot change the behavior of light. It's given by nature. There are applications which are very suited to quantum computers, and here are the 2 best-known algorithms, Grover's algorithms and Shor's algorithms. Of course, we are looking forward to see new breakthroughs here, but from the theoretical perspective, this is the best-known what we have right now. Which means that an unstructured search that you do on a classical computer in order n, with a quantum computer, you can do in square root of them. And then factoring also has an improvement towards polynomial time. I have chosen here 3 applications that I want to share with you that we directly worked on. And we all know that cryptocurrencies have its own stories with ups and downs. Right now, we are a little bit on the down, but who knows? We don't know exactly what the future brings. But in order for the currencies to work, we need miners that try to find the golden laws. Golden laws means to search over and over again along this red path to find a number with a certain property. Now, we have shown in our work that if you use Grover's algorithm, you can do this in square root of n time, which means that a quantum computer of a reasonable size will outperform all other miners. So once a quantum computer reaches, and it's not much, 1,000 qubits, then probably the miner's landscape will change into quantum. So here is a domain in which quantum computation will enter, we believe. When we published this work, we were actually appreciated that we even gave bound on how big the quantum computer has to be. The idea was not necessarily super new, but the evaluation was. The second application is quantum bit commitment, and it applies to a setting of zero trust partners. And here I want to describe a little bit what bit commitment actually means. We have 2 partners that do not trust each other, and Alice hides a bit in a safe. Then you have the time elapse. And this is here the core, because at this point when you wait, Alice is not allowed to change, and Bob is not allowed to see. So how do you design the protocol that this is happening? And then at the end you have Bob that can accurately read. We have results here from our group that you can do this with a quantum computer, and we have done so with IBM Quantum Experience, which right now offers for academia a small size of qubit that you can use for experiments. So we have experimented with that. Our claim is that with a large enough quantum computer, you can apply this directly. Errors are tolerated. It depends how secure you want it to be. You can do it as secure as you want, depending on the availability of the hardware. The last application, which we also found that quantum computation comes in with new ideas in the sense of its paradigm comes with capabilities which we don't see in the classical computation. And quantum steganography means that I have to hide a message into an image. The image in this case is given by qubits with the polarization, and the stenogram, the hidden message, is given in the entanglement domain. Now, what happens here is that each qubit carries 2 properties, which again, in classical computation, you don't have that. A bit is a value, and that's it. But here you have 2 properties, the polarization and the state, whether it is entangled or not, which means that in this case, the image is exactly as the original, and it is still hiding. Whereas in the classical version, you say, okay, the image is changed slightly. Here it is not changed at all. There is absolutely no way of checking that there is something hidden there. Okay, I think I will go through this a little bit further and faster. I just wanted to show the present state of the hardware. This is not our work. I just wanted to show that there is, we feel that we are now at the level between the theory and the practice, and we are trying to see when we are actually stepping over. The IDF right now has 127 qubits, so not kilo, not mega, just bits, qubits. And then we have quantum computing incorporation, which tries to do a merge between classical computers and quantum services. Then we have Xanadu, which works with photons, and their claim is that they try to do quantum computers at room temperature. The first quantum computers were at very low temperatures, like very close to absolute zero. I will skip this a little bit and say that there is interest worldwide, including China. And there is actually a competition between what we have seen before, Canadians and US companies and China. For China, I would like to say that they have a communication with a satellite based on quantum security, so very far away and very secure. And then they plan to have a quantum computer with 60 qubits, which brings us to the idea that quantum computers are used in competition, including this cyber war, I will say. To protect us from this, there is an effort to develop security systems that are hard against quantum attacks, but it's maybe more difficult than it seems. We have NIST that has chosen and standardized 4 encryption standards, and within 2 months, one of them was proven to be insecure. So we are in there, hanging in there to see what is going to happen. We have no certainty about these standards. So we had students working on this project, especially the second one was done by students had actually the major contribution to this one, and we are very proud of it. We also are developing a collaboration with Aramco, and this is our group from our university and from outside. I would like to honor also the students that have been working with us. And thank you.
Thanks a lot, Dr. Naya, for the presentation. Now I will call upon the second part of today's talk. Dr. have a round of a discussion to share a few questions with you, and on that note, we'll be ending our first part of the conference. Welcome back. So on the interesting point of quantum computing, so basically because now it's a big challenge nowadays, basically to simulate and to be able to replicate an environment that would actually carry on quantum computation. So on that note, if I could just ask you a question to each of you, what are the prospects and challenges and applicability of actually adopting this technology, especially at this certain stage?
So I can only speak for our organization if I talk about moving forward with the quantum technology. If I look at the potential of it in the future, it's going to be huge. We're not there yet. It requires ecosystem changes. It requires applications and the modeling of applications to become from scratch. So it's not a thing that's going to happen overnight. I see a future for it, but for us, it's still reasonably far away from an operational perspective. We're not really seriously looking at the development of technology to participate in the quantum challenge.
Yeah, same thing here. I think it's better to ask the experts over there.
So from my side, I actually talked about this during my presentation, so I don't know what else to add. For me, I think because I have been working in this for 10 years and I started off in pure theory, and at the time everybody was looking at us as somewhere outside of reality. I am actually surprised that after 10 years I am invited to speak here. And I have questions about what's going on, if this is like a war between which countries. The competition, my perception, that the competition to have the upper hand in quantum computers is really high. Of course, I am not within the competition directly. I'm an academia, so I just can tell my own opinion and my own experience over the last 10 years. I did not really, my realistic self, think that I will be here after 10 years, that we will be here after 10 years.
Thanks a lot. So, Ms. Mira, I would like to ask you about the basically future of high performance computing, especially with around parts. What about the prospects and possible applications?
Well, I can't speak about HPC, but my perspective is cybersecurity in HPC. They are improving, and there have been so many improvements in the last few years. And I believe that also in the future there will be great work.
And if you further growth about HPC and the future product as well. So back to here, all right, the vision for them.
Thanks for asking. So you've seen the presentation, what we are showing today. For the near future, for next year, we are developing a new appliance, which is cloud native, but for on-prem installations. So this is our near future, and that will enable people who went to the cloud and will go through the pain, my French, of porting their application to S3, for example. This will enable them to get back some of their data, controlling their data on premises, but leveraging their past efforts of porting their application to S3. So we believe that this S3 cloud native storage appliance will be a good addition to what we do for HPC and Scratch and work file systems. So we're very busy doing this. Thanks for asking.
Thanks a lot. Due to the time restrictions, we'll end on this note. And now we would like to call on the Dean of Excellency Dr. Rdma Mahedin to honor the speakers. Let's start first, we'd like to invite Professor David Pease. Professor D.K. Panda. Mr. Walid Shari. Professor Rajin. Ms. Munira Al-Qaeda. Mr. Ray Koopman. This is the role of our identifiers. And finally, Dr. Naya. Okay, now we have a short break, and afterwards we'll be preparing for the second round of presentations. So please, questions are available. As for clarification, the break will be until 1 p.m. So you can also kind of be back the time, so we can begin on time. Thanks.
please scan the QR code if you have any questions. So now, please join me to welcome our first keynote speaker, Mr. Mu'taz Al-Barwani, the Senior Director of the Center for Research Computing at New York University, Abu Dhabi. Mr. Mu'taz Al-Barwani will provide an insight into the Center for Research Computing at New York University, Abu Dhabi, the infrastructure, application, tools, and the skills needed to manage all computational data in the center. Please join us.
Thank you very much for inviting me to come and speak at this conference. I think this is my second time I speak at Saudi HPC. I spoke last year in 2021, but that was virtual, so no one really got to see it. But I was there. Okay, here we go. So my name is Mu'taz Al-Barwani. I'm the Senior Director for Research Computing at NYU Abu Dhabi. NYU Abu Dhabi is the second campus for NYU, which was opened in 2010. The third one is in Shanghai, China. So our university, very briefly, is a self-contained campus with its own research and education program. We have many undergraduate programs in 4 different divisions. We also conduct a lot of research and arts as well. My talk today, I will talk a little bit about our center. I'll talk about HPC and some of the research that we do. I may not get to the last part because I'm told I have to cut down a little bit, so I'll try to be quick. As many centers that are well established, we have to have a mission and a vision. The working of this mission and vision actually was put together when I started this center in 2012, and 10 years later, it's still very valid and it's still very accurate to, and it's still something that we strive to achieve. Our strategy, I'll just talk about this very high level, maybe is enabling researchers and collaborating with them. So our job is to make sure that researchers and faculty at our university can conduct their own computational and data-related research. This is our main job, and we can do that through implementing and developing tools, implementing new clusters, and refreshing them. The second aspect is the bottom one there is actually carry out innovation in HPC and technical computing. And towards that, we are partnering with vendors to establish this center of excellence in Abu Dhabi for high performance computing. And if I have some time, I'll touch on that a little bit. Our center has basically 3 areas of focus. HPC is one of them. The other is research support, and that is mainly support of computational and data research that's not on the HPC side. So it could be any computation, it could be data related and so on. And now we are building a data science capability as well, both in human resources and infrastructure. I have a sizable team. I think that is about 11 people, 12 including myself. And I have scientists who their focus is on the innovation part, the application support, who support our users and the installation of applications on the HPC, and obviously the sysadmins who look after the cluster. Research support is, as I said, infrastructure and development outside the HPC. Fatma Al-Hajri at the bottom there, the junior HPC application, is actually our first Emirati intern who will be with us for 3 years. By the end of this, she will be a fully fledged HPC application specialist. And she'll be the first Emirati to achieve that knowledge and expertise. Okay, so let's jump to the HPC. There's a picture, as you can see, from the logos, Dell and AMD. This is the pitch for the Dell and AMD guys. Our current cluster, named Jubail, launched in March this year. And essentially, it is a 1.3 petaflop HPC cluster. It's based on AMD EPYC Rome, not Milan. We could have gone with Milan, but the performance versus price didn't make sense for our application. So we went with Rome. We got more CPUs for it. We have two categories of nodes. We have what we call a bulk node, which is CPU only. And then we have a versatile node, which is GPU, NVMe, and has the capacity to, or capability to add more memory. All of them are starting at 512, but the versatile nodes can go up to 2 or 4 terabytes. We have a few specialized nodes with large memory already in place, and we have all of the GPUs are A100s at the moment. We still have V100s from our previous cluster. I don't mention our previous cluster here, but we have around 13,000 cores connected to this cluster as well. So we have a total of about 40,000 cores. Our storage that you see there is Lustre-based. We are in the process of soon to be releasing an RFP to refresh our storage. So hopefully by February, March, we'll have a new storage in place. The InfiniBand connectivity is HDR for this cluster. Most of the nodes are connected at 100. Here's the picture of most of the clusters in these 2 rows of about 11 racks at the moment. These racks are air-cooled internally, but they're connected with chilled water and cold loops. So we don't cool the whole data center, we only cool the rack. This is in reference to Rick's talk earlier. So it's somewhere in between the cold, the completely air-cooled and the chilled doors. Just a picture of some comments. One of the things that we implemented with this new cluster is we wanted to lower the entry barrier for new users to make use of the HPC. And the way we did this was introduce a tool called Open On Demand. And what Open On Demand did was it allowed people to interact with the cluster through the browser. Sure if you can see it from there, but we have already some interactive applications on the left here. You click MATLAB, Mathematica, or any graphical application, and you can view it through Firefox or any other browser. You can also use Jupyter Notebook or Lab. So for the Jupyter Python people, for R people, we have all of those data scientists now who want to use the cluster, can easily do this without having to learn Linux or to control things through the command line. How we planned it, just briefly for those interested in the technology, we did a technology survey. We needed to know what technologies are available, what's coming up by the vendors. We did an external review. We had some HPC center directors come in and review us and provide a report. And we did a user survey, how happy they are with our services, but also what their requirements and projects that are coming down the pipeline. And putting this all together, we managed to come up with a number in terms of million core hours, size of the system that we need, and the features that we need for it. As I mentioned, we are refreshing the storage this year, but our compute was done last year and the year before. And what we've been doing is we've been doing a cycle of 4-year planning. We did this with the previous cluster. I'll show you a slide in a minute, where we each year we spend a small amount of money rather than spend a huge amount of money at the beginning. And every year we beef it up, we grow it as needed. Therefore, we have a shorter cycle for refresh in some cases, but also we are more up to date with the new projects that are coming in as well. This slide shows you an overview of the HPC system, as far as I'm aware, in academia in the United Arab Emirates. So at the moment, our system is the largest in terms of cores and nodes. Khalifa University, UAE University, Sharjah University has a couple of small clusters, and then more recently, Mohammed bin Zayed University for AI. This is a new university that was established recently. It's a graduate level only, focused on AI only. And they currently have 2 clusters that are merging into one, which are focused on GPUs. As you can see, their computation is, I don't know the benchmark, so I don't know where it stands, but they have a significant number of GPUs there. They are in the process of buying another cluster, which will be their second cluster for their research. Our previous HPC clusters, the first HPC we had was Latina. This is the picture here. This was an HP before it was split into HPE cluster. And it was a 70 teraflop machine. And at that time, it actually made it in the top 500 for 6 months. It lasted 6 months and then it was gone. So we had that moment of fame. 512 nodes, 6,000 cores. This is based on Intel Westmere, I think it was. We had a few specialized nodes. The networking was InfiniBand QDR, and we had 2 levels of storage. Scratch was a 900 terabyte Lustre system. I believe it was DDN, and a tape and disk archive. The second cluster, which was Dalma. This is the picture of Dalma, which we decommissioned early this year. This lasted for 6 years. This was 13,000 cores at the end. It didn't start at that number, but we grew it over the 4 years. It was 700 teraflops. Most of the nodes were based on Broadwell. There were some GPUs which had the Voltas. These nodes are still functioning now. They're still running as part of the new cluster. The storage is the current storage that we have. The growth of Denmark, as I said, it started off with 236 nodes. Followed by, we had some buy-in by faculty. We allow faculty to buy in nodes when they have research funds, depending on their needs. We did an expansion in academic year 2018, 2019, and added some storage as well. And then we just added support. Over COVID, we couldn't really refresh, so we just extended the support for this cluster. The InfiniBand here was EDR. Okay, so that's the infrastructure where we are. Our computational research, just a brief slide of some facts. I apologize for the cutoff there. This is the current from AY 2021-22 for NYU Abu Dhabi. We currently have only about just under 2,000 students, undergraduate students. This is the target, actually. We are near our target. We're not designed to be a big undergraduate university. We will be growing our graduate level with masters and PhD students, mostly PhD students soon. We have a faculty of around 330 from different nationalities. From inception in 2010, so far we've had $30 million worth of external grants. Most of the funding for our research is actually internal. 5,000 research publications. So the volume is not very big, but however, the significance here is the level of the publications. These are world top science journals. We've made it in the Nature Index as well, quite highly there. Quite a few patents, and we have a very active arts and creative work. So we have multiple theaters, people working designing plays and music and painting and so on. In terms of research that the HPC supports, so almost everything, almost every discipline is represented here. Our biggest users are astrophysics, so a lot of simulation, formation of the galaxy and so on. We also do a lot of bioinformatics, so computation is not very high, but data-wise, they generate a lot of data. Chemistry, molecular modeling, NMR, climate modeling is also a very big user, so 2 big sets of code that run are which are pretty standard for atmosphere modeling and models. Computer science, they do a lot of NLP, machine learning, deep learning, robotics and engineering, for example, as well. We even have people in humanities. There's a new field in humanities called digital humanities. And they use GIS, a lot of manuscripts out there that are historical manuscripts that need to be analyzed. These get sent into the HPC. Mathematics is standard. People doing quantum computing and modeling. Psychology, we have a functional MRI lab, which again sends images of the brain into the HPC for analysis. Social sciences, we have 3 areas in our social science division: economics, political science, and social research and public policy. These actually mainly use R, they use data, these are statistic packages, but also we track the publications. We ask them to acknowledge us in every publication that they publish year on year. So the first HPC, if you remember, was launched in 2012, and we've been tracking any publications since. And 2022 obviously still growing. This slide shows you the different areas that have, in terms of the publications, we have over 280 publications to date that have access, that have referenced us or acknowledged us. And as you can see, they are the largest user. So it's genomics, ESGB is Genomics Center, and we have also our climate model, CPC. This is just a quick, some of the websites and publications, snapshots of some of the work that's been done. The Camel Lab is a lab in computer science that does focus on using NLP on translation. Now you'd say, well, Arabic English translation is done, yes, but not the dialects, not the different. People don't speak in classical Arabic, right? They speak in their local dialects of Arabic or local accents. And this lab, Nizar Habashi's lab, actually focuses on trying to do this translation. The next slide, this is some of the work that was done. Try if I can play this very quickly. Yes, formation. So Andrea Macheo, the picture there, does a lot of simulation of the formation of galaxies. And this is some of the animations of the results of the simulation, as you can see, how a galaxy forms over giga years. That's the number there at the top. Molecular simulation. We have a faculty member, Serdal, in chemistry, does a lot of biomodeling, such as this. So climate modeling with a focus obviously on the Arabian Gulf. As you can see here, this is sea surface temperature, looking at trying to model this. This is very fine-grained calculation. So this, it's not a very big area, but to get all the details, you really have to do very heavy simulations and try to get this kind of calculation. Engineering, we've had Professor Sunil Kumar looking at the engine, the jet engine, the output of the gas as it's compressed out of the jet engine in the back. And simulation like this, which only ran for only 6 seconds, actually took 700 cores and 8 days to produce. So this is just a very short, but this is not something you could do on a laptop, for example. Genomics, one of the key high-profile projects, and I always display this, is they had a 100-day Palm genomics project where they sequenced 100 different dates, types of dates, and they won an award for this. But they also managed to identify the gene, for example, that determines the color of the fruit, the date fruit, red versus yellow, for example. Social sciences, Andy Harris here is a faculty in political science, And he uses the HPC to analyze a lot of the data. For example, he looks at how people vote in Kenya, a country in East Africa, in terms of how do they decide on a candidate, from the name, from the facial features. So this is because they don't know, there's not a lot of communication. So they just look at a picture, they look at the name and decide on who to vote for. So he's trying to correlate between that and who actually gets voted. And then we have some of the research that we actually, members of my team, collaborate on. So Benoit has been working with the genomics group in speeding up the calculations during COVID, trying to identify certain features of the COVID virus. And of course, people needed to know this very, very quickly to develop a vaccine, to understand this virus. So, you know, something that could have taken months or years to calculate, managed to do it in a very short period of time. So we worked very closely with that group. Another one, our data scientist, I apologize for the size. Karuna Kara is our data scientist, has been working with Kansang Lee in social sciences, and they have multiple posters out. This is one of them. How am I doing for time? 1 more minute. Okay, quickly, we'll go through the other services that we do. So not everything can run on HPC. So we have developed services outside HPC to support all computational and data-related services. And these are the general categories. So someone comes to me and says, look, I have a laptop, and I have a lot of research that I need to do. It's not HPC kind of research. It doesn't run on Linux, or I need it to be interactive, or it's very low on performance requirements, but I have a lot of it. So we then look at what can we do. They could go to the cloud, or we could create our own cloud. And this is what we did. We give them a virtual machine, for example. They can do whatever they want with it. If they need more, we expand it. If they're done with it, we dissolve it and give it to someone else. So this is the kind of things we do. Some people have funding to buy their own machines, but they don't want to manage it. Nobody wants to stick a big server under the desk. So we host it in the data center. We can manage it for them, create accounts, install applications, support their application development outside the HPC, and so on. Even experimental setups, labs, things like genomics, we set up the pipeline for them. Sequencer to HPC and the whole pipeline for the applications, the analysis. The same for fMRI and so on. Additionally, we have created these new services related to data science. Now, this is, as I said, most people now have a large amount of data and they don't know how to analyze it, how to get information. So we are collaborating with them, but also we can provide this and help them, guide them, give them the right tools and so on. So internally, we have invested in a hyperconverged infrastructure. So basically a bunch of nodes that are running VMware that we can give out a virtual machine. We can virtualize GPUs. We have GPUs in them. Some of them we are using vCenter, vSphere, vSAN, so storage as well, a little bit. But the focus here also is on containers, and we manage that through Ranch. The data science services I talked about in general, we focus, a lot of people focus on data analytics, but sometimes they need help with data visualization, AI, implementing AI in their code, dealing with large quantities of data. Now, one of the popular things is people have a lot of data from Twitter, for example. It's a website, but they don't know how to extract that. So we can help them with extraction of this volume of and databases with data management. Yeah, so that's again more detail. And so, yeah, we do it through support and consulting. We also help with, we can do it through collaboration and different work on different projects with designing and implementing the analysis pipelines, working with prototypes of research-focused software tools as well. And that's it from me. Thank you very much.
Thank you, Mr. Matal, for that presentation. With the latest increased interest in AI, think Apple University of Science has adopted strategy to provide the necessary tools and support for AI research. In the coming keynote session, an overview of how high-performance computing and AI infrastructure, services, and applications in AI. So please welcome our second keynote speaker, Dr. Jason Lee, Director of Research Computing for Labs at Aws.
So first of all, I want to thank the organizer for the invitation, and also I want to congratulate the organizer for the organizing wonderful conference. When I organized this event 5 years ago, and I know what kind of effort you have to put in to make this happen. So I hope you, after this conference, you can have a short break that we all need. So I want to give a kind of overview of my operation instead of providing HPC and AI services at Aws. So let me start with a couple of small machines that I have. So our flagship machine is the Shaheen 2 supercomputer. This is a Cray X640 machine with an impact performance of 5.5 petaflops. And this is powered by roughly 200,000 Intel Haswell cores. This is one of the largest all CPU machine even now. And that's by design. We want a system that is very easy to use. And that strategy has paid off. And now I believe number of faculty using the Shaheen is 109 in my last count. That's roughly half of the Aws faculty. So as you can imagine, that's very unusually large fraction of computational science activities. Actually, I believe that Shaheen has been acting as a magnet to attract really excellent faculties and also even encourage the computational science activities in the campus. So then we also have IBEX cluster. So this is heterogeneous cluster and built and maintained by my team. So there's no vendor. Of course, I mean, we have a vendor that supplies the part, but my team is actually to build one. And it's roughly 10% of the Shaheen. And you might wonder why you need IBEX if you have a Shaheen. And I say software and hardware and operation. There are workloads that either doesn't fit in Shaheen or Shaheen is not the best place to fit in. So for example, let's say bioinformatics workflow. I mean, these workflows consume one core, but it can run few days. That's not a good fit for the Shaheen. And also there are these data that has to be generated from the sequence machine and electron microscope that has to be processed. Nowadays, I mean, if you look at the data generated from the one sequence machine, it's order of terabyte per day, right? And you need a pretty powerful computer to do that. And that's how the IBEX came in handy. And one other aspect is that because of we have kind of different way of upgrading the system. For the case of Shaheen, because we have to maintain the heterogeneity, we have to maintain homogeneity. We have to upgrade roughly every 6 to 7 years. It used to be 5 to 6 years, but I get roughly 6 to 7 years. But IBEX is like yearly refresh and similar to the operation in the NYU. So when the one problem we had was that when Shaheen was introduced in 2015, AI was not much a big issue. I mean, there are some AI activities, but it was not significant. But I guess that's probably here too is no longer the case. I mean, AI is one of the major activities on campus. And we have to find a way to support it. And GPU is like one of the hardware they are demanding. And IBEX provide a way of supplying these resources on-prem. It's the most economical and efficient way of supporting these resources. So I feel that, I mean, by responding to the whole demand from the house community, using this duo of the Shaheen and Ibex, I find this is the most efficient way of responding to resources, the request. And the one problem is that, I mean, out of this duo, Ibex is being refreshed every year, so it's always young in some sense, but not Shaheen. Shaheen was introduced in 2015, so it's the time to think about the next machine, and that's Shaheen 3. So, well, I mean, I admit that I don't have too much imagination. After Shaheen 2, it's a Shaheen 3. That's the name of the new machine. And it starts from the design point is we start to, okay, we are trying to say the difference from the Shaheen 2 is that we have to accommodate different workload. So what I meant is that, of course, we have to accommodate everything runs on Shaheen. That's kind of, we call traditional HPC workload. But also we have to accommodate AI workload too, right? But also what we envision is that besides these two, there are more increasing trend of the hybrid workload. Even in one application, they use both AI and HPC at the same time. So to make that happen, what we eventually decide to go for a single unified system with a modular architecture and CPU partition and GPU partition, but also not only the hardware, but in terms of accessing these resources, we feel that we need a departure, we need more way of user accessing the system than scheduling. So that was a kind of design consideration. And the performance requirements come from the users. So we had surveys and also we had one-on-one interview with our users. And the emphasis on real application performance, I mean, I care less about performance by the synthetic benchmark. I care more about how my faculties are impacting their science, how to do their science to make their science do better, faster with the computer machine. So that's the whole thing. So the performance on the CPU and GPU partition, the requirements gathered through the process and for storage and or the internet. And I'm happy to announce that, okay, we made a selection. I think maybe some of you have seen the announcement that sent out a couple of days ago. So it's a Crane, HPE Crane. I still don't know whether it's just HPE system or HP/Crane system. That's what it is, HPE Crane EX system. And it has a CPU partition and GPU partition. And CPU partition is really more than 4,600 nodes, and each node has a two AMD Genoa CPUs there. And the GPU partition is more than 700 nodes, and each one has a 4 Grace Hopper multi-chip. So that's the, I mean, if you do the math, that's a huge amount of computing power. It's available. And storage is the one that we are putting around 80 petabytes of storage. Divided into the storage and project storage. And of course, the interconnect is a slingshot, and the whole system is liquid cooled. And this system will be operational in next year. Okay, so I think this was the kind of procurement of the Shaheen 3 was good chance for us to look back how the Shaheen 2 has been utilized. So this is some of the numbers we gave. Over the lifetime of the Shaheen 2, we delivered around 7 billion hours. That's actually a lot. And we supported about 1,500 users. And I believe the last count was that we have 1,208 papers came out so far, hopefully more. And in terms of the areas, as you can see, we really support all the diverse areas. I mean, there are some areas that is more heavy using the system, but it's pretty much all over the place. And also we checked whether we are using the system as intended. So I don't want a situation that we buy a Ferrari, but using like a Toyota or a Hyundai. You know what I'm saying, right? So the breakdown is shown is that how many cores the job requires for a given time. So we don't want a system that we want this huge machine, but actually is the collection of the PC. That's not, we don't want that to happen. So when we do the analysis, I'm kind of happy is that jobs that use more than 1,000 cores, that's pretty HPC scale job. It's about 2/3 of the jobs. And the jobs that requires really extreme machine is like 16,000 cores, and that's 25%. So we kind of did benchmark for like DOE or NSF facility, and we are kind of comfortable with these numbers. So that was kind of added justification, I mean, for the Shaheen 3. And the IBEX was the other view, and the GPU portion was, as you can see, that it's basically AI. So that, I mean, that's the kind of in some sense we are having at this point, is that the demand on AI is growing so fast, and it was just not. We are still kind of trying to catch up with the demand, and with the Shaheen 3, I think that problem is solved. But I mean, there's a huge demand on the Windows side. So how do I run time?
Yeah, 3 more minutes.
Okay, so all right. So that's all about the system, and I want to just focus on 2 things. Like, so the Shaheen is, of course, this is the asset of the house, right? But we feel that there is asset of the kingdom too. So of course we have to accommodate all the need from the cloud side, but we are trying our best to accommodate need from the kingdom. So this is one couple of example. Is that one example is that we have wonderful collaboration going with Aramco for a few years so far, and this is one example of the seismic, reservoir simulation. The Ali Debru that he was able to prove that his concept for the TerraPower, and before he asked for money to the CEO of Aramco. But also we did work together on the seismic side, on the Excel wave, and also for the downstream research in the reservoir simulation. So in that sense, like I see that in parallel with in the US, there's a DOE supercomputing centers, and they are kind of acting as a complementary resource to the industry. And I feel that we are doing this kind of similar role to the Aramco. And so just another example is that we have to find out the other entities that now is it used to be now it's NCM, National Center for Meteorology. And what we're trying to do is that we are trying to help them to provide resources to have a better forecast for the kingdom. It's not only weather, but also like climate conditions and so on. And also we have helped them to procure their own resources. I mean, we are trying to help them to do whatever needed from their side. I mean, we are not, I mean, the goal of all this effort is not trying to make money out of that. We don't care about that. We're just trying to make an impact. So not only just, we don't want them to be too depending on our resources. We don't want them to have their own possibilities too. So not only for their providing resources, but we have to help them to procure research. And the one aspect came out there is, I mean, you see this system, there's a huge system, right? But the equally important part of the whole ecosystem is people. And that is unfortunately, this is widely underappreciated. I mean, if you just think about like how much money you are going to spend hardware and how much for people you are going to spend people, there has to be some kind of balance. But I feel there's a little more about the bias to their hardware. And this is kind of thing that my staff helps. So in building all the ecosystem, of course, we need people like David who use these wonderful facilities to just do a WordPress research. I mean, that's like part of ecosystem. but we need the people kind of enable the scientists to do what they can do, right? And that's the role of my people, my team. And there are, I guess you have seen some members of my team giving a presentation and just doing a posters, and they are good looking too. So, and they're going to stay here. So just please to talk to my team. And so there, we did one more thing on this is an interesting activities on the data science part is that there was an effort from we worked with the Saudi electricity company, and there's an effort to try to enhance the efficiency. And we work with them to build a prototype for the anomaly detection. And that's a potential to save, that's not our money, that's not our estimate, about 70 million SAR every year. So that was kind of another way of, not by resource, but by expertise of our staff to help in the kingdom. Right, I think that's roughly my story. And so there are a few events that's going on being supported by my staff. So there will be a workshop. It's going to be tomorrow. That is, if I don't show this slide, my staff will kill me. So there's a data science workshop that we are organizing, and also actually not in next week we are organizing this NVIDIA workshop. So this has been a wonderful story that initially this has been going on like 7 to 8 years, and initially like one event. Now it's 1 week event, and with the help from the NVIDIA, I mean JJ is there, I mean for just giving all the support and the building all the expertise. And as I mentioned, is that we have to invest in people, not only hardware, right? So that's the part that we are trying to play our role. Okay, thank you for listening.
Thank you for your experience with time. Now, please welcome our first speaker, Mr. Ecology. Environment development management at Hewlett Packard Enterprise. Will cover 2 topics. Today, about developing software environments for high performance for supercomputing. The second topic will be supercomputing for the exascale computing.
Thank you for the introduction. And I think I can quickly solve the branding strategy from HP in the sense that Cray is the supercomputing division of HP. Right, so it's our team and solutions focused for the supercomputing market. So talking about supercomputing, our design, our approach in both AI and HPC is focused on 2 key criteria: efficiency and scalability. Efficiency is not just a matter of performance per watt, power performance. It's also about the environment, the software tools that you can use in order to really exploit the resources that you have on the infrastructure layer. So what I'm going to talk about is one of the efforts that we are making in terms of delivering a software environment that can easily, or let's say that enables users to run at scale their problems. In particular, I'm going to address the machine learning development environment, which is the software tool that comes out of the acquisition we made last year of the Determined AI software, which is an environment that is intended to facilitate training at scale for AI developers. So we all know a very common problem. Teams, researchers, they start with small problems. Maybe it's one person starting with playing and working with AI frameworks. And then, I mean, the experiments are small. There is not that much to work on. Actually, most of the developers, they start from their own workstations. Then they don't even need to share any resources. Access to data is pretty simple because the data is local and so on. very soon, as the research becomes more complex, you end up into several challenges. So first of all, the access to the resources, right? As it was mentioned before by Dr. Lee, users at Chaos, they are growing their demand of GPU utilization. So you have a contention of resources, and this is the very first problem you face easily as soon as you go in your AI journey. You have other elements like the hyperparameter optimization, having proper snapshots of your training activities, do the proper experiment tracking. As soon as you start having this multiplied by many users on several resources, and then you have different frameworks, different environments that your users work on, then this creates a significant complication. So, oops, yeah, okay. So our solution to this problem is this software environment that we call, as I said, with just a little bit of a long name, the machine learning development environment, which is an open source tool. So it's available without any lock-in for download, developed by HP. This tool is intended to solve exactly those problems. So to reduce costs for development of training at scale. So we have seen this applied to many cases. We have customers running on thousands of GPUs that have been able to significantly reduce their time to development. What it provides is that it gives you distributed training, first of all, and the training is almost linear, as I said, to thousands of GPUs. It provides an environment for hyperparameter optimization, and it does allow you to scale on multiple GPUs with very minimal intervention. It allows the developers to focus on being data scientists, not HPC experts, which is one of the other aspects typical of the AI world. AI developers, they are not HPC people usually. So how does it work? As I said, the focus is on the training aspects. So you need to have your pre-processing, data preparation pipeline, and you can have data sources that will go from HDFS to Spark and Pachyderm and so on. Then the environment that you have, which is pictured here at the center, does give you a layer underneath that enables the sharing of the cluster resources. And you can have different GPU targets underneath. This software works in the cloud as well. So for instance, it supports also tensor processors in the Google Cloud. Then you have distributed training, experiment tracking, hyperparameter search and optimization. You have also NAS features enabled in there, debugging. So it's your front end and your environment for focusing on how to optimize your training. Then obviously you need then the next step, which is the model deployment, and when you put that in production, and there are several solutions in there from MLflow to Selenium and so on. So this is in a nutshell. There will be a workshop tomorrow from one of my colleagues specifically to deep dive into the features of this environment. But this is in a nutshell what the HP machine learning development environment provides. So it's intended to address AI workloads, and in that sense, you have what HP provides is this software, and this software is open source and freely available. Obviously, we provide also support on this specific software. We do provide, along with the software, we provide turnkey solutions. So we provide a machine learning development system, so a system that comes with that software as well, standardized with benchmarks and so on. There is another interesting element talking about the convergence of HPC and AI, we have been focusing, and this is one of our key focuses, as it was emerging very well from the previous presentation, to enable the convergence of HPC and AI. And so this software does support the integration with Learn, for instance. So you can have on the same system users that are submitting jobs in a traditional HPC batch mode and users that work in the MLE environment with their own front end and their own tools. So it does enable possibility to run the two different types of workloads together, so traditional simulation and AI. Before switching to the supercomputing solution, there is also another, I think, quite important element, which is the fact that this is not the only software tool that we've been working on. This is a series of applications and I would say better tools that we are developing and that we have been developing in order to facilitate this convergence. I just want to name one, which is available and is an environment which is open source as well, which is called SmartSim. It comes out also from Cray Research that enables the utilization of AI in traditional simulation. And you will hear about this tool pretty soon much more. So then moving into our supercomputing solutions. Let's say this is an interesting year, and very happy also to be here. As you heard, HP has been awarded for Shine 3. But let's say this comes out of our continuous investments into HPC. So we have acquired Cray. Before Cray, we have acquired SGI, and before that, HP has been working in HPC for 30 years. So we have an industry leadership that keeps us on the first place by a long distance, and we have more resources than any other company deployed in HPC development and support. So this brings in several innovations. I was just mentioning about the software tools. This is obviously only a part of the story. But when we speak about exascale, our interpretation is that exascale is not just a number to hit, but it's about integrating traditional modeling and simulation with artificial intelligence and with big data analytics. Exascale is all about this. And it seems like this has been pretty successful in the sense that we have won and deployed the most powerful supercomputing systems in the world. And we're proud also to say that we have deployed these systems with different architectures. So we have experience in working with basically all the HPC architectures available in the market. And obviously, the top one is Frontier, the R as for the second line. So Frontier has been the first system in June to break the exaflop barrier. Just to have an idea about Frontier is faster than the other 7 systems underneath. And then if you consider the other systems after the 8 is 68 times faster than the other ones, and then going down almost 400 times faster than the other. So it's a step up, significant step up in terms of performance. And some interesting numbers. It's not only the first system in the top 500. It's also the greenest system, which for a system that consumes around 40 megawatts of power is a quite interesting approach. But so exascale wouldn't be possible without megawatts in place. So another element that is interesting about Frontier, apart from the technology used, it runs on EPIC CPUs, AMD CPUs and GPUs. It has almost 40,000 GPUs. out of a single system. It does use HP slingshot interconnect, but there is another element that I find particularly interesting, and in my opinion, not enough highlighted. The fact that there is 700 petabytes of storage, of cluster storage. Actually, that speed of 5 terabytes per second will turn into 35 petabytes per second going forward. So we are talking about a system, a storage system that is capable of responding to the massive amount of data movements that a solution like this requires. And as we know today, compute is relatively easy. Handling data is extremely complex. We are talking about a system that is capable of, I don't remember how many billions of IOPS. So you can imagine with all those clients what that means. So this is frontier. But as it was mentioned earlier, we're also quite proud of having achieved the award of Shane 3, which is an extremely interesting system for multiple reasons. One, well, it's a great system, so that's one reason. But apart from this, it does leverage all the new technologies that we've been working on. And in particular, I look forward to the integration of HPC and AI workloads on this machine, because we have we do believe that the path to exascale comes from a deep integration of all these elements. This system is a combination, as you can see from, and you can see also earlier, the CPU portion is based on AMD, and on the GPU portion, it does utilize a Grace Hopper architecture, which is also a quite innovative approach, having an ARM plus GPU solution there. So that's let's say my quick overview. Just want to give you a glimpse of what we're working on and how we focus on providing an entire environment that goes from the best of breed in terms of hardware infrastructure, but it also provides the software tools and the software environment that are needed to efficiently utilize these systems. And with this, thank you.
Thank you, Mr. Rdma, for the presentation. Our next presentation will give an overview of some of the reports to optimize the time of critical with large data. Please welcome our first speaker, Mr. Project Engineering System Analyst at Algebra.
Hello everyone. It was really great to see the advancements in the hardware in the previous presentations. But allow me to give you, or to take you one level above at the application layer, and to present one of our key optimizations inside the ARM code to fully capitalize on the hardware. During this presentation, I will highlight our innovative approach to monitor, evaluate, and optimize the reservoir simulation numerical solver tolerances in real time to optimize the simulation runtime. Now, due to the time constraints, I refrained from going into the reservoir engineering and reservoir simulation aspects of the solution. But if you are interested, I'm more than happy to explain to you after this session. But during this presentation, I will give you a quick overview of the reservoir simulation. Then I will move into the simulation time slipping concept. And after that, I will detail two major issues we face in reservoir simulation, which are the slow convergence and the numerical rules. Finally, I will go into the model fine-tuning and our solution and the results we got. Starting with the reservoir simulation, it's an area of reservoir engineering in which a 3D model of the reservoir is created and used to predict the fluid flow inside the reservoir, typically oil, water, and gas, which aids in developing and effectively managing oil and gas fields. Reservoir simulation is a main technology used to conduct many processes such as field development, production strategy evaluation, business plans assessment, uncertainty quantification, and running numerous what-if scenarios. Now, Saudi Aramco's reservoir simulation numerical solver is a finite difference solver. These simulation models are discretized in the form of grid cells, and fluid flow equations are solved for each grid cell in a series of temporal steps, which we refer to as time steps. And to illustrate that, this schematics shows a simulation model timeline. The start of the simulation is January 1990, and the end date is October of the same year, where the simulator would take leaps in times progressively from the starting date to the end date. As you can see in the light green lines, those are the time steps, the size of the time steps, and the number of time steps the simulator took. The size and the number of the time steps directly affects the simulation runtime. And to illustrate that, let's see these scenarios, where in the upper scenario, the time step size is ideal, which is 30 days, and that will give us a total of 9 time steps. But in the other two scenarios, the time stepping is taking another scheme, where it will have more time steps with varying sizes due to the solver convergence, which is heavily impacted and influenced by the reservoir model complexity. Those complexities could be the reservoir properties, the number, the types of wells, the fluid properties, and much more. As you can see, the unnecessarily small and many time step sizes resulted in having very large runtime. As we can see in the last case, where it took 4.5 hours instead of 1 hour, which is not ideal in our situation. This is what I mean by slow convergence, and this is one of the major issues we face in reservoir simulation. Now, allow me to illustrate the other issue we face, which is the numerical wall, where the run starts normally, as we can see, up until July, which it's ideal and didn't face big obstacles, and the slope of time looks normal. But in July, the simulation model started facing convergence issue due to a sudden production increase in that month, which causes numerical instability, where the simulator has to reduce the time step size over and over again to address the convergence issue. As you can see, the slope of time looks like a wall, and that is what I mean by a numerical wall, where the simulator gets tangled in small time step sizes. It will converge in a matter of days or weeks instead of hours. And to address the numerical walls and the slow convergence, a few years back, we used to manually fine-tune the tolerances, which is very tedious. It is time-consuming, it requires much more resources, and lots of computational resources will be wasted due to the manual attempts. Also, it is model-specific and cannot be generalized to other reservoir models. But the approach we developed fully automates the diagnostic and fine-tuning process. The diagnostic and fine-tuning process will now happen in real time, which will eliminate all the manual attempts and the unnecessary runs. This way, this approach will avail more capacity, reduce the manual attempts, and avail more computational resources for more studies. Now, let me illustrate the solution. This is the same example from before, where the run got into a wall in July. But this time, the auto-tuning agent will detect and update the tolerances to address this instability. Also, while the simulation is ongoing, the agent will keep monitoring the run, and once it sees slow convergence, it will intervene, analyze the run, and if it's stable, it will increase the time step size. In this, as we can see in this example, where it increased it, and that caused the run to finish smoothly. We have tested this approach in several simulation models that represent different fields. As you can see, our agent has detected the slowness and auto-corrected the tolerances. which resulted in having faster runtime. And furthermore, the agent was able to match the manual tuning of the tolerances, which in result will eliminate all the manual attempts. This auto-tuning approach helped us in reducing the runtime by up to 60%. In addition, engineers don't have to worry about what solver tolerances they'll have to use, since our agent will automatically set the optimum tolerances during runtime. And simulation support rarely have to intervene, since our agent will automatically optimize the runs. And this solution will automatically monitor the runs and will alert us every slow run. This will save lots of time and efforts for the simulation engineers and the simulation support. This concludes my presentation. Thank you.
Now we move to the last talk in the first part of the session. The talk is about the technology that AMD is developing to support accelerated HPC and AI skills. Please welcome Mr. Mohammed Jawu, Senior Field Application Engineer for AMD Middle East Canada.
Assalamu alaikum, everyone. Good afternoon. So we've had lots of discussions that happened about the research centers, the HPC solutions, the great simulations and innovations that everyone has had during this conference. Mine is a bit different, so bear with me on that. So we go a little bit deeper into the solutions. So to start with, of course, computational sciences has been more and more important every day, right? I mean, and that's why we are here today. We're here to discuss how we can make things better, especially the amount of data that we have and how do you want to make sense out of all of this. Now, with the technologies, if we continued with the rate of technologies that used to be, then we would not have reached the exascale era, right? And we've had different conversations about the exascale. Everyone wants to be there. But with the new technologies that's there in the market, we were able to bring this one earlier in time. And right now we had it, as HPE was talking about it. But this comes with challenges. I mean, nothing is easy. So those challenges come from different factors. So the first factor was Moore's law. Everyone is aware that Moore's law is slowing down, and that's one factor. Now, on the other hand, that brings us also into the manufacturing process, and that comes with the yield of the cost per yield of per millimeter of the CPU or the die. And we can see with the graph that we there that is increasing exponentially, especially when we move from 14 nanometer manufacturing process to the 7 and 5 nanometer process. The other challenge is the size of the die, and what we call the theoretical limit, which is how much capacity do we have on the processor. And around right now, it's around 800 millimeters square. We can see that the server CPUs and the GPUs are also expanding in size radically, as you can see in that graph in the blue and the red dots of it. Power consumption, and I think that's everyone's concern nowadays. So power is not cheap. Power, we need to be more sustainable. The solutions has to be with a specific limit. But that's increasing drastically as well. So on the last top 100 supercomputers within 2009, 2019, we have seen an exponential increase in terms of power consumption. On average, it was around 1 megawatt, but right now we're talking about 10 megawatts. So how do you see the future of computing? That demand will keep on happening. Those things that we've seen about the demand, the die size, the power consumptions, and the technologies that we have is going to keep on increasing. And there is also a requirement to have more high efficiency domain specific accelerators, as we can see. So there was a CPU plus GPU solutions, and other solutions that might come in for specific uses. From a chip manufacturing process, we looked into one of the solutions to help in supporting those challenges that we have and to look into the future of computing, which is a modular design. So, and of course, I mean, probably everyone have heard of the word chiplet, and that's what AMD is famous for. What this chart shows, it shows the difference between a monolithic architecture, which is on top, and the chiplet design, which is below. The benefit of having a chiplet design is, as you can see here, is that the die size can be smaller, but making it smaller does not only mean that the size itself is smaller, but also we have a better yield. Because with a monolithic design, as you can see on top, you get less number of chipsets or dies once the testing has been done, and that will lead into the same number of processors. If we move to a chiplet design, as you can see below, we have a better yield, which means we have more amount of dies that can be used in the end product, and those can be used towards multiple CPUs because we can put them, have different functions on the same processor. To do that is not only about gluing things around. We have to think of how do we need to put those processors into a single package. And this is how the package development has happened. So in 2015, we started thinking of this idea of having multiple chips on a single package. And that started with the HBM technologies, the GPUs that we had. That uses what we call the 2.5D packaging technology that used something called the silicon interposer. You can think of it as a passive layer in between the chipsets and the PCB board, and everything connects through it. Now, moving on, we moved to a multi-chip module. So we use the same technology to the first generation of EPIC, and that was mentioned, which is Naples, where we have multiple chipsets. Each of those chipsets does all the functions: memory controllers, PCIe, and of course the infinity band connections. What was mentioned today? So we have heard about Jubail, for example, which is running Rome. We have heard about Shaheen, which is running Genoa. So all of them use the latest technology in package. And that's what we see that came in 2019 with Rome, Milan, and Genoa, that we will have the different way of putting in the chipsets. So we'll have different type of dies. Some of them are the core dies, which are the smaller ones. But in addition to that, we also have a bigger die. So that's a combination of both, which contains only the functions itself that support the cores. And those functions can be either a PCIe adapter, PCIe controller, memory controllers, or even a secure processor that looks into security. And that shows you how the functionality and how flexible this sort of a design is. Well, that helped in a lot of the challenges that we've seen in terms of power consumption, in terms of the die size, and in terms of the cost itself, because we had better yield. But there was another issue as well. I mean, which is probably you've heard about Von Neumann. So Von Neumann is the designer of the basic architecture and any processor that we have it right now. But there's a bottleneck, and that bottleneck comes between how do we read from the physical memory towards the CPU and the number of cycles that sits idle with because of the way it reads and fetches the instructions, and also because of the speed of the bus that we have between the CPU and the memory. The solution for that is mainly, as a startup, was the cache, and L1, L2, L3 cache, because this is a closer memory towards the CPU, and you can fetch data easily. So when you're talking about a cache, talk about probably 8 nanoseconds to read the data from, which can go to like 10 to 100 times to read from the memory. Now, the idea from AMD that we have a great architecture, and we have this die that we can do multiple chipsets in it. So initially, the base, which we have, has a 30 megabytes of free cache on a single die, and we have 8 of those, which means that it gives you 256 megabytes of cache. But some applications requires more L3 cache to be more progressive. And that's why we thought of an idea. How about we put another layer of cache on top of it? And that's what we see above, which is an additional 64 megabytes of L3 cache, which we use a technology called hybrid bonding to create a 3DV cache. In silicon, it's not a matter of gluing things around, right? You cannot just bring the super glue and put things on top of each other. So that's why we had to come up with a new innovation to see how we can put that L3 cache on top of the die and make sure that it's efficient. We reduce the latencies, and we make sure that it's seamless for the end user or for the application when using this L3 cache. Those are the traditional technologies that use to bond or to put chipsets on top of each other. So the first one is the traditional one, which is called a flip chip or a C4, just traditionally putting chipsets together. What we can see is the connectors here in gray. There was another technology which was called a micro 3D, which is also used to bond chipsets on top of each other. But the micro 3D has less number of connections that we see in blue compared to the technology that we use right now. So you can see the density of connectors that we have there in orange compared to the blue ones, which is around 12,000 wires per millimeter square compared to around, I think it was 5,700 wires per millimeter square. And that density in connectivity means that it's seamless for you to use that additional L3 cache on top of the existing chipset. Another advantage by using that way of bonding is that we kept the die, the processor packaging as is, right? I mean, the size of the processor stayed the same. So for example, Roma and Milan stay the same size. This is the ones with the additional cache is called Milan X, which is another generation, has also used the same size. So it was like a matter of you need to use it, just swap your CPUs and you can use that one. No additional power consumption, no additional connectivity, no additional requirement. And what that 3dV cache gave us in different analysis, when we look at, for example, fluid dynamics, or we look at FBA, we have seen a great improvement in those use cases. So this is not for, I mean, as was mentioned, it's not a one size fits all, right? I mean, you have different applications with variety of technologies. So this additional Bcache technology can be used for those use cases and other use cases to get you the improvements. And I think hopefully I'm on time, so I'll try to make it quick. That concludes everything, but if you need any further details, I'll be around, and hopefully it was short and crisp. Thank you very much.
Thank you. Now we've reached the end of the first part of the session. I will have the speakers don't participate for the session at the disposition. I will start with the question that they have. The first question for Mr. Ramataz. Several cloud vendors have recently established HPC services in Kuwait. How do you see academia of on-prem HPC versus cloud landscape change?
It will change for smaller institutions. So smaller universities that may not have the budget to implement their own on-prem HPC could make use of it. For those of us who are heavy HPC users, most likely would prefer to have an on-prem because of the cost implications. But also some universities have issues with space, for example, from a hosting perspective, they don't have a space to host their own HPC. Cloud may be a cheaper option.
Question for Mr. Edmondo or Loki. What is the impact of large language models in society?
Talking about implementations, large language models represent probably the most disruptive technology that is being introduced in this decade. I'm quite straight on this. I believe they're going to change significantly the way that, obviously, the way that we interact with machines, but they're going to affect heavily also the way that we run research as well.
Mr. Obey, you have talked in your presentation about time steps. The time step side of perspectives.
Yes, in general, the smaller the time step, better the accuracy, but there's the trade-off between the runtime and the accuracy. More accuracy results will take way much time. So that depends on the engineering of the one section.
Another question from Mr. Mohammed Jabu. Do you consider 3D Bcache technology-based processor replacement for accelerators?
Not necessarily. So, as I mentioned, so it's not one size fits all. You see that through different use cases that accessors will still exist, but the 3D Bcache technology will help to put different use cases into a better performance depending on the requirements for that.
Is there any live question from the audience? Yes, so can you
Hi, okay. Do you think you can take advantage of the hybrid storage thanks to the new agents that you have in your application. Sorry for the routine question.
Yeah. But we can try and hopefully we can sit an experiment, but for this agent, really this on the front time. It will not affect really the non-usage any other thing. So you can try. I highly doubt it will be running.
This is Dr. Aws Batch from KPPM. I have a question for Dr. Disugi. First of all, congratulations for Shine 3. I hope it will fly high. You mentioned it will be launched in 2023. Start and or is it too difficult to answer?
Yeah, at this point in the second half. So of course there are, as we all know, we have all the challenges, supply and demand, so on. But yeah, just that the second half.
Hello, my name is Siva. I have a question for Dr. Jaisi. What is your perspective on using AI in sustainability, especially for Ocean?
I didn't listen to the last part. Using AI for
In sustainability for Ocean, using the computer, the supercomputer.
I think the prospect is actually pretty high, and even where we are now at cost. So there are faculties like always modeling stuff is kind of traditional HPC domain. But kind of one trend is going on is that they have to solve all these differential equations, which is very expensive to do. But they are trying to replace some of that with deep learning models. And so even now there are efforts that's going on in that house that try to substitute that to one. I think that's probably like short term, but in the longer term, with all the data and with the capabilities, I think that the data mining aspect will be pretty huge.
I read in your website, customer page, that you're open for collaborations. But we're trying to contact you, but we're not getting any. We're not getting any response.
I don't know which. So okay. So this one's for everyone because we provide also try to help this kingdom. So so my operation is to provide services. So in that respect, I mean, if you contact anybody from my team, actually Bilal Hadri is one expert for the contact point, but then anybody receiving regarding the support and the services will respond. But if you want to like collaborate with the faculty, I mean, I don't have control over the Navy, right? So I mean, I think I can help you. I can try to connect the faculty. But I mean, if you are thinking about collaboration, not in my operation with the services, but with the faculty of science matter, it probably is faster that you can just directly contact the faculty. So I mean, so depending on which kind of collaboration you're looking for, there are different contact points. I mean, House is one university, is one entity, but I mean, but within House we have many departments, right? So in that respect, I mean, anything about service here, I will handle it. But about the science collaboration, that we can always try to help you, but probably just go to the individual faculty.
Thank you. So right now we have reached the end of this discussion. Thank you. The second part of the session.
We move to the second part of the session. Our next speaker will talk about the concept of HPC and we dive into the convention of HPC and AI. Please welcome Mr. Balamorgan Ramasamy, the Director of HPC and Cloud Solution at Algebra.
Thank you so much for the invite. It's a great pleasure to be here. And I was here for most part of the presentations, and it was fantastic. So we spoke about the CPUs, we spoke about system design, we spoke about securities, we spoke about accelerators, we spoke about operations, and probably all of my friends here left resource management and the workload management to us at there, and I believe we do it the best in the industry. My 10 minutes is going to be largely on how we should look at workloads today in the contemporary world, and how to design the resource management policies and structure the system design in such a way that we avoid unnecessary siloing of infrastructures and improve the return on investments on these systems. So for people who are getting introduced into HPC, you would by now probably have figured out, though these systems are powerful, you are not going to get a supercomputer for yourself. So it is always going to be time to share. Yeah, so that's how the world is, and it will remain that way for a very long time. So let's go ahead and before I start the presentation itself, I'll probably try and give an overview of Altair. Altair is a 37-year-old company. It is headquartered in Troy, Michigan. We are listed in NASDAQ. Okay. We have about 30,000 plus customers globally. It's a slightly dated slide. I believe I'm trying to update it, but it didn't make it to the final version of it. So yeah, so we have about 150 plus software titles. Our investments are around physical simulation softwares. My friend from A&B actually showed a benchmark that showed Altair radios. So it is an explicit solver, FEM solver that kind of helps you do crash analysis and stuff like that. So our investments are largely there. We do a lot of investments. Our software titles are also around data analytics and AI. And the third piece of our software titles are around high performance computing. So Altair is uniquely positioned in the convergence space of simulation, AI, and HPC. So when we speak about high performance computing, it is generally accepted to be okay to skew around the CPUs. So when we speak about resources, we always tend to speak about CPUs as resources. But as the CPUs become faster, as the CPUs become more powerful, it is also important for you to consider other aspects when you schedule your jobs, or when you make sure that your job runs at the optimal possible space, right? So what are the other possible resources that you can think of within the scope of high performance computing, or from the workload perspectives? As we saw, accelerators are becoming more prominent. It could be the GPUs, it could be the IPUs, or it could be FPGAs. All of these are accelerators that kind of give you multi-fold performance improvements on your workloads. Yeah. The other one is storage and probably network. So these are always shared commodity within the sense of HPC. So the network is a fabric that kind of binds all the compute nodes in the HPC system. So we are at about 10,000 plus nodes, or maybe millions of cores at this point in time. So we're going to see much bigger systems. And all of this is tied together by the network fabric. if you take a job today and you want to run on a subset of these nodes, by how these nodes are allocated within your HPC system, you can gain or lose 10% of your performance. So it is very important for you to understand how your processes are utilizing these resources available in this space. The other important factor is whether you have the right kind of storage. Do you use a parallel file system, distributed parallel file system? And do you use it in the right way? Do you have a sense of how much bandwidth your application is going to consume out of what capacity you have? Or is it the right time to co-locate another job with an IO-intensive job? It might be okay to kind of throttle the job throughputs on your cluster when you know that you're running an IO-intensive job. So we have done some work around this. There is a framework called Saga that I kind of work with Dell. And it has proved that, say, for example, it's not always like if there is enough number of CPUs available, just go ahead and run a few jobs. It is okay to kind of see from a holistic perspective and throttle your jobs when you know that you're constrained by other parameters that are kind of going to be the bottleneck. Yeah, so by the Saga framework kind of in the EDA space has proved that just by throttling the number of jobs, you can get 10x speed up on certain workloads. Yeah, so you're not adding any CPUs, the same infrastructure, but just by knowing when to run your jobs, you can get 10x more throughput. This is one aspect based on the resources, but there is another dimension. You also need to make sure that every engineer, new or an experienced one, gets the same amount of productivity from a HPC cluster. So the technology has to be really transparent. It should not have a large learning curve. The second aspect is probably there is cloud offerings available. We spoke about it a lot. They're on demand, okay? So, but then they necessarily need not have the same stack. So the users, even if they have access to resources, might not be able to kind of use them. The other area where we kind of are the experts is policy-based decision-making or scheduling, knowing when to run a job, where to run a job, and who should run a job matters a lot. Okay, so you cannot, as an administrator or a system manager, keep making these decisions for your users. So there should be an automated way of figuring out who qualifies to run and where. Finally, you need tools to monitor and optimize your operational means or policies on a regular basis, and your administrator needs mechanisms to put cost controls. If you're using chargeback mechanisms and stuff like that, you need ways to kind of understand your workloads and stuff like that. Yeah. Okay, so it was always the right resource to the right engineers at the right time. But the speakers before me have already made a point that it is not just the right engineer getting the right resource, but it is also the right workload getting the right resource. So that's what we're going to talk about in the next couple of slides. This is something that we've been working with some of our large customers for a very long time. What we are thinking here is, the PBS professional and their PBS professional being the global unified scheduler, and it can have resources from your on-prem cluster, or it could be cloud. Okay, we are cloud agnostic. We could work with AWS, Google, Oracle, Azure for that matter of fact. We work with smaller players or regional players like Huawei, Orange, or if you have an OpenStack based private cloud, we could burst to that. So the resources can come from anywhere. Okay, and on top, you could have any kind of workloads that are within the paradigm of technical computing. It could be MPI based jobs, it could be high throughput jobs, it could be big data jobs, it could be AI jobs. So AI and ML jobs are a little different in the stack that they would use. Okay, so we had Walid speaking about Kubernetes today. I did not vouch to take Kubernetes name so many times that he was too, but then it is imperative that you talk about AI and deep learning in today's context. You are going to be working with Kubernetes. So when you work with Kubernetes, it is also important to know that you will always have some level of containerization happening. All your workloads are going to be container workloads. So PBS Pro is capable of kind of running all of these workloads without you having to do anything more on the resource layer. So say, for example, if I want to run a deep learning workload, in terms of resources, it is going to probably run on a couple of nodes with 8 or 16 800 GPUs. Okay, so the user need not know from where the resources are being allocated. It could be on-prem, it could be from the same cluster where the HPC jobs are running because the infrastructure is exactly the same, or come from a cloud provider. Okay, so that's the whole idea. I had to kind of remove a couple of demonstrations that I had because of the limitation of the time here, but I'll be happy to talk to you about this. This is probably the last slide. I'm going to talk about in a technical sense. What we do here is an integration with Kubernetes, which means Kubernetes and PBS Pro coexist inside a HPC system. Kubernetes is a scheduler, as a scheduler. PBS Pro is a more, HPC style scheduler. Okay, so you cannot have two decision makers in the same room, or you cannot have two brains in the same room. So you have a split brain condition here. If you have 1,000 nodes and you want to run 800 nodes for the HPC MPI workloads, and you have 200 nodes where you want to run AI kind of workload, the only possibility that you have today is you split the cluster into 800 plus 200 nodes, and that is where you create a silo. What this framework allows you to do is to have the 200 nodes taken out of the traditional HPC cluster on the fly and given to Kubernetes when there is a pod that requires the resources. Okay, so there is absolutely no hard partitions being made. There's absolutely no silos being created. This is all on the fly. When the Kubernetes jobs are over, the resources are returned back to PBS, and you can run your traditional HPC workloads on the same cluster. So if you have been to KubeCon, or if you have listened to the KubeCon recordings that are available on the internet for this year or the last year, there is a lot of focus coming into batch jobs using Kubernetes that kind of vindicates our position that Kubernetes has use cases that requires batch processing. Okay, what we are not doing here is disrupting in any way how the users use Kubernetes on top. Okay, so ML flow or tensor serving or any other Helm charts, for that matter of fact, any upper layer abstractions that you're already using are still usable with this kind of an integration. I'll take less than a minute to kind of summarize. So if you see the central column, that is what is required by large HPC centers today. Okay, these are technologies that they need to keep their clusters at their top operational performances, and the same technologies are required for the on-prem cluster or on cloud. Okay, so I think kind of understands these requirements and have products specifically to address those challenges. And we use them internally. As one is a SaaS offering, software as a service offering for our simulation softwares. The same set of tools are being used there. So with whatever time I had, the only thing that I wanted you guys to remember is that if ever you think of job scheduling or resource management, think of it. Thank you very much for the time. Thank you.
Now we will move to our next topic that will provide an overview of HPC facilities at the university. Please welcome Dr. Brian Mosley. He is assistant professor at the University. He is the director for technical affairs of the high performance computing practice.
Thank you very much. Thank you all for coming in to listen to me. I'd like to first thank the organizers of this wonderful event. As mentioned, my name is Brian Mosley. I'm the Deputy Director of the High Performance Computing Center at Aws University. Aziz is the HPC that we have at KAU. We provide many services to our users, including, of course, HPC services, big data and AI services. Our facilities are currently being used not only by academics, but also by business and government organizations. We have both local and foreign partners that work in a large variety of fields, including physics, chemistry, biology, computer science, aeronautics, and climate change research. So this is just a small picture of Aziz, some of the services that we provide at the center. This is something we really pride ourselves in our flexibility when supporting our users. We are very flexible in terms of the support that we can provide. We provide hardware customizations as needed by the user, which includes Intel-based CPUs, general purpose GPUs, Intel Xeon Phi co-processors, and like the storage spaces that can range from just a few gigabytes to several terabytes. We also provide some software-based services where we help install all the required software needed to by our users to conduct their research and their experiments. We have already pre-installed software such as VASP, Quantum Espresso, Gaussian 9, and Newton-X. We also help our customers convert their sequential code to efficient parallel code and provide support in code optimization and performance tuning. So we help as well in education. So we offer our services and aid in setting and creating HPC curriculums. We provide materials for labs handouts, and we provide remote assistance to students and faculties. We try to help as much as we can, to help our users and researchers as much as we can to provide a seamless experience and to allow them to obtain the best results that they can. We annually we have a training program that we renew annually, which we train our users in topics such as MPI, OpenMP, CUDA, scheduling strategies, some performance evaluation techniques, and we also support in the compilation and the debugging of software. Some of the services we also provide is consultation and customization services to centers that are just starting out. We help in estimating, for example, the required computing power, the storage capacity for computationally intensive problems. We help design HPC clusters and assessment services. This is just like a small overview of the different services that we provide at Aziz HPC Center. So what makes Aziz Aziz? So I'll just give you a small overview of the different components that we have. So we have in total almost around 500 compute nodes, which hosts approximately 12,000 cores. Of those 500 nodes, we have 380 standard compute nodes, which has around 9,000 cores and 96 gigabytes of RAM. We also have 112 high memory computing nodes, which has 2,600 cores and around 256 gigabytes of memory. We also recently installed 20 new A100 GPUs to support AI research that is performed on the Aziz supercomputer. So some of these AI capabilities, we try to help our users in the full pipeline of AI research. If that is in terms of the analysis of visualization, and we support both in terms of traditional machine learning and deep learning. We already have a variety of different AI platforms readily available for our users, and if the software they need or the platforms they need are not available, then we can always work with them to get the tools they need installed. So let me just give you a small overview of the utilization of Aziz. So currently we have almost 300,000 jobs running each year, which comes to almost 85 million core hours per year in utilization, which comes around to about 80% of the available computing power. And in terms of storage utilization, we currently have 1.7 petabytes of data files, which comes around 85% of the available FEFS storage. In terms of users, our biggest user category comes from the physics department, and just the physics departments, they have around 40-30% utilization of the Aziz capabilities. We also have other users like the chemistry department, biology, the Center of Excellence for Climate Change Research, the aeronautics department. And some of our users are also outside of King Abdulaziz University, like, for example, our partners at Qasim University and the College of Arts and Sciences at Rabat. So in terms of publications, we have seen a steady increase of the number of published papers, dissertations that are relying and using Aziz. We since 2016, we saw an increase from 23 papers to over 100 papers and dissertations per year. And just to give you a sense of some of that research that occurred recently, some of our notable use cases in 2022, our first, and this is something that we're very proud of, we have a patent that was recently awarded to one of our users in molecular dynamic simulations and protein folding for anti-allergy research. And as well as the Center of Excellence in Genomic Medicine Research, which have been using the facilities at Aziz extensively for next generation sequencing research. Other notable uses that has been going on recently at Aziz is molecular dynamic simulations and protein foldings for studies that involve vaccine research for the Marburg virus, Ecology, and the SARS-CoV-2 virus. So that was just a quick tour of the Aziz Center, the Aziz HPCC Center. And I just want to thank you all for tuning in. And later on, if there's any questions, I'll be more than happy to answer. Thank you, everyone.
Now we're going to move to the to University, in Sweden, with high performance computing systems and application at the university. Please welcome Dr. Aws Batch.
Thank you very much. Greetings, everyone. So my name is Aws Batch. I recently joined KFUPM. Before I start, I would like to acknowledge Dr. Abdul Jabbar. In fact, he helped me a lot to put up this presentation. Previously, he has been presenting and representing us at Saudi HPC. So what I will talk about today is the HPC system we have and its current applications and our future demands. Food for thought for everyone, particularly so the audience. I bear a good news for the session too. I'll be very brief. So that is good. Now, so at KFUPM, we have two clusters. One is ICTC K20, which is for everyone. And one is Al-Fahad. This is for Center for Petroleum and Geosciences. They have a dedicated cluster. So first talk about K20, that is ICTC for everyone. We have traditionally one node to connect in and then 32 nodes for simulation. In total, we have 660 cores. Considering what we have seen for Shaheen 2 and the foreseen Shaheen 3, this is just nothing. For Al-Fahad, they have 2 nodes to connect in and 180 nodes with a total of 3,304 cores to perform computation. Time to time, they allow other departments to perform their computations, but they have the large resources as far as KFUPM is concerned. Now, to compare, if we have Al-Fahad here and our ICTC HPC, we got an approval to have another new HPC, which is relatively better than what we have currently. It will have 48 nodes, and overall we will go up to 4,600 cores, much better memory. So this is something we are looking for. Hopefully we'll have it. So we got an approval for it. This is good news. Now, when we talk about HPC, the applications of why we use it, because we are a good university, a good number of departments, so we can't perform most of the computation on single computer. We need HPC, and we use it for computational fluid dynamics, computational structural mechanics, seismic reservoir simulation, signal processing, computational chemistry, molecular dynamics, and so forth. The one topic which is not presented here, which I will present at the end of the simulation, which is the topic I'm mostly involved in. Anyways, so since we have limited resources, thanks to the available computational resources within the kingdom, since 2017, KSL team, they have been helping us. They have been helping us to perform different computational simulation based on, particularly on Shaheen 2. So since 2017, there have been 23 KFUPM users. We are working on 20 different projects, and we utilize about 40 million core hours. And this has to do mostly in material science, geoscience, and computational fluid dynamics. And I would like to take this stage and appreciate the nice and kind support of Aws, particularly KSL team. So if you join me, I would like to thank them with a round of applause, because they have been extremely kind. When I met here,
Khurram and also Mohsen. They have been very nice and helping us. Thank you. Keep doing it, please. Now, in terms of applications, I will not go into the detail of many. I have two applications. One is molecular dynamics and electrochemical corrosion studies. We use DFT computation. We use here HPC and DFT for PD alloys design, characterization of material. We use here a lot, one of the main areas. Now, I told you one area which was not mentioned earlier, which is my main core. I recently joined here, and my main core of simulations I perform is nuclear engineering. So this is the work I do a lot. I want to share here some of the future needs since I've recently joined. So I've taken two examples from my nuclear work. One of the work which we did in 2019, we performed direct numerical simulation. It's an accident scenario, but we mimicked it, simplified it based on the computational resources we had. One of the case we did is just an impinging jet on a wall, which replicates a nuclear problem. And we performed this work. It costed, we used 160 million degrees of freedom. We use a spectral element code, and it costed about 40 million core hours. So this is an example I intentionally put it because compared to, remember what I showed, we used 40 million core hours KFUPM when we were using Chaos Shine 2. So this just one example, we use 40 million core hours, and this I didn't perform it here. This is a CHISH cluster in Europe we did, so I would like to acknowledge them. So this is one example. Another example is nuclear fuel rods. When we have high-speed flow, they cause vibration, heat transfer is the main issue. Once again, we perform direct numerical simulation, but based on the computational resources we had, we reduced that power. But eventually what we did is we ended up 1 billion degrees of freedom. We performed this simulation and that costed us roughly 100 million core hours. And once again, this was performed at a CHISH cluster in Poland. I collaborate with them. So this is a food for thought. I recently joined here. So our computational demand will increase with time, a bit of heads up. So this is something within the kingdom we can also think for, because nuclear energy is well within the vision of Vision 2030. We are going cleaner, much more, and this is one of the things we will be working a lot at KFUPM. And with this, I would like to thank you for your nice attention. Thank you.
Now, the last speaker of the day is Aws Batch. The Contributor Mission.
Assalamu alaikum wa rahmatullah. Thanks a lot, Dr. May, for the kind introduction. Again, time is of the essence, so inshallah, I promise you I won't take very long, and hopefully within less than 10 minutes again. And again, it's an honor to be speaking here with you again in this final presentation. So basically, I'll be talking about medical AI from research to clinical production, and I'll focus mainly on certain key technologies that fall in line with the conference was all about. And I really hope that the audience will gain more insight and more potential, and will be motivated to carry on with basically the things that inshallah I'll be sharing with you in terms of advances in technology. I am from the Department of Computer Engineering, assistant professor, and specializing in machine learning and deep learning. And also I'm a certified trainer and university ambassador representing NVIDIA in the region through the Deep Learning Institute.
So the focus is mainly on medical AI. So medical imaging is an extremely exciting and critical component of modern medicine. And by the way, this talk is actually a follow-up to a presentation that was presented that actually inspired me to focus on this area more. And that was by a key speaker, Professor Yahya Bukhari, who spoke clearly about the need of using technology to serve certain aspects of research, and that is about medical imaging and labeling data. So this session is a continuation to that session. So with that in mind, medical imaging and also medical AI actually allows us to see the organs inside the body and even look at the cell level things that might actually go wrong. So devices that are used to acquire medical images are constantly becoming more and more advanced. They're becoming cheaper, faster, more accurate, and of course safer. With those advances come new capabilities for seeing inside the human body with even greater precision and greater volumes. And of course, since AI is nowadays fueled by the idea of the prospect of big data, each of these advances also present new opportunities for AI to enhance medicine. As you have probably known from any prior exposure to the area of deep learning, which is formed of the basis of neural networks and beyond, you need a lot of data to train these models. And all the recent advances in medical imaging have created larger and larger repositories, as was actually highlighted yesterday, especially with the conference theme. Repositories of medical data to learn from. So it's nowadays prime time for AI applications, especially in this domain, in this space. So we are living in an age where data is being produced faster than it can be consumed. And this is all so true, especially in healthcare, which has obviously been discussed a lot these days, and especially yesterday. So physician burnout, which is one of the major issues that, of course, our fellow colleagues from the College of Medicine or hospitals would agree on, which is, of course, a major topic of our conversation in healthcare these days. And much of the burnout is due to the increased data that the physicians are required to input and consume about their patients. The specific role of medical imaging is no different from the entirety of medicine in general. So while this presents burnout, it presents larger challenges for especially our kind colleagues who are radiologists. It also presents great opportunities also for AI, because AI can enhance efficiency, reduce human errors, and achieve goals with minimum human operation. So they are tools that help commission more easily find suspicious areas in medical images. Other applications of machine learning and also deep learning include reprioritization of clinical workflows so that needier patients are seen faster. And even more cutting edge and also our applications for personalized medicine, where deep learning can be used to search, for example, search incredibly large data sets these days to find patients who are like one another and suggest specific treatment plans based on treatments that were successful for patients who are more likely of them. So the life cycle of medical AI involves labeling data, which was introduced yesterday, so I won't be going too much about it. Also training the models, building and optimizing AI applications, and finally developing and monitoring these applications in a clinical production. So as AI researchers, we are constantly on the lookout for appropriate tools, platforms, and reference applications so that actually span across the entirety of the entire AI lifecycle in medical imaging. Once we have a robust AI model applications, and then that can build around for production development to evaluate workflow, and finally for production development for device clinical impacts. Leveraging the large quantity of medical imaging data, AI models are developed with principles of reproducibility, and this is an important factor.
To build more robust and generalizable AI models, the evaluation can be federated, which was also talked about today, federated with clinical collaboration from medical institutions. So to complete this loop, I will briefly introduce a key technology, which is called, maybe some of you have heard about it, maybe not. But if not, this is a great opportunity to learn about, and that is Project MONAI in a bit. So to better understand why developing domain AI is so difficult and hard for anyone seeking to build their own AI-based solutions from scratch. So we come to know by practice that building domain AI solutions is not just basically technology challenging, but indeed a collective ecosystem opportunity. So first, on this research and development front, reproducibility, as I mentioned before, is mission critical for validating medical AI. The magnitude of this issue is best captured through the results of the publication that was published in 2012 by Dr. Glenn Bigley and Dr. Lee Ellis. While it has been years since this paper was published, of course, nothing major has been changed so far. So researchers from both academia and industry are often seen to be constantly reinventing the wheel and are slowing down the pace of innovation. And we've kind of seen this in the presentations of the posters, where we see a pattern in these presentations where the same, for example, same techniques have been used are kind of limited, and there is always room for potential for further development in the area and also to serve the domain. So, for example, we often hear from colleagues that their AI models cannot be easily integrated due to clinical and operational challenges, which some of you might have actually experienced. And on the other hand, we commonly see researchers trying to get their hands on readable data files that are hard to come by. And of course, there are so many other challenges to face. Furthermore, clinical evaluations and deployment landscapes are even more complex. So cases can be seen through with no interoperability standardizations for AI workflows and so forth. So again, incorporating different models in and bringing these trained models from the R&D loop into an actual production is yet a big challenge. That is why Project MONAI was chosen to be presented in this session. So what is it? Project MONAI was originally started by NVIDIA, was actually a collaboration between NVIDIA and King's College London to establish an inclusive community of AI researchers, which is still growing until this day, for development and exchange of best practices for AI and healthcare imaging across academia and enterprise researchers. This collaboration, this is basically crowd collaborative open source community-driven project. And again, there is no catch. Everybody from the community can basically partake in this. That is built on a rich set of tools and frameworks and aid in the labeling of medical imaging data and the training of top-performing models of course, in a timely fashion. And in technical terms, I'll be focusing on 3 key technologies that I hope by the end of the presentation you'll be able to learn more about through through either contacting us directly or through just basically looking up the project. So the journey of medical AI really starts with unlabeled data sets, and any AI model is only good as the quality of the data that was used during training. And this is the first component. It has something called AI MONAI label, which actually aids in the challenge of solving the labeling issues with medical imaging. And of course, if anybody has done this before, has tackled this issue before, like dealing with missing labels or trying to overcome the issue of inconsistent data sets, this is where you can look into MONAI label and utilize the key technologies to be able to solve these issues and move forward. The second component, of course, once you have a good source and which we call annotated data sets, you need a robust training library. And this is where MONAI core comes into place. It does utilize specific hardware. So basically, you can actually start with simple GPUs, like for example, the RTX A6000, which contains 48 gigabytes of RAM. It's one of the top end or high end GPUs that you can consider. And Project MONAI actually
is actually built on something called PyTorch, which can be used to utilize these simple clusters that you can build either at home, or you can utilize any NVIDIA technology basically to carry out your medical AI research. So that's more and more. There's a lot, of course, to talk about it, but of course, this session won't be able to provide the means for doing that. Finally, we have Monai deploy, and that is basically you have the model. You would basically use it for deployment and testing within a clinical setting. So these three major components form the project. In summary, of course, this is a 10-minute presentation. I won't be able to talk and honor the topic, but I hope to encourage you to look into this key technology. There is also something called the Monai Zoo, and this is really interesting. That was just recently announced at the GTC conference. Is basically a place for researchers and data scientists to use and share the latest in great models. This is where there is a great opportunity for researchers, especially in this domain, to use and also collaborate with fellow researchers worldwide in the area whereby they've actually provided robust models that are freely available for training and also inference to be tested in various subdomains of medical healthcare, or basically medicine. So this is basically a screenshot of what you may expect. And this is an ongoing project. And again, the initiative is basically to allow us as researchers and anybody who's interested in medical AI to be able to obtain freely different models and also access to data. Again, data is a very crucial component, and it's really important for us AI researchers to obtain the data when needed. So that's basically Monai Zoo. The prerequisites, again, to start the investigation on Project Monai is basically you have to have an understanding of Python. Again, I'm targeting the students here. If you're interested, you can actually learn about, if you have Python knowledge, you can basically hop on, and basically you have to have some sort of level of understanding of programming to wish to tackle the bigger challenging issues of adapting the technology. And of course, it requires some concepts of understanding of deep learning, and of course, in medical healthcare. So with this, of course, I won't be able to talk deeply because this, again, the last session. I hope you've gained much knowledge and got inspired by what I've been able to share with you today. And I thank you for your patience and participation. And thank you.
And now we will open the discussion. And this is a reminder that the QR code is there for any questions. I will start with Mr. Ramadan. What are the major design constraints when planning cloud integration projects involving HPC work?
So I think all the building blocks that are required to have a full-fledged HPC system is available on the cloud. If you ask me, with all the constraints that we have today, you will have to design for applicability, which means even if you can run all the jobs on cloud, not really make sense in the sense of fast data movement and stuff like that. So you need to kind of qualify your jobs that makes more sense to run on cloud. That's the first one, design for scalability. The second is I believe we should also design for cost awareness. So it's infinite resources, which means you need, even if you have deep pockets, you can run out of it very quickly. So you need to be cost aware when you design. You need to have certain caps applied to make more sense out of the cloud investments you're making. I think the third one probably is design for data locality, because data movement into a cloud is cheap, but then getting it out is very expensive. So I think those are the constraints that makes more sense.
I have another question for Renan mostly. How can users outside UK use data?
So there are multiple ways. First is through research collaboration with faculty of AAU. So that access proxies. Otherwise, we do have a rent system in place where users can rent out nodes proxies based on the
Another question also for you. What are some of the future plans of the center?
So we're continuously improving and upgrading. So hopefully in the future we get bigger, better, upgrade our hardware and improve our systems.
I have a question for Dr. Akshan. How do you see the use of HPC for future solutions with nuclear emissions?
Yeah, that's a good question. Yeah, we, as you have been following news, we are from good in nuclear, we have good initiatives. So this is a food for thought for example, one thing which I can think of, at KFUPM, we have started nuclear. And this is my understanding that in Eastern region, we do not have Shaheen. So the question is, where is our Shaheen? This is maybe something we can think of for this region, and this can have nuclear also.
So for now, only inside the university.
Yeah.
Okay, Dr. Mustafa, I have a question. Can Kunai be used with the front-end application?
Yes, so basically, so this project, again, it does rely on high performance computing to some extent, depending on the hardware. So for anybody that's in the medical field, they can utilize the existing tools and frameworks that are currently used by physicians. Maybe some of them are using them for educational purposes, like OHIS, Web Standard, and also 3D Slicer, which is one of the famous tools that are used for performing analysis of data, and also labeling of data, sort of becomes also like for 3D and so forth. So there are, again, the project is still based on the analysis of data, does support multiple applications and still ongoing. Still time and hope that.
So if there is any live question from the audience. So we reached the end of the session today. I would like to thank the audience for their attendance, my speakers for their valuable information. Thank you very much. And now I would like to ask to honor the speakers with the certificates. The first one, the certificate, the thank you certificate for Mr. Bala Morgan Ramadan. Mr. Ryan Mosby. Mr. Akshan. Mr. Mustafa. Dr. Al Barwani. Dr. Kisuni. Mr. Edmondo Orloti. Mr. Ubaid Najjar. Mr. Muhammad Jahu.
Thank you.
Assalamu alaikum. Good afternoon. This is Mariam Dosri, a lecturer at Imam Abdurrahman bin Hassan University and a coordinator of the poster competition. The scientific poster competition is a significant part of this conference, and today we are delighted to announce the winners of this competition. But before we would like to take this opportunity and to once again thank the platinum, gold, and silver sponsors for this competition. The theme of the poster of the scientific poster competition is using HPC and AI to accelerate and improve medical research, which aims to encourage participants, especially students and fresh graduates, to share and present innovative ideas, research proposals, and in progress projects in the field of the conference topics. At the registration, we received 49 submissions from 12 different institutions, and 18 posters were accepted. And we have seen brilliant posters with great effort made, and they are evaluated by the evaluation committee. The members of the evaluation committee are Engineer Ahmed Al-Jashi, Engineer Saeed Al-Zahrani, Professor Panda, Dr. Sabir, and Professor Mahmoud. And we have received the positive feedback from the evaluation committee. Specifically, one of the evaluators considered all posters winners. Well done all. And now we are going to announce the winners. But before, we would like to welcome the Vice President for Academic Affairs, Dr. Ghazi Al-Ataibi, and the Dean of the Computer Science and Information Technology College, Dr. Abdullah Mhedib, to join us on the stage. The first place winners are from King Abdulaziz University, Sami Nawar, and the Professor Ahmed Berman. Please join us on the stage. And this is the poster. If you would like this to take 2 to 3 minutes just to speak about the poster, can you just us, please?
The human heart is the most important organ in the body of the human. The heart pumps the blood to all the motion in the body. Heart disease are known as a cardiovascular disease. A cardiovascular disease is the highest danger to the human. The human being hit around all the world. In 2019 cities caused the death of 17.9 million people over the world, which is very huge percentage. And this, we use the deep learning as a very powerful machine to classify the heart disease. We have the VCD signal. We use the VCD signal to classify the normal or abnormal heart sounds. In this work, we use the 3-point data set to compare the VCD to images. After that, we take it to the image 3D model and audio 3D model, and this model called VGI as an audio 3D model. We have a good validation accuracy. In the future, we will go to the VCD signal. We will use the reuse denoising to remove the reuse of the signal. Inshallah, we will try to increase this percentage to have a good diagnostic tool. Inshallah, we will try to take these models and deploy it for application. That means we will use this application for helping the doctor in the clinics, or can be used as in the telemedicine that will discover the cardiovascular disease. Thank you so much. Also like to thank this university for this conference and thank the committee and organizer of this conference. Thank you so much.
In the second place, the winners from King Abdulaziz University again, Reem Ahmed and Dr. Hanan Benjamin.
Assalamu alaikum. My presentation today is about autism spectrum disorder. Autism is affects about 1 out of every children in Saudi Arabia, according to new statistic in 2022. This disorder, maybe this surprised you, but you may be more surprised to learn that with so many people affected, its causes remain unclear and no drug for it. Only early behavior can help the children's lives, but unfortunately, the current diagnostic method for ASD is costly, take a long time, and it's maybe more subjective to differences in clinical training tools. So genetic and environmental factors linked to ASD cause brain abnormality. A recent advances in structural MRI can overcome for objective diagnosis by highlighting busy potential biomarker. And this is the aim of my in progress work, which is to develop machine learning optimized for classify autism spectrum disorder from healthy people using structural MRI. I used two publicly and heterogeneous data sets, one for training and the other for testing. Also, I collect the data from King Abdulaziz Hospital. To my knowledge, this is the first Saudi data set for MRI in ASD research. I used 4 models for training this data, and since the model effects are related, very related to data quality, I use data pre-processing steps to pre-process my data. I use FreeServer, which is the best software for neuroimaging data in general. It takes 10 hours for pre-processing each image. So here I leveraged the power of higher performance computer Aziz by using 24 CPU in parallel and run the pre-processing steps on 24 images at the same time. Totally before, if I use this software on my PC, it will take 280 days. But after I using a supercomputer, it only take 11 days. For optimization, my model, I also used feature selection and particle swarm optimization, also grid search for hyperparameter tuning. This step also will take time and make the training slow. As a result, for training, the result in 20 experiments I did also above all of them above 18, And this result presented here is just for data set, this data set. I get the best accuracy with support vector machine and as well optimization method for only 24 features, which is belong to thickness of 66 brain regions. This result also related to clinical feature as the particle thickness in the frontal lobe. It's very related to the disability in social communication and environment, also related to repetitive and restricted activities in ASD children. Another example is the temporal lobe. It's the thickness in temporal lobe region, very related to motor disability. So in the conclusion, I conclude that the structural MRI biomarkers with machine learning can help to early diagnosis ASD. While they are promising, they have not achieved that expected success accuracy diagnosis. We need still more data. We need increasing computational power, including high performance computing. And we need more and reliable, faster machine learning models. However, this result brings us closer to understanding the biological basis of this disorder and also make the prediction start from 5 years. In the picture, I will use the new sharing dataset, publicly dataset, which is entered for infant from 1 month to 2 years. I will change the work on this dataset and I will check the result and the accuracy. So if it gives me a good result, here I will make the diagnosis very early from 1 month only. Also, I will use deep learning model with augmentation technique, as I have here just 600 images, and we need to collect or make more data by another technique. Just thank you.
Thank you. In the first place, the winners of the HPC scientific poster competition are from KPUBM, Mona Zahrani,
Good afternoon, everyone, and thank you so much for attending. And I'm going to tell you a bit about our work. So in this we were trying to find to implement a model for antigen specificity in order to find a vaccine or what is the process component of the vaccination to any virus actually. But the showcase that we have used that is the recent one, which is the happened in the pandemic of 2020, which is coronavirus. This one is working or interested only on a specific part of the amino acid, which is called the CDR HFA. This part is a very crucial part in order to know if this would be a good vaccination or a good component of the vaccination to a specific virus. So we have used data set that published by the Oxford University, and I would also add a contribution to it. Is we looked at more data in order to make this a balanced data. And we have used several ways of feature extraction. We have used something that is called the ID and frequencies, and we also use another 3 additional feature extractions from the AI feature. For the classification models, we have tried more than 250 trials in two sections or in 2 scenarios. The first thing that we have tried the IDs and the frequencies, and have just noticed that the best result can be gained by the IDs. So we just took this result and we have replicated the work again. Additional with the I feature, which those features are actually, they are so sensitive to the bio classical features of the amino acids that we will feed into the model. And that will enhance the accuracy of our result. And we end up by 88% accuracy with using the CDT and the ID. And for the best to our knowledge, that this is the first work actually in combining the AI in predicting the best component of any vaccine for any virus of the future. Thank you. Supporting this work, and we will thank the organizer of the HPC. Thank you all.
So thank you all for listening. And next, a presentation of the hackathon competition with Ms. Reem Assad.
Assalamu alaikum wa rahmatullah. Hello everyone, I am Reem Assad, a lecturer at the Imam Abdurrahman bin Faisal University and an organizer in the AI and Healthcare Hackathon. Today I have the pleasure to announce the winners of the hackathon, and it was organized under the patronage of His Excellency, the President of Imam Abdurrahman bin Faisal, Dr. Abdullah Bish. The hackathon was an 48 journey with interesting challenges to find innovative AI solutions to recent trending problems in the medical field. The hackathon was conducted online. We've had 76 participants in 22 teams. In 22 teams from 10 Saudi universities. We have seen great efforts made in these projects, and I'm happy to announce the winners shortly. First, we'd like to thank our platinum, gold, and silver sponsors for their contribution to the success of this conference. We would also like to extend our thanks to Zaka, the community sponsor of our organizing the hackathon, that helped organize and execute the AI Hackathon Healthcare. Zaka is an AI education company with the mission of democratizing AI. The judging panel reviewed the projects based on innovation, correctness and technical soundness of AI solutions, prototyping quality, and now, for the moment we've all been waiting for, announcing the winners. Given that the hackathon was online, some of the participants were not able to fly here. They will join us virtually, but if you are here at the conference and you hear your name, please come up to the stage. I am pleased to announce the winner of the third prize is DMN from Imam Abdurrahman bin Faisal University. I would like to welcome the Dean of Computer Science and Information Technology, Dr. Abdullah Mhedib. In second place, the runner-up team is AI Pioneers from Imam Abdurrahman bin Faisal University. With Ahmed Jabali, Rahaf Al-Qahtani, and Afnan Mahran. In first place, the winning team of the hackathon is NARS from Prince Sultan bin Abdulaziz University. The members are Arman Ziad and Native Hpc. Are they here? I think they're online. Congratulations to all of our winners, and thank you to all of our participants, and thank you for joining us today. And now the concluding remarks with Dr. Abdullah Mhedib.
Assalamu alaikum everyone, and good evening. On behalf of my colleague in Computer Science and Technology, on behalf of the organizing committee, I would like to thank all the distinguished speakers. We have over around 50 speakers from the HPC community, from AI community, from the medicine community. I would like to thank them for joining us these 2 days, sharing their experience, enriching our community. And I would like to thank also the audience for their engagement with the speakers. I would like to thank the sponsors, our partners, for making this conference a success. I would like to thank also the organizing committee for the hackathon posters. It was very full, engaging 2 days. I hope everyone enjoyed benefits for these 2 days. Tomorrow we'll have also a full day of workshops. We'd like also to ask you to join us and benefiting from these also full experience workshops. So thank you again for joining us in Dammam, in Mount Humphrey, University. Okay, so we'll announce also those who engage with us in the Twitter account, social media, and would like also to thank those who attend the conference remotely. So also we have very good engagement from different universities. We have around 14 universities engaged with us in the poster, in the hackathon, also in these. And hopefully, we would like to welcome you in future events in the Imam and Imam Faisal University. So thank you all. So we'll announce the winners, and we'd like to have a group photo of the speakers with the audience as a memory of this event. So thank you.
Assalamu alaikum, I'm Nora Dhafir, and I'm going to announce the winners. So basically, we distributed the number card, and the number that will show on the screen will win. Inshallah, we will have 3 winners. Number 25. Who has number 25? Okay, we'll try again.
Lucky one.
خلاص وصلنا بس اعطيها الجائزة.
Okay, now we will announce the winners that participated in the hashtag INU_HPC22, the most interactive tweet. The first place is
كلها بالاسم كلها بالاسم.
the first account won Fadila. Is Fadila here? Okay, the second place is Lujane.
حطي اسم
كيف كيف مو مسوي شير
استغلنا هنا.
اوكي نقدر الاول اوكي
Yes. The third winner, the best tweet is Manian. Are you here, Manian? Congratulations for all the winners and hard luck for the one who did not win. And thank you so much for your attendance and your time. Hope you enjoyed it. Thank you so much. Thank you.
The right to have the babies.
Ah, so then, so they autonomize. Yeah.